6 months ago, I set out on a journey to learn how to apply machine learning to games. This was sparked from an interest after seeing what was possible with AlphaGo and what was happening with StarCraft. Also, it was sparked a little bit by none other than CodeBullet. I mean, have you seen some of his videos? Anyway, this leads us to where we are now. This entire course goes through 4 different deep learning projects which use reinforcement learning to train machine learning models, aka AI, to play games. There are 4 distinct projects, including Mario, Streetfighter, Doom, as well as creating our very own custom OpenAI gym environment to play the Chrome Dino game. That last one will open up the realm of possibilities as to what's possible with reinforcement learning, because you can take that project and apply it to just about any game that you want to. Anyway, hopefully you enjoyed this course, kick it off and see how you go. And if you do get some value out of it, please do like, share and subscribe. It'd mean the absolute world to me. Anyway, good luck guys, have fun. What's happening guys? In this video we're going to be taking a look at how we can build an AI model, but specifically a reinforcement learning model to be able to play Mario. As per usual, we're going to be treating it as though we're performing a developer or data scientist and client relationship, so you'll be able to see the back and forth as we go and build up this model. Ready to do it? Let's go take a deeper look as to what we'll be going through. So in this video, we're going to be focused on a couple of key things, but the main goal is to be able to train a machine learning model, or specifically a reinforcement learning model. Don't fret if you don't know what that is. I'm going to talk a little bit about it later on. But we're going to build a model to be able to go on ahead and play Mario. So ideally, we want it to smash through levels and effectively be able to collect coins and get to the end of each world. Now, how are we going to go about doing this? Well, first up, what we're going to need to do is set up a Mario environment. So this means that we're going to need to be able to get Mario to be able to interact with some Python code. So I'm going to show you how to do that. Then we're going to pre-process it for AIifying it. So this means that we're effectively going to be able to pre-treat our environment with a couple of pre-processing steps just to make it a little bit easier for our AI to learn how to play the game. Then we're going to use a technique called reinforcement learning to be able to go on ahead and teach it to play Super Mario. And then last but not least, we're going to be taking a look at the final results. And as per usual, we're going to be treating it as a data scientist / developer client relationship. So you're going to be able to see some of the back and forth as we go on ahead and build our model. Ready to do it? Let's get to it. Yo, Nick, you're into Python, right? Yeah, why? You reckon you can use it to play some games? Say no more, Jimmy.
So Jimmy wants us to get a game running with Python. Well, as you might have guessed, we're doing Super Mario. In order to do this, we're going to be coding with Python in Jupyter Lab, and we're going to be using OpenAI Gym. This is a common framework that makes it easy to train AI to play games and interact with other simulated environments. Think AlphaGo, but on a smaller scale. For our mission, we can use the Gym Super Mario Brothers environment that's been built on top of the NES emulator for Python. Let's do it. Alrighty guys, so welcome to the Mario AI tutorial. So in this video, we're going to be focused on building a full-blown reinforcement learning model or AI model for Mario. Now, in order to be able to do that, we are going to need to go through 4 key steps. So first up, we're going to set up Mario. Then we're going to take a look at how we can pre-process our environment. We're then going to train our reinforcement learning model, and then we're going to test it out. Now, the first thing that our mate Jimmy asked us to do is just to see whether or not we can even play Mario using Python, given the fact that we're Python focused here. So that's exactly what we're going to do in this section up here. Now, I'm going to be coding all of this in Python, and the environment that I'm working in case you haven't seen something like this before, is called Jupyter Lab. This is great whenever you're building machine learning models or doing data science and all that type of good stuff. So the first thing that we're going to go ahead and do is set up Mario. Now, in order to do that, we're going to be installing 2 key libraries. That's a little bit too zoomed in. We're going to be using Gym-Super Mario Brothers, and then we're going to be using 7.3.0. That's fine. I'm going to show you how to use it. Now, before I jump into that too much, this basically allows you to play Mario using Python. So we've got a whole bunch of different types of environments, and this is what we're going to call our game and a game environment. We've got a bunch of different environments that we can effectively use. And the great thing about this is that we can easily set it up to be able to train deep learning models or reinforcement learning models later on. So it's pretty cool when it comes to using it for AI. So we're going to be using this and installing this. And we're also going to need NestPy, which effectively allows us to build a virtual joypad for Python to be able to play around with our Mario game. Now, all of this is based on top of a framework called OpenAI Gym. This is a really popular framework. So if you've seen any of the AI that Google builds to play AlphaGo or any of the AI that OpenAI builds, they're actually using this a lot for their reinforcement learning applications. And you can actually see some of the different environments they've got available here. It's actually really, really cool. If ever you get a chance to check it out, by all means, do go and check it out. We've also got some other videos on the channel that talk a little bit about it. But for now, enough blabber. Let's actually go on ahead and install some dependencies. So that's the first thing that I'm going to go on ahead and do. So I'm going to write it and then I'm going to explain what we've gone and done. Okay, so that is our first line of code written. So it's just a single liner. And what I've gone and written is pip install. So exclamation mark pip install and then gym underscore super underscore Mario underscore bros equals 7.3.0. So that is effectively installing this, and it's going to be what allows us to play Mario in Python. Then I've also gone and installed nest underscore py. So this is no different to how you might go about installing a regular package whenever you're writing any of your Python code. So we've gone and installed that now. That is all well and good. What we now need to do is actually import it into our notebook to be able to start setting this up. So let's go on ahead and import our dependencies, and then we'll be able to set up our environment. Okay, so those are our dependencies now imported. So I've gone and imported three key things there. So first up, we've gone and imported the game. Now, in order to do that, I've written import gym underscore super underscore Mario underscore bros. Then I've gone and imported the joypad wrapper. So in order to do that, I've written from nest underscore py dot wrappers import joypad space. I'll talk about this a little bit more in a second. And then the last thing that I've gone and done is I've gone and implemented or imported the simplified control. So I've written from gym underscore super underscore Mario underscore bros dot actions import simple movement. This is really important. So a key thing whenever you're building AI for games is to try to simplify the environment as much as possible, because the more complex it is, the harder it's going to be for your AI to learn how to actually play that game. So what we can actually do, or what we're doing in this particular case, is we're simplifying the amount of actions that our Mario character can take. So this simple movement variable over there simplifies what our Mario character is going to be able to do and what our AI is going to learn to do. So what we're doing is we're simplifying it down to 1, 2, 3, 4, 5, 6, 7. So there's only going to be 7 different types of actions that Mario can actually take using our AI. And this is common practice, right? If you actually take a look on the official PyTorch repository, they actually simplify this even further to just 2 actions. We are going to be taking these actions. So we can either take no option or no operation. So that means no key. We can hit right plus A, right plus B, right plus AB, A, and then left. So these are going to be the different actions that our AI is eventually going to be able to take. And then what we need to do is we set up our game using gym underscore super underscore Mario underscore bros, and then we wrap it inside of this joypad space wrapper. So you're going to see wrappers a little bit more once we go to preprocess environment. But for now, just know that we've gone and imported the game, we've gone and brought in some wrappers, and we're going to simplify our movement using this. So now that that's done, we can actually go on ahead and set up our game. So this is akin to effectively turning your Nintendo on. So let's go on ahead and do it. Okay, so that is our game now set up. So I've gone and written 2 lines of code there. So I've written env equals gym underscore super underscore Mario underscore bros dot make, and then to that we've passed through this option here, or this parameter. So I've written super Mario bros dash v0. So if you take a look inside of the documentation, you've got a bunch of different types of environments. Now I keep saying environments, but just think of your environment as your game. So where our Python code is going to be running against, and effectively it's an emulator. So we are going to be using this environment, which is just Super Mario Brothers, and we're going to be using the standard version. You can also play the downsampled version. So if you take a look, this is much more pixelated versus this to this. We can take it one step further and effectively go to pure pixelated, and you can even go down to one which is just a rectangle. So that is Mario there, that little red block. You can even go play Super Mario Brothers 2. So there's a whole bunch of different versions, and effectively whatever you go and pass through into here is from here. So we can choose which version we actually want to go and play. So that's that. The second line of code is, remember I said we're going to be wrapping our environment to be able to use those simple movement actions. So if we actually, let me actually just hold that off so I can show you the different spaces. So if I go to env.action space let's go .sample, you can see here that there are 200. Let me actually just show you the number. The fact that this has come back and said discrete and 256 means there's 256 different button combinations that you can actually go and play, which is going to take our AI a ton of time to actually go on ahead and learn. Now, by wrapping it inside of this joypad space wrapper over here, we can simplify that down. So right now it's 256, which is way too high. It's going to be way too hard for our AI to learn how to play this. If we go and wrap it, you can see we're dropping it down to 7 now. So this simplifies how our AI is going to be able to learn how to actually play Super Mario. Cool. So that is now done. So we've gone and written those 2 lines. So the second line is env equals joypad space, which is what we brought in from up here. And then to that, we're passing through 2 keyword arguments, 2 positional arguments. The first one is env, and the second one is simple movements, and what we got from over there. Cool. So let's go on ahead and play it now. So we've gone, I also showed you the action space as well. So whenever you're working with these environments, so specifically OpenAI Gym environments, there's 2 key tips that I can recommend. If you go and take a look at the observation space, this tells you what you're actually going to be getting back from your environment, in this case, your game. So we're going to get 240 pixels by 256 by 3, which is effectively a frame from the game. And then we can also take a look at our action space, which in, we don't need the dot shape, which in this particular case tells us that we've got 7 discrete actions. So for example, up, down, left, right, A, B, so on and so forth. But really in this case, there's these simple movement actions. Let me show you that again. They're these actions. Okay, so that is a little bit about our environment. Let me actually show you how to actually go and play it. So let's go on ahead and write this loop. So we're effectively going to loop through and take some random actions. It's just going to be pretty random at this stage. So let's go on ahead and do this. Okay, before I run this, let's actually go and comment it together. So the first thing that I've gone and done is created a flag. And I've set this to true. And this tells us whether or not to restart the game or not. Restart or not. So by setting it to true, I'm effectively telling the environment or the game that we need to start a game to begin with, because right now we don't have one started out. Now to start a game, we can run the command env.reset. So this just resets our game. It's like turning your, I don't know, your GameCube or your, I'm trying to think, turning your Switch on and off. So env.reset allows us to restart the game. So that is what we're doing here. So basically we're going then and looping through every single frame of the game. So think about your game as being a set of frames. So you do something with each frame. So something updates on your screen, you press a key. Something changes on that screen, you press another key. This is what we're doing here. So for step, or this could just as easily be frame. For step in range, 100,000. So we're going to take 100,000 frames. And then colon, if done, because keep in mind our game hasn't started yet, so we've gone and set it to true. So we are going to reset our game. So this is effectively start the game. Start the game. Let's add another comment here. Loop through each frame in the game. Start the game to begin with. And then what we're going to do is we're going to take a step in the game. So we can use the method, so env.step. And this is like passing through an action to your game. So it's like pressing a button or moving a joypad or changing a control. So env.step allows us to pass through an action to our game. So it could be jump, move right, move left, so on and so forth. So in order to do that, we can type in env.step, and then we're just going to randomly take steps. So this line here allows us to randomly take steps. So env.action_space.sample allows us to take random action. So let me show you this before we get into it. So env.action_space.sample is just getting random actions, which is from this simple movement list here. Let me show that. Right, so we're taking random action, random action, random. Let me zoom in so you can see it a bit better. Random action, random action, random action, random action, random action. So you can see that as we're going to go through, we're going to just take random actions, because right now we don't have any smarts, we don't have any AI to actually go on ahead and play Mario. So we're just going to do that to begin with. Okay, so we're at the env.step line. So this is just going to just take random actions, take random actions. Actually, it's more do random actions. And then what we're going to get back from taking a step is we're going to get back the state, which is, I'll explain that a little bit more in a sec. We're going to get back something called a reward. We're going to get back whether or not we're dead or not, or done or not. And we're also going to get some info. Then we run env.render. So this allows us to show the game on the screen. And we are also able to close the game using env.close. Right, so if I run this now, this should effectively allow us to see just Python randomly playing Mario. And you can see that there. Let me, no, why did I do that? All right, so that looks a little bit better. So you can see that that is Mario now effectively playing. But he's just getting up to the pipe and he's not able to jump over because we haven't actually embedded any smarts in this. And as soon as that timer gets to 0, it's going to restart the game. So let's let it run out. Right, so it's restarting, it's jumping over one pipe, doing nothing, sort of getting stuck there because it doesn't know how to actually jump over the pipe. We haven't actually added any smarts yet. But now keep in mind, Jimmy just asked us to be able to get our Python environment up and running. So for now, we've at least fulfilled that initial first mission. So we've got Python playing Mario effectively, but we definitely want to take this further a little bit further on. And you can see he's clearing that first one. And you know what? He's only clearing that first one because he's taking just random actions. And one of those random actions just happens to be jumping, which you can see there. He's jumping to the right. Okay, so again, that's just going to keep on going until we stop it. So we've gone and run it for 100,000 steps, which is a ton. So we can just go back into our notebook, hit stop, and that is going to stop the game. We can also run env.close. If it's still popping up down there, you can see, let me zoom in so you can see that. So you can see we've got a little Python icon running down there. We can actually go and close that down, just running env close. It's going to shut it down. Cool. Okay, so that is our environment now running. What else did I say I was going to... let me just quickly take you through env.step before we go back to Jimmy. So if I type in env.step and pass through action 1, what's happened there? We've got... All right, so if you get this OS error, exception, access violation, blah, 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 this basically means that there's a little bit of a mismatch between your notebook and the simulator or the emulator. So all you need to do is just go to kernel, restart the kernel, and you can get through that. So then what you need to do is just unfortunately go and rerun these imports. So if I rerun that import and then go through, that is effectively back up and running. So now if I go and run env.reset or env.step, let's run reset first. So you can see that we're getting these values back. Now these values that we get back are what we call a state. Now, a state in this particular case is just the frame from the game. So let me zoom in on that. So it is going to be 240 pixels wide by 256 pixels high by 3 channels. So it's a color image. So we're going to be able to give this color image to our AI later on to try to learn how to play Mario. What else do we get? So that's env.reset. Now, if I go and take a step, we get back some more information. So if I run env.step, and let's just take a random action for now, we're actually going to get 4 things back. So if I show you the length of this, right, we actually get 4 values back when we run env.step. So if we go and run this and grab the first value, so the first value is getting our state again. So it returns a new state after we've taken an action. So imagine you jump, what you're going to get back is the frame after you've jumped. So ideally Mario should be up in the air. Then if we go and run, so what is our second value? Our second value is our reward. Now this is, I'll talk about this a little bit more once we get to actually training our reinforcement learning model, but just think of this as whether or not you've done something right in the game. So whether or not you've got a point or not. I'll explain let's actually take a look at how this works. So the way that the environment works is using this reward function. This is really, really important. So what's going to happen is, or in this particular case, the reward function is based on, or it has a main goal. And that main goal is to move Mario as far right as possible, as fast as possible without dying. So every time we get him to go to the right, we get some sort of reward. Now, in this particular case, you can see that that reward was 0, and that's because Mario's probably hit that pipe and is no longer able to go further right. Hence, we're getting a 0 back. Now, we effectively train our AI to maximize that reward. That's what we're going to be doing in a second. So in this particular case, we've got 0, but that's fine. Eventually, our AI should be able to get some more reward. The third thing that we get out of this is whether or not we're dead or not, or whether or not the game is done or not. And the fourth thing is we just get some info back. So the number of coins we've collected, whether or not we're at a flag, the number of lives we've got, our score, our stage, our status. And you can find more about this inside of the documentation. So this tells you a little bit about the info that you're getting back. And I'll link to this as well as all the code for this tutorial in the comments below. What else do we get? What world we're on, our X position in respect to the screen, and our Y position. Cool. Okay, so that is Python playing Mario. Again, it's pretty basic at the moment, but we've successfully, let me expand this again, but we've successfully been able to get our Python environment playing Mario. Let's jump back over to Jimmy and see what he thinks.
Yeah, that's cool, but can't you, like, AI it? Build some sick model to actually play the game? Yeah, well, you kind of got to pre-process the game first before we can get to that. Well, chop chop then. Get pre-processing, mate.
You know what they say about data? Big data, big, shit, wrong quote. I think what I meant is rubbish data, rubbish AI. In this case, it's no different. We need to pre-process our Mario game data before we AIify it. We're going to apply 2 key pre-processing steps, grayscaling and frame stacking. Our AI is going to be taking in images of the Mario game to learn. A color image has 3 times as many pixels to process, so converting it to grayscale cuts down the data it has to learn from. Frame stacking helps our AI have context. By stacking consecutive frames, we're effectively giving our AI model memory. It'll be able to see Mario and his enemies' movements. Time to pre-process. Okay, so Jimmy was kind of impressed, but not super impressed, right? But we also know that from here, we actually need to start pre-processing our environment to be able to start building AI to work with Mario. And so that's exactly what we're going to do. We're going to start pre-processing our environment. So we're now up to step 2. Before we do that, let's actually clean this up a little bit. So we don't actually need this observation space bit. We don't need that. We don't need that. And we can get rid of this and this. So all that we're left with at the moment is our imports, setting up our game, and then actually testing it out. But again, all this code as well as all the final code is going to be available in the description below. So you can actually take that and run with it. Cool. So the next thing that we're going to do is pre-process our environment. Now, as per usual, we've got to import a couple of things before we can actually go on ahead and do this. And the majority of these things are going to be wrappers. So keep in mind, we wrapped our environment once already inside of this joypad space environment, or this joypad space wrapper. We're going to now bring in a couple more wrappers. So let's go on ahead, bring these in, and then we'll take a look. Okay, so I've gone and written a bunch of lines of code there, but I realized that we haven't actually gone and installed something that we're going to need. So I'm going to come back to that in a second before we run this, but let's actually take a look at what we've written so far. So what I've written is from gym.wrappers import frame stack, comma, grayscale observation. This is going to do 2 things. So frame stack is going to allow us to capture a couple of frames while we're actually playing Mario. Now, this means that our AI model is eventually going to be able to see what happened in, let's say, for example, the last 4 frames. So we'll actually be able to see what direction Mario was moving in, what direction our enemies were moving in. how we're actually interacting with the environment. Because otherwise, say for example, we just pass through one frame to our AI, it's only going to know what's happened right then and there. It doesn't have any concept of where our enemies are moving or what position or velocity Mario is actually moving at. So we're actually going to use this to stack some frames together. So think of them exactly as stacking them together to be able to train our AI. Then the second thing that we've brought in is grayscale observation. So this actually allows us to convert our colored game into a grayscale version. This has a really great effect of actually cutting down the amount of information our AI model needs to produce, because a color image is effectively whatever the image size is, so by the height and the width, multiplied by 3 channels, because you need 1 channel per color to represent red, green, and blue. If we make a grayscale, we effectively shave it down by a third. So rather than dealing with 100% of data, we're only dealing with 33%. So it means that we can deal, or we've got less data to process to actually get our AI to work. And this means that our AI is going to be faster when it comes to actually interacting with it as well. Then we've brought in some vectorization wrappers, and this is where I realized we haven't actually gone and installed some stuff. So when we actually go and implement our reinforcement learning model, so our AI model, we're going to need to vectorize it in order to be able to actually use it with our AI. And the AI library that we're going to be using is called Stable Baselines. It was originally built by OpenAI, and then a bunch of open source guys went and cleaned it up and made it a bunch better, and implemented a ton of extra stuff. So there's some great vectorization or great wrappers inside of that. So let me read you out that whole line. So it's from stable_baselines3.common.vec_env import vec frame stack and dummy vec environment. So our vec frame stack allows us to work with our stacked environments, and our dummy vectorized environment, it just wraps our base environment inside of a vectorization wrapper. So just think of it as how you need to transform your model to be able to pass it to your AI model later on. So I'm gonna show you how to do all of this. And then last but not least, I've brought in matplotlib. I'm gonna use this to show the impact of frame stacking. So you'll actually be able to see that. All right, but before we go on, we've actually got to install some stuff, because this right now, without actually going and installing some stuff, is actually going to throw an error. So I've got it installed in my environment, but I want to show you how to do it. So the first thing that we need to do is install PyTorch. And to do that, we just need to go to pytorch.org. And again, I'll include this link in the description below. And then we just go over to here, hit install, scroll on down, and you've got a bunch of options, right? Depending on the type of machine that you're working on. So I'm just going to choose stable, hit Windows, the way that I want to install. And so if you're on a Mac, hit Mac. If you're on a Linux machine, hit Linux. We're going to use Windows. Then we need to choose how we want to install the package. So we're going to use pip, good old pip, and then the language that we want to install it for. So we're going to choose Python, and then the compute platform. So this is where things can get a little tricky. So if you have a GPU on your machine, which I recommend for this, or recommend using for this, if you've got a GPU, then you need to be, and you want to use it to train your AI model, we need to have CUDA running, or some sort of GPU acceleration running. So if you're on Linux, you can also use RockM. In this particular case, we're running on Windows. So we're going to choose Windows. And the CUDA version that I've currently got installed is CUDA 11.3. So if you're not too sure how to install CUDA, I've actually got a video on how to do that as well, but I'll link to that below. Where was I going with this? So you choose the compute platform, and this is purely, so you want to choose one of the CUDA ones if you want to use a GPU. If you don't have a GPU, that's perfectly fine. You can still do this. Just hit CPU over there. And then to actually go ahead and install it, you just need to copy the command down the bottom. So I'm going to choose the CUDA 11.3 one, because that's what I've got. And I'm going to copy that. So copy this command. And we can go back into our notebook, paste that in there, and then delete the 3 and then run that. We've got some error in our syntax. What have I gone and done? Add an exclamation mark. Cool. So in this particular case, we've got PyTorch already pre-installed, so it's installed relatively quickly. Now, the next thing that we need to go on ahead and do is install Stable Baseline. So this is going to be let me actually show you, or Stable Baselines 3. So this is a reinforcement library. So if you've ever done any machine learning or data science or AI type stuff before, this actually gives you a whole bunch of different algorithms that you can use to train your AI model. Now, in this particular case, the type of deep learning that we're going to be using is called reinforcement learning. It's great because it allows you to work with different types of open environments. Now, these are the algorithms that you've got available. So A2C, DDPG, DQN, HER, PPO, SAC, and TD3. I'm not going to go into a ton of detail. We're going to be using PPO. So it stands for Proximal Policy Optimization. Don't ask me to explain that in great detail, but basically think of it as an algorithm we can use to train to play our game. So we need to install this. So let's go back and let's take a look at our installation steps. So in order to install it, we just need to run this line here. So pip install stable dash baselines extra. So we're going to copy that and we are going to paste that in. Let's just double check. Do we need anything else? Nope, that's all. So let's go and install stable baselines. Now, the reason that I went and installed PyTorch before running this is this stable baseline package will actually install PyTorch. But if you want to use a GPU, you need to force or run it that installation, the custom installation for a GPU to begin with. So just keep that in mind if you want to use your GPU. If you don't, perfectly fine. So I'm going to include an exclamation mark there, and I'm just going to add a comment for good practice. So install stable baselines for RL stuff. Cool. All right. So that is all installed. Doesn't look like we've got any errors there. So that is all good to go now. So we've gone and installed PyTorch, and we've also gone and installed stable baseline. So the line, so I'm not going to read out the whole line for the PyTorch. That's just from the PyTorch site. The line for stable baselines is exclamation mark. Let's zoom in on that. Exclamation mark pip install stable dash baselines 3. And then inside of square brackets, we'll pass through extra. That just installs some nice little extras for us. Okay, cool. That is that installed. So we've installed PyTorch, we've installed stable baselines. We can now go on ahead and run our imports. Okay, so that's imported successfully. So I just went and ran this cell. You can see no errors there. We've gone and imported our frame stacking wrappers, our vectorization wrappers, and we've also gone and imported matplotlib as well. Cool. All right, so the next thing that we actually want to go on ahead and do is wrap our environment inside of these additional wrappers. So we're actually going to start off with this. So we can actually just copy this. And this was how we set up our game to begin with. Now what we're going to do is we're going to apply some pre-processing. So let's actually comment this a little bit better. So this is create the base environment. And I'm actually going to number this so you can see the different pre-processing steps. So that's the first one. Then the second one is simplify the controls. Because remember, we had something like 200 different controls before we went and applied our simple movement wrapper over the top of it. The next two that we're going to do are, we are first up going to grayscale our environment. So we're going to grayscale. We are then going to, what's the first one? We're going to wrap it inside the dummy environment. And then last but not least, we are going to stack the frames. Okay, so let's go on ahead and do this. Okay, so that is our environment now grayscale. Now I've only done one line so you can see it. We're actually going to visualize this one at a time. So if we go now and run state equals frame env.reset, what we should get back is a frame. So if I type in state.shape, so what we're getting back is, so remember, cast your mind back to, actually, let me just run this so you can see it. So this is our first environment, right? So if I comment out our grayscale and run reset, you can see that we've got 3 channels. So it's 240 pixels by 256 pixels by 3 channels. This is a color image. So if we now go in and let's actually visualize it. So if I type in plot.imshow and run state, so that is our Super Mario environment in its color form, right? So you can start to see that there. And so what I've basically just gone and done there is I've grabbed the frame from env.reset, and then we can pass that to plot.imshow to actually be able to visualize it. This is using matplotlib. So use matplotlib to show the game frame. Okay, so you can see that right now we haven't actually gone and done any pre-processing. It's still a color frame. Now what we want to do is actually go and grayscale this observation. So if I go and run env equals grayscale observation, which is what we brought in from our gym wrappers, and then we pass through env and then comma keep underscore dim equals true. And I'll explain that a little bit more. So we need the keep underscore dim to be able to use or stack our frames later on. Otherwise it just throws, let me actually show you it without keep dim equals true. So you can see it gets rid of the, well, let's actually, hold on. That's color too. So this is with keep dim equals true. So you see that we retain this last channel. If I delete this, you can see it gets rid of that last channel. We need that last thing to be able to do the frame stacking, which I'll explain a little bit more. Okay, so now if we go and visualize this, so we've now gone and applied our grayscale. If we go and take a look at it, you can see it's now gray. So in this case, Matplotlib plays around with the colors, but this is actually a gray frame that we're getting from our environment now. So this effectively cuts down the amount of information. Now by how much? So the number of pixels that we've got to process is 240 pixels by 256 by 1. So this means that we have 61,440 pixels to process when we're grayscaled. Now keep in mind, when we're not grayscaled, we have 3 channels at the end. So it means that we're going to be processing 184,320 pixels. So significantly more data that our AI model is eventually going to have to process. But we are going to grayscale it, so we don't need to worry about that. So we can delete those, and let's leave that for now. Okay, so the next thing that we need to do is wrap it inside the dummy environment. So let's go ahead and do this. I actually just realized we're not going to use this frame stack. We're going to use this one. So we can actually drop that out of our import. So let me just quickly go through that. So remember, from gym wrappers, we imported frame stack and grayscale observation. We don't actually need this frame stack, so we can get rid of that. Okay, so we're going to wrap it inside of the dummy environment. So let's go ahead and do this. Okay, so that is our environment now wrapped up inside of our dummy stable baselines vectorization environment. So if we now go and run it, again, what you can see there is that we are now inside of another array. So we've now gone and placed it inside of another effectively set of arrays, right? Or list. So if we go and visualize now, it should throw an error. That's fine. If we go and just pass through 0, again, we can still get our frame out. So you can see that each time we do one of these processing steps, the shape of our data changes slightly. All right, now the last thing that we want to do is, let me actually take you through this line of code. So I've written env equals dummy vec env, so what we imported from over here. And then to that, I've passed through a set of square brackets. So this is a list, and then we're specifying lambda env. So it actually returns an environment back to our dummy vectorized environment. Last thing that we need to do is stack our frames. So let's go ahead and stack our frames. Okay, before I go and run that, let's take a look at what we've written. So I've written env equals vec frame stack. And then to that, what we're passing through is our environment. So remember, we're just taking these environments and passing it through to each one of our pre-processing steps each time. So by passing our environment through to vec frame stack, we can specify how many frames we want to stack. So in this case, I'm choosing 4. You can choose more, you can choose less. I found 4 works. And then we're also specifying that where our channels order is. In this particular case, our channels order is last, so I've passed through last. So if I go and run this now, all things holding equal, you can see that now our state shape is now 4 at the end. And this is because we actually have 4 channels at the end to represent each one of our different frames. Now, I haven't exactly explained this all that well because it doesn't actually visualize it that well here. But what we've actually got is we've actually got 4 different images now stacked together. So if I go through and grab the first, wait, why are we not getting this back? So 0, 1, let's take a look at our shape. State. Oh, so it's the last channel. Okay, so that's fine. So right now it's visualizing that. So we haven't actually passed through any additional data to our state. So let's actually do that now. So if we go and run env.step, and we're going to pass through, so let's unpack this again. I'm just going to copy this down to here. Actually, let's just copy that whole line. So what we want to do, so right now when we run our state initially, we're only going to have one frame back. So when we actually go to stack our frames, there's only going to be one frame to stack. Hence why we're only seeing our gray image there. If we go and run this again, what's happened? So let's run env.reset. Now we're getting int object is not subscriptable. Let's put this inside of an array because we are now vectorizing our environment. Okay. So you can see that we're getting different colors. So if I go and run that again, different colors, run that again, different colors. And what we're actually getting back is a stacked frame. Now, let me actually show you what this actually looks like. So I'm just going to write some additional code to be able to show you this visualization or a little bit better. Okay, there we go. That's a little bit better. So you can see there that this represents each one of our different stacked frames. So if I actually go back, let's reset our state first. So I'm just running this cell up here. And if I go and run this, you can see that right now we only have one frame. And this is because we've only gone and run one. We've actually gone and seen one frame from our environment because we've only gone and run, or we've only just gone and started our environment. Let's just delete this so we can see this a little bit better. Now, if we go and take a step in our environment, so if I go and run this line and run this again, you can see that we now have two frames. If we go and run another line, or if we go and take another action, again, we're now up to our third frame, go and run it again, another action. Let's actually make this a bit bigger, so 20 by 16. That's a little bit better. So if we now, let's reset our environment again, right? So we've only got one frame. Go and take, let's actually, what's the right action? So env dot, what's simple movement? Right is number 0, 1. So if we go and just keep going right, let's see what that looks like. So if we go right, actually, the better action is jump, because then we'll actually be able to see that. So simple movement, what is jump? Right, A. So let's try 0, 1, 2, 3, 4, 5. So if we go and pass through 5, we should effectively see him jump. Run that. Mario's not jumping. Let's go and run it again. Okay, so there, I've just run it a ton of times, and you can actually see that Mario is jumping. So it looks like it's just moving really, really slow. So let's reset this, and then let's keep hitting it a bunch of times. All right, so that's Mario down the bottom. And then if we go and run it again, let me actually get rid of this just so we can see what we're doing. So, all right, so let's reset our environment. All right, so that's Mario standing down the bottom. So now if we keep running this, let's go back up. So you can start to see that Mario is moving up. So down here is, let me zoom in. So you can see that Mario is down the bottom here. And as we scroll up, he's moving up, he's moving up, he's moving up to the top. So this actually allows us to stack each one of these frames. Sorry, I had to run it a bunch of times for you to actually see it. But you can now actually see that our AI model is going to have some sort of memory. So it'll actually be able to see the velocity or the movement that is actually being enacted when we're actually going on ahead and playing Mario. All right, so now that we've actually got that running, we can go back to Jimmy and at least show him that we've got a pre-processed environment. So let's do it.
All right, man, it's all pre-processed. You end up checking out the code on Discord? Yeah, cool. But are you gonna build the AI models now? Definitely. Yeah, I was just showing you progress, right? It's about the journey, not just the destination. Yeah, nice try. Go build it. I want to see the destination.
Want to learn a quick way to 10x your startup? Just add AI to the domain name. I mean, we've talked big game about AI, but what exactly is it really, and how are we going to use it for gaming? Well, the type of AI we're going to be using is called reinforcement learning. It has 4 key elements. An easy way to remember these is to think of Area 51. Agent, reward, environment, and action. And 51. Mario, in this case, is our agent. He can take some action, for example, jumping, moving right, moving left, and so on. inside of the game environment. Then, depending on the results of his action, he might get a reward or might get a penalty. The AI controlling Mario learns what actions to take inside of the environment in order to maximize that reward. The specific reinforcement learning algorithm that we're going to be using for this is called PPO, which stands for Proximal Policy Optimization, which was originally created by a team of researchers at OpenAI in 2017. Okay, so we're now up to the good bit, actually building our AI model. So up until now, what we've gone and done is we've gone and built up our environment, we've gone and pre-processed it. Now comes the good bit. So the first thing that we need to do here is import some dependencies. And we've already talked a little bit about the dependencies that we're going to need. We are going to be using stable baselines, and specifically we're going to be using the algorithm called the Proximal Policy Optimization algorithm. So this is exactly what we're going to use here. Now, first up, let's go on ahead and import those dependencies, and then I'm going to give you some sample code that actually allows you to save models as you're training them, so you can actually go back through and see the different models that you've actually gone and built. So let's go on ahead and do this, and we'll be able to import our dependencies. Okay, those are our 3 dependencies that we actually need to build our AI model. So first up, I've gone and imported OS. So this just makes it a little bit easier when it comes to actually determining where we want to save our models. Now, I'm going to give you a callback, and I'll explain this in a second. I'm going to give you a callback, which actually allows you to save a model every, say, 10,000 games or 10,000 steps. So this means that you can actually have a backup, so you don't go through and train your model and then you lose all your progress. You've actually got the ability to go on ahead and reload that. Okay, so we've gone and imported OS, and then we've imported our main algorithm. So from stable underscore baselines, we've got an extra space here, from stable underscore baselines 3, import PPO. And so this is just importing the algorithm that we're going to be using to train our AI model or our reinforcement learning model. And then we are going to be, and then I've imported the base callback. So from stable underscore baselines 3.common.callbacks import base callback. This bit is kind of optional, and it's because we are going to be using my train and logging callback. I don't remember where I actually got this from, but I think it was inspired from someone else. But I'll include this code inside of the description below, or inside of the GitHub repo where I've got this code. But this is kind of optional because you don't need to go and save your model every 10,000 steps. It just makes it a little bit easier when and ensures that you've at least got some sort of backup as well. So that is our train, or those are our dependencies now imported, and this is the callback that is going to allow us to save our model every X number of steps. So to this callback, we're going to be passing through the check frequency. So this is how frequently we want to save our model. We're also going to be passing through a save path, and this is where we want to save our model to. Now, again, this is purely optional because you can save the model manually, but I find it good practice to effectively have this. That being said, the models can be big. So I did this a while ago. Each model is around about 282 megs. Let me just go back. So if you don't have a ton of disk space, just be careful how frequently you save it. So you can see 282 megs, that they get quite big. And I saved it every 10,000 steps. So you can imagine, I think I trained for 4 million steps. So it can take up quite a fair bit of space. But that is our base callback, and those are our dependencies now imported. Cool. Now what we want to do is we actually want to go on ahead and set up this callback. So first up, we need to set up some directories or where we're going to save our stuff. So let's go on ahead and do this first. Okay, so those are our 2 directories. So I've gone and set one up called checkpoint underscore dir, and one called log underscore dir. And I think I've already got these created, but that's fine. They create themselves. Where are we? Mario RL, Super Mario here. All right, so inside of here, I've got 2 additional folders, and we've got one called logs and one called train. So inside of train, all of our saved models are going to be saved, and inside of logs, every time we run the algorithm once, we're going to create this new log file. So you can see I've run PPO a ton of times when testing this. Inside of there, you're actually going to get a TensorFlow log file, and we're going to set this up in a second. But we can actually open up TensorBoard to actually be able to go and see the progress of our model and a whole bunch of different metrics. So I'll show you how to do that as well. Okay, so that is those two directories now set up. Now what we need to do is set up our callback. So let's go ahead and do that. Okay, so that is our callback now created. So this is just an instance of this big train and logging callback. So what we're effectively going to be able to do, and again, this is purely optional. I'll show you where to disable it if you don't want to use it, if you don't want to use this. What this is going to do is it's going to save our model every 10,000 steps. So this means that rather than ensuring that our model stays up and we don't have any errors, we can actually just have it automatically do its saving for us. So every 10,000 steps, we're going to get a new model saved. So let's walk through this entire line of code. So I've written callback equals train and logging callback. And then to that, we've passed through two keyword parameters. The first one is check frequency, and I've set that equal to 10,000. If you wanted to only save every 100,000 steps, you could just add in another 0 there. So you can actually tune this depending on how much disk space you've actually got. And then what I've also gone and passed through is the save path. So in this particular case, I've called it checkpoint dir, and this means that everything is going to be saved into that train folder. So that is our callback now done. Now, the next thing that we need to do, so it's pretty straightforward from here on out, we just need to go and set up our model and then kick off our training. So once that starts, we'll actually be able to let it run and we'll be able to come back and test it out. So first up, let's go on ahead and set up our model. Now, remember, the model that we're going to be using, or the AI, whenever you hear me say model, I'm talking about the machine learning, deep learning, or reinforcement learning model, or our AI model. So here it's going to be our PPO model. So let's go on ahead and create our PPO model. Okay, so that is our model created. Let me just run that. Okay, that looks fine. That is our model created. So I've gone and written a single line there. So this is the AI. So you can start to see a recurring theme in a large number of machine learning and deep learning projects. The hardest bit is actually getting the data into the right format. This is actually creating AI right now. So that one line has created a temporary AI model. We just need to go and train it. But the hardest bit is actually getting all the data in the right format, ensuring that it's ready for training. So we've gone and created that. So let me just write, this is the AI model started. And what I've gone and written is I've gone and created a new variable called model, and I've set that equal to PPO, which is this algorithm from up here. To that, I'm passing through the type of policy. So when we actually go and create a reinforcement learning model, behind the scenes, what we've got is something called a policy network. Now, if you've ever heard of deep learning, this is where the term actually comes in. So in deep learning, we've got something called a neural network, and think of this as basically a computer-based brain. So you've got a bunch of neurons, and these learn the relationship between different variables and target variables. So think of this as the brain of our AI. Now, by passing through CNN policy, we are using a specific type of neural network behind the scenes that is really fast when it comes to processing images. Because remember, our game is just a set of frames. It's the frames from our images. So this is why we're going to be using CNN policy. You can use another one. There is another one called MLP policy. This one stands for multi-layer perceptron policy. And it's great for tabular data, or like think Excel spreadsheets. I'm trying to think of other stuff. Excel spreadsheets, CSVs, JSON-based data. So that's where MLP is good. CNN stands for Convolutional Neural Network Policy. So we're going to be using that type of policy. And let me actually show you where this is. So if you go into stable baselines and CNN, so down here, so this is inside of the documentation. So you can actually see what types of policies you can use with different types of algorithms. Now, just as a little bit of background, and I know I'm probably diving into this too much, but inside of the older version of stable baselines, so stable baselines 2, you've actually got even more policies and even more algorithms. That being said, stable baselines 3 is a little bit more stable. So if we go into PPO 2 inside of stable baselines, what do they have there? So here you can see that they've got MLP policy, CNN policy, CNN LSTM policy. So this one LSTM actually stands for long short-term memory, and it's great for sequence-based data. So our frame stacking data, it's great for that as well. So you could definitely try using that. In this case, we've chosen CNN. Okay, so to PPO, we've passed through we've chosen the policy that we want to use. We also pass through our environment. This is going to be our data, remember, our pre-processed data from over here. And then to that, let me just double check we've gone and done that right. Oh, we've actually removed something from here. So this should actually say channels order equals last. Let's just double check that's working. Yep, cool. All right. So just remember that we need to have channels underscore order equals last in that side of our frame stack. I think I removed it when I was messing around. Okay, so what we've gone and done. So we've gone and specified our policy. We've gone and specified our environment, setting verbose equals 1. This means that you get a whole bunch of information when you start training. I've gone and set up the TensorBoard log. So this means that we can actually see a whole bunch of metrics on how our training is actually performing as we're actually going and running our model. Then I've gone and specified my learning rate. This is super important. So if you want your model to learn faster, then you can drop this down, but just keep in mind there's a trade-off here. So if you learn too fast, it might not actually converge to a good AI model. If you learn too slow, then you might be training for years. So I've set it to 0.000001. And then the next parameter that I've gone and set is n underscore steps. So I believe this is, so the number of steps to run for each environment per update. So basically it's how many frames we're going to wait per game before we go and update our neural network. So I found that a good parameter for this is about 512. Again, you can play around with this. I just found that that actually gives us a model that tends to perform relatively well, relatively quickly. Cool. So that is our algorithm now set up. Now, the next thing that we need to do is actually go on ahead and train our model. So let's go on ahead and run this. And then I'll show you how to actually view the log directories. Then we're going to go back to Jimmy, show him that we've actually kicked off our training and see where to from there. So let's actually go and kick off this training. And then we'll wait 10,000 steps because we'll be able to go and see our parameters straight away. So let's go on ahead and learn. All right, so we can go and run model.learn. And then we want to pass through total time steps. And we're going to set that to, I'm going to go 1,000,000 for now. You don't need to let it train for all that time. It's just going to, it's basically dependent on how long you want your model to train for. And then I'm going to specify callback equals callback. All right, so let's go and take a look at what we've written there. So so this is actually train the AI model. This is where the AI model starts to learn. Okay, so what we've written is model.learn, and then to that we've passed through total underscore time steps, and we've set that equals to 1,000,000. This is effectively how many frames our AI is going to get to see. So this means that for every single game, imagine every single move is a frame, it's going to get to see 1,000,000 frames. You can amplify this. Say, for example, you're doing multi-processing. This is where you could actually run it way faster, add in a whole ton more frames, but there's GPU limitations and whatnot. And then remember how I said, if you don't want to use this big callback over here, what we set up over here, you can just remove this. So if you don't want to use that, then you can get rid of this and you can get rid of this, right? So that's all you need to write to actually go and train your model. So it's actually not that much when you actually take a look at it. Given how sophisticated this stuff actually is, it's actually pretty cool. Okay, so if we didn't want to run callback, but we are, so that is the full line there. So we're going to actually leave that. We want to run a callback. Let's write it again. Callback equals callback. Okay, so this is where everything comes to fruition. So let's actually go and try to run this. Also, another key thing to note, if you are using a GPU, it should say using CUDA device up here. If not, it'll say using CPU device. So let's kick this off and see how this goes. So this looks like it's running. You can ignore this error. Okay, so this is a good sign. So the fact that we've got this little log appearing, or this little bit of information, this shows that our model is successfully kicking off training. You can see it's running. So what you're actually going to get is a whole bunch of information out of this. So you're going to get the number of frames per second, the number of iterations, the time elapsed, so how long it's been training for, the total number of time steps. So this is effectively how many frames your model has gone through. And then you get a whole bunch of training metrics. So you get, I can't remember what KL is again. You get clip fraction, clip range, entropy loss. So I normally pay attention to entropy loss, this loss metric down here, and then this value loss down here. You can also see your learning rates. Ideally, you want to see your loss going down as you're going through. You also want to see your explained variance going up as you're going through. So those are two good signs that your model is actually converging. But this is just going to keep training for 1,000,000 steps. Now, once you hit 10,000 steps, our callback should effectively save a model. So let's wait for 10,000 steps. So you can see it's going pretty fast. We're up to 5,000. Now up to 6,000. Where are we up to now? 7,000. I'll fast forward this and see when we get to 10,000.
A little longer than a few minutes later.
Okay, that's 10,240. So you can see that our loss is progressively going down. So we're now at 0.125. Our value loss is going down and our entropy loss is going down as well. Okay, so those are all good signs. And again, it might bounce up and down because the environment is consistently changing. But for now, we're going to let that run. And a good sign that you want to see is if you go into that training folder where we set up where we're going to save our models. So in this case, for me, it's inside of YouTube and then Super Mario and then train. You can see that we've got our first model now effectively saved down there. Right? So that's a good sign. So we've got best underscore model underscore 10,000. So we are looking good there. So the other thing that I also wanted to show you is how to view these logs. So if you wanted to go and take a look at what these TensorBoard logs look like, let me actually show you how to do that. So I'm going to create a new command prompt and I'm going to navigate to that log folder. And again, this is purely optional. If you want to view these logs, you can go in and take a look at them. So I'm going to go into my D drive and then what do we need to do? So we need to first up activate a Python environment. So I'm going to go into YouTube or wherever I'm working from. Where's my 17-1? And we are going to activate our environment. So I've got a virtual environment here. This is optional. If you don't have a virtual environment, you can just use basic Python. Nope. Right, so you can see I've got this virtual environment created. Then I'm going to go into my log directory. And then I'm going to go into the last PPO folder. So this is the latest one. 23, and then what we could do is run TensorBoard. So this is the main command. So TensorBoard --logdir equals dot. So this over here is going to be what allows you to actually view the logs. And this assumes, I can't remember if I've got TensorBoard on this environment, but we'll see. Okay, so that looks like it's running successfully. So we can actually copy this link here and go and open it up. So you can actually view your training progress. So this actually allows you to see how things are actually going. Pretty cool, right? I'll include some more information on each one of these metrics as well as what you should be looking for in the description below. But basically, this allows you to monitor how your training is going. So you can see our FPS, we can see our approx KL. There's not a ton of documentation on what you actually get back from here, or what each one of these actually mean. I'll see if I can find some stuff for you. But basically, this allows you to monitor how your model is actually performing. So you want to see explained variance going up. I normally look at this, and I normally look at the loss as well. So ideally, you want to see loss going down. Okay, so that is our AI model now training. Let's jump back over to Jimmy and have a chat to him.
Well, it's built. Ain't nothing to do but check it out now, right? Yeah, let's see it. All right, so I'm actually gonna show you the AI at different stages of the process, not just right at the end. This will allow you to actually see what it's actually learned, right, Jimmy? So you'll actually be able to see our AI model learning. Cool? Cool.
All right, we made it, guys. Time to bring it home. Now that we've trained our reinforcement learning model, we can use it on our Super Mario environment. This is pretty straightforward. In mission 1, we set up a model to take random actions in each game. All we have to do is sub out those random actions for the predictions from our PPO model using a command called model.predict. Let's go. All right, so our model has finished training. So we've got to the 1,000,000 steps. So what we can now do is we can actually go and take a look at we can actually go and load our models. So we've got our million or our, what is this? How many different models? So we've got 100 different models there. I'll see if I can share some of the best ones via GitHub. They're pretty big. I don't know if GitHub's got a file upload limit, but that's fine. So we've got a ton of models, so we can now dazzle Jimmy. Now we'll probably take a look at some of the best ones here, and then we'll skip through to a montage where you can see all of the results sort of compiled, or at least some of the better ones. Okay, but now how do we actually go and use this model to play Super Mario? Because so far we haven't actually been able to apply our AI to our model. So the first thing that we need to do is actually load our model from memory. So say, for example, we stop this training or we shut down this notebook. We want to be able to reload it from a file rather than relying on the model that we've got in memory. So we can do this. So in order to do that, we can use model.load or the actual ppo.load method. So let's do that. So I'm going to write model equals ppo.load, and then we pass through the name or the directory or specifically the file path to the model that we want to load. Now remember that our models that we've gone and trained are inside of a folder called train, and then all of them are here. They're called best_model and then the number. So let me zoom in on this so you can see that. So they're called best_model and then the actual number of the model or how many steps it was at. So let's try loading in one at 50,000, and then we'll maybe go to, I don't know, 500,000, and we'll probably go take a look at 1,000,000. But then I'm going to do the montage and show you a whole bunch of different models as well. Okay, so first up, we need to load our model. So we're going to go to ./train, and then let's just take a look at one of them. So if we go into YouTube and then Super Mario and train, let's start off with 100,000. So I'm going to copy the name of that, paste that there, load in the model. Cool, so that's loaded successfully, so no errors. So let's just add a comment. Load mod. Oh, also, if you want to just save the existing model, right, you can just type in model.save and then type in the name of the model. So this is a test model. Right, so that's like a manual save. So rather than using the callback, that's how you'd go about actually saving that model manually. And if you go into the base folder, you can see that we've actually got that model there. So you can see that that is now saved there. But if you do use the callback, then it effectively does that all for you. So you don't actually need to go and do this. All right, so we've actually gone and loaded up our 100,000 model. Let's just run that again, just make sure it is that. Now what we can actually go and do is try to play Mario with this. So this should be the final swan song. So we're testing out the 100K model. We'll try out 500 and then maybe 1,000,000. All right, so let's test this out. Okay, so that's all we need to actually go and test out our model. So some of this will actually look pretty familiar to you. So the first thing that we're doing is we're starting our game. So start the game. And then what we're going and doing is we're loop through the game. We're then going and making, so all right, so this is the bit where it gets new. So here, rather than, so remember previously to get our action, let me just add a comment there. Previously, to get our action, we were just, this is actually wrong. To get our action, we were just grabbing a random action using env.actionspace.sample. Now what we're actually doing is we're actually making a prediction. So we're passing through model.predict and we're actually grabbing out our state. Then out of that, we're going to get our action. What are we actually getting out of here? Let me just write env.reset. So this is going to be state. Let's take a look at a prediction. So state equals env.reset. And then we can get our model. So we can use model.predict and then pass through our state. And this is actually giving us our action back. So we actually get action 5. Now, if we extrapolate that, so let's go and grab that action. And then where do we need to go to grab it again? Right? Then we can go, all right, so what is this action actually saying? So if we go to simple movement. So this is basically saying that in this particular environment, the best keys to press are right, A and B. We go and reset it, run it again. So in this case, it's right. So if we keep running it, right, A. So you sort of get the idea, right? This is how our model is actually making predictions and actually determining what is the next best action. Cool. All right. So it's kind of weird that we're getting different actions based on the same state. But anyway, that's fine. So let's actually take a look at how this actually performs. So if I go and delete this now, what we can actually go ahead and do is, so we're going to get two values back. We can pass that to env.step to actually make a prediction. So if we go and run this, you can see we're getting that popping up. And remember, this is our 100K model. So let's actually take a look, make it a bit bigger. Right, so again, still getting stuck at the pipe. Doesn't look like it's making too much progress. Kind of average, right? Like it's not that great at the moment. Okay, we can shut that because it looks like it's just going to stop there. So what we can go do now is rather than loading up the 100,000 model, let's load up the 500,000 model. Right, so all I've gone and done there is I've gone and changed what model we're going to load up. Now, if we go to state again, see if this runs. Okay, take a look at that. It's clearing a bunch of stuff. So it's able to jump over one of the bigger pipes. And again, it's going to, oh, look at that, killed a mushroom. Looks like it's having a little bit of trouble jumping over that second hole. You can see it's definitely playing better. And remember, keep in mind our reward function was all to do with how fast and how far it can go right. Hence why it's going so hard to the right. It's having trouble with that second hole. You can definitely see it's playing better than what we had as our random environment. Pretty cool, right? So that is our AI model successfully running. All right, so the last thing that I want to show you is let's actually take a look at the million model, and then we're going to do a bit of a demo for Jimmy. Or a bit of a montage. So let's actually stop this, and let's try loading up our 1 million model. So that's 1, 2, 3, 1, 2, 3. All right, so that's that. So we can load up our million model, reset our environment, rerun this. So this is our million model running now. Still doesn't like that hole, does it? So like occasionally it's going to run well, and anybody that says these models work perfectly every single time is probably lying to you, unless you're part of the DeepMind team and you've trained this for God knows how many steps. Still doesn't like that second hole. So in this particular case, our 1 million step model might not even be performing as well as our 500,000 model. Kind of crazy how fast it runs as well, right? Like, this is insane. I mean, I can't play Mario this fast. Okay, that's cool. I could keep watching this for a ton of time. What I'm going to do now is let's kill this off. Let's quickly do a review, and then we're going to jump over to a montage and see a whole bunch of the different progressions. So I've only shown you 3 different models, but let's actually take a look because some might actually perform better than others. So let's stop this now. So what we've gone and done is a ton of stuff. So first up, we went and set up Mario. We then went and pre-processed our environment. And remember, we did a couple of different pre-processing steps. We went and simplified the controls, grayscaled, and then we also went and frame stacked to be able to give us some sense of motion. We then went and created a specific AI model, and we're using a method called reinforcement learning, and the algorithm that we're using is PPO. We then went and learned for 1 million different steps, and we were then able to successfully load up our model using ppl.load. And then this little script down here is actually allowing us to go out and test out our model. So remember, this is pretty similar to what we had originally right up here, except the only change is that rather than using env.actionspace.sample, we are now using the model.predict function, which is over here, model.predict, to actually predict what is the next best action that we should actually take. But on that note, let's jump over to the montage and see how this model actually performed across time. So first up is the model trained for 10,000 steps. This one was pretty sucky at this stage. 100,000 steps started to get a little bit better. It took a little while, but it eventually got over the second pipe. And 500,000 steps. This is where the game started to change. You can see that Mario is going for a hell of a lot longer. So I ended up training the model for a bunch longer. The models through 1 million to around about 3 million steps were pretty average, to say the least. And then it happened. We got our dream run, guys. At 4 million steps, Mario went and smashed out a level. Every now and then he gets stuck, but he does make it out through. And wait until the end to see how he finally performs, and take a look at that final score up in the top left corner.
So, what'd you think? Not bad, man. How do you think you might go about improving performance? Well, there's a couple of ways. What you could try doing is training it for longer with a slower learning rate. This would mean that it takes longer to teach our AI model how to actually perform in the game, but ideally it should end up at a better outcome. Not always the case, but can definitely help. We could also try multi-processing. So this means that our AI model plays multiple games at the same time, which should effectively mean that it learns faster. The last thing that we could also try is a different algorithm. There's a whole bunch of things that we could definitely do. Sweet, not bad for a first crack. So what game's next? Who knows? Let me know what games you'd like to see in the comments below. And that's a wrap. Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell. And again, thank you so much, guys. We just hit 50,000. I appreciate every single one of you. Thank you so much for getting us here. If there's anything that you need, by all means, do hit me up in the comments below. Thanks again for tuning in, guys. Peace. What's happening, guys? My name is Nicholas Renat, and in this video we're going to be teaching a reinforcement learning agent, or AI, to be able to play Doom. Let's take a deep look at what we'll be going through. Alrighty, so what is it exactly that we're going to be going through in this video? Well, there's actually a ton of stuff, and we're actually going to be treating it like a client and developer relationship as per usual, so you get a feel for how to explain some of these concepts to people that aren't necessarily data scientists or developers or machine learning engineers, so on and so forth. All right, so the first thing that we're going to be doing is setting up Vizdoom. So this is a visual environment that allows you to play Doom using Python and other programming languages. What we're then going to do is we're going to wrap it inside of the OpenAI Gym framework. So this is going to allow us to actually build machine learning models to play around with the game. Then we'll get to the good bit, so we'll actually train a reinforcement learning agent using the PPO algorithm. Now stick around because I've actually got a detailed explanation for how PPO works. We've sort of glossed over it before, but we're gonna dive into the details in this video. We're then going to change the levels that Vizdoom is currently playing on. So before we might train on a simple level, we can then change it and play something a little bit more complex. And then I'm gonna show you one of the most important techniques that I've found when it comes to reinforcement learning. That is reward shaping, so how to shape your rewards to be able to produce good results, and curriculum learning, which I'll talk about a little bit later. On that note, ready to do it? Let's get to it. Hey Nick, do you play Doom? Nah man, not in ages, Bob. Dude, check out Vizdoom. You can use it and actually integrate it with Python. Alright, we'll do.
Alrighty, so Bob's asked us to check out Vizdoom. So that's exactly what we're going to do. To get Vizdoom up and running, we need to install it into our Python environment. This is pretty straightforward using the command pip install Vizdoom. Let's get started. Alrighty guys, so Bob's gone and asked us to go on ahead and get Vizdoom up and running. So that's exactly what we're going to do up here. Now the cool thing about Vizdoom is that it is a full-featured, well, you can see it there, full-featured AI research platform for reinforcement learning. But the cool thing about it is that it is super extensible and there's a ton of stuff that you can actually do with it. In this particular case, we're going to be using it for exactly that, doing some RL. Now, in order to go on ahead and install it, you just need to go over to the GitHub repository. Now, it is mywdmuch/Vizdoom. So this is Mark Widmuch. So again, first time I've actually pronounced that. So Marek, if I'm pronouncing that incorrectly, let me know. But I do thank you very much for this Vizdoom repository because it's absolutely awesome. Now, the thing that we need to do is actually go on ahead and install Vizdoom. So we're going to go on ahead and leverage Marek's environment or package. And to do that, I'm on a Windows machine, so we can just run pip install Vizdoom. If you're on a Mac machine or a Mac OS machine, you got to run this brew install command beforehand. If you're on Ubuntu, then you're going to need to run this. I'm going to include a link to this GitHub repo in the description below if you want to pick this up, as well as the Vizdoom documentation. Cool. So what we need to do now is run pip install Vizdoom to get that installed into our Python environment. So we can just run or create a new cell and run pip install Vizdoom. And that's going to go on ahead and install Vizdoom. So I've already got it installed. So it went relatively quickly, but let me quickly walk you through that command. So it's !pip install Vizdoom. And that's going to install it into your environment so you can actually start working with it. Now that that is done, we've just collapsed that. Now that that's done, the next thing that we need to do is actually go on ahead and clone this GitHub repository. So we've got a ton of stuff that we need in here, but specifically inside of this scenarios folder, we've got all of these configurations. Now, these configurations are what allow us to fine tune what we want our Doom level or map to actually be. Now, you can actually go ahead and create custom versions of these. We're just going to be using the ones that are inside of the repo, at least for now. So we're going to be using this basic environment, but you can see that it's got a scenario path, what map we want to use, what we want our reward to look like. We're going to touch on that a lot more later, as well as a whole bunch of rendering options, when our episode starts, when our episode times out, the buttons that we've got available, really, really important when it comes to action, so we can move left, move right, and attack, as well as any game variables that we've got available, what mode, and then Doom skill. So this is really important for curriculum learning, which we'll talk about later. Okay, but for now, what we need to do is go on ahead and clone this repo. So first things first, let's create a subfolder to house this. So inside of the folder that I'm currently working in, I'm just going to create a new folder and I'm going to call that, let me zoom in because this is super small. So I'm going to create a new folder. Where's new? New. Nope. New. Oh my God. This is a nightmare. All right. New. And then GitHub. So I'm just going to call this GitHub. And the reason that I'm creating this is so that we've got a separate isolated folder to hold all of our GitHub stuff. So we're going to be having a lot of stuff inside of this repository. So keeping it nice and clean is going to make our lives a little bit easier. So what we now want to do is clone this repository into that folder. Sorry, I'm losing my voice. So I'm going to create or run a separate command, and that is going to be cd GitHub. So keep in mind that this Jupyter notebook that I'm working in right now is in that root level folder. So first up, we need to go into that GitHub folder, and then we're going to run git clone, and then we are going to be cloning this repository. So the full line is !cd github and git clone. And then we've passed through the full link to this GitHub repository. So if I go on ahead and run this, it's going to start cloning that down. So if we go into the GitHub folder, you can see that it's now starting to clone into there. So we'll give that a second, let it go on ahead and finish cloning, and then we'll be able to kick things off.
5 minutes later.
Okay, so that is the Vizdoom GitHub repository now cloned. So if we go into there, you can see that we've got all of our stuff, including these scenarios, which we're going to need in a sec. So everything that you saw inside of the GitHub repo, we've got those available here. Now that that's done, what we actually want to go on ahead and do is import a couple of dependencies, because we're going to need some stuff to actually be able to work with our environment. So namely, we are going to need to import Vizdoom itself. We're going to need the random the random module to be able to take random actions. And I think we're also going to need time. And this just gives us the option to sleep between frames, give us a little bit of time to visualize what's actually happening with Vizdoom. So let's go on ahead and do this. Okay, those are our dependencies now imported. So I've gone and written three lines of code there. So from Vizdoom import stars. So this is going to import all of our Vizdoom dependencies. I've then gone and imported random. So import random. So that's going to allow us to take random actions. Now a little bit on the actions, right? So let's actually just jump back into that basic config. So if I go into YouTube, and then Vizdoom, and then GitHub, and then Vizdoom, and then scenarios. And then if I open up this basic folder, no, that's not going to, there we go. I'm trying to make the font a little bit bigger. All right, so inside of this config, we've got this section here called available buttons. These are going to be the buttons that our reinforcement learning agent has access to from Vizdoom. So if, for example, we wanted to use the move left action, that's represented as an array or a binary array. So it's going to be 1, 0, 0. That is the action that we'd actually pass through to our environment to move left. If we wanted to move right, then we'd be passing through 0, 1, 0. If we wanted to attack, then again, it's going to be something similar, but this time we're going to be passing through a binary 1 inside of the last column. So these three commands or arrays map through to these three actions. So we're going to be randomly taking these actions, at least initially, but later on we're going to be able to train our reinforcement learning agent to know which one to take in order to maximize our return. But for now, we don't need to know any more than that. We're going to be playing around with it in a sec. Okay, so we've gone and imported random, and then we've gone and imported time. One thing that you'll notice is that this environment runs hyper quick. That is a key advantage of Vizdoom. It trains really, really fast, and you get a really high frame per second rate. So we ideally want to be able to show this to some potential users or people that actually want to see our game environment. So by importing time, we're going to sleep and at least give ourselves a little bit of time between frames to see what our agent is actually doing. Okay, now that that is imported, the next thing that we can actually do is at least initialize our game and load our config. So let's actually go on ahead and do this. Okay, so that is our game now set up. So I've gone and written 3 lines of code there. So the first one is creating a game instance. So I've written game equals Doom game. So this is coming from the Vizdoom class. So it's capital D O O M, capital G A M E. So Doom game, and then inside, and then we've added a set of parentheses to initialize the class. And then I've gone and written game.load_config. This is what actually allows us to load up these configs that I've been harping on about. So you can see that we've got basic.config, all of those there. That is actually what allows us to load up that specific configuration, which defines our map, our reward, our buttons, so on and so forth. So this line is actually loading that into the game. And then by running game.init, we're actually starting it up. And what you might have noticed is that we've actually got Vizdoom happening at the back over here. So this is actually our game environment. Now it is a bit small. That's just the frame size. You can configure this inside of the config. That's our game now started. Now, you're probably thinking, Nick, that's great, but I actually want to do something in it. So that's exactly what we're going to do now. So we're going to start taking some random actions. Now, first up, what we want to do is create a set of actions, because right now all we've got is we haven't actually gone and created some actions that our agent can take. So to do that, I'm going to import NumPy. Import NumPy for identity matrix. And I'm going to, what are we doing? Cut that, paste that over there. So NumPy is going to give us a quick way to build up that array matrix that I was showing you. So what I can do is type in actions equals mp.identity and pass through 3. And if we type in actions now, that is effectively our set of arrays. Now, do we need to make these? And let's make them integers. dtype equals mp.uint8. Right. So that is effectively our set of different actions. Now, remember when we were taking a look at our basic configuration, we had 3 different actions. So move left, move right, and attack. These are what our different actions represent. So action 0 or index 0 is going to be move left, index 1, move right, and the last one is going to be attack. So we can now randomly choose from this set of actions using our random package that we brought in up here. So I think it's random.choice. So you can see we're now taking random actions from our identity matrix. So for now, what we're going to be doing is using random.choice to just take random actions because we don't exactly have a smart agent. So let's just add some comments here. So this is the set of actions we can take in the environment. And so this random.choice is effectively going to be what we actually use to take random actions inside of that Doom game effectively. Now, it's obviously going to perform like crap because there's no actual set of smarts which is actually gone and been applied here. So at least it shows us what our game actually looks like. So let's go on ahead and set up a bit of a loop to actually start playing our game, and then we're going to be able to take our random actions and apply them to our game. So let's do this. Okay, before I go any further, let's actually take a look at what we've written here. So first up, what we're defining is a new variable called episodes, and I've set that equal to 10. So this basically means that we're going to play 10 games, or at least initially while we're trialing this out. What we're then doing is we're looping through each episode. So for episode in range episodes, so this is effectively going to loop 10 times. And we are now creating a new episode. So game.new episode. So this is like restarting the game or starting Doom all over again and initially starting from scratch. So game.new episode is going to be what allows us to do that. Then we're checking that our game is not done. So effectively we're not dead or we haven't actually gone and completed the level. So while not game.isEpisode finished. So if I actually go and type that in, so well, we haven't actually created a new episode. Let's create a new episode. Game.new episode. Right? So that is a new episode or a new game. So that resets our environment. Now we can check game.isEpisode finished. And you can see that right now our game isn't finished. So we can still keep on going and still keep applying steps. Now let's actually, rather than looping through, let's actually just go and take some random actions to begin with. So we can actually type in game.makeAction and then run random.choice. Let me move this over so we can see this happening side by side. Random.choice.actions, and this should effectively allow us to take random actions. So over here, we're getting our reward back. Let's go and run it again. So you can see that our agent is moving. So it's a little bit slow at the moment. You can see it's taken a shot. Right, cool. So you can see that that is moving, albeit a little bit slow at the moment, You can see that stuff is actually happening. Right, so this means that by using game.make_action and then passing through our random actions, we are effectively doing stuff inside of our game environment. Now, doing it this way is a little bit slow, so we can actually loop through. So let's quickly just recap on that one line there, because that is quite important. So game.make_action allows us to take an action and actually apply it inside of our game. So this is akin to just pressing buttons, right? Now, what we're going to do is we're effectively going to loop through and do this a little bit faster so you can actually see what a set of random actions looks like inside of the game. Now, the goal here is to kill this monster over here. I think there is a set, inside of this README, it actually tells you what the rewards are like. Let me go back. So if we take a look inside of our documentation, so you can see that this is the information about the basic environment. So the purpose of this scenario is just to check if using the framework to train some AI in a 3D environment is feasible. The map is a rectangle with gray walls, blah, blah, blah. All right, so we're really, let's actually read it. So the player is spawned along the longer wall. In the center, a red circular monster is spawned randomly somewhere along the opposite wall. So that's that dude over there. The player can only go left, right, and shoot. One hit is enough to kill the monster. The episode finishes when the monster is killed or on timeout. Now, the rewards that we're going to get, so we're going to get 101 points for killing that dude over there. We're going to lose 5 points for missing. So this is if we shoot and we don't actually hit the monster, we're going to lose 5 points. So because we're effectively wasting ammo. Then we've also got some additional rewards. So we lose 1 point for every step that we aren't killing our monster. Got 3 buttons and we've got 300 frames to go on ahead and kill that dude. So let's go on ahead and loop through this and run a whole game. So let's do it. Okay, so I've gone and written a bunch of extra lines of code here, but for now, let's actually go and test this out and see what happens. So if we go and run this, we've got an error, name episode is not defined for episode in range. Oh, this should be episodes over here. All right, so you can see that that is running super quickly. You can see our agent is actually doing stuff now. So he's taking random actions, and you can see that we're losing 1 life for every step that we don't kill it. All right, it's gonna kill it. Boom. All right, so we should have got a bigger reward for that. So you can see that we got 100 there. So that's because we actually went and killed the monster. Now you're probably thinking, why isn't it 101? Because remember, we lose 1 point for every step that we are currently living. And this incentivizes our agent to do it quick and effectively kill the monster quick. But you can see that this is effectively the agent playing, right? So he's going around taking random shots and we can actually see our reward down here. All right, so we can keep leaving that playing, but it's just going to go 10 times. So we don't actually need to keep watching that. Now, I think we can run game.close. And that's going to close that down as well. Cool. All right, let's take a look at what we wrote here. So first up, we are looping through our episodes. Loop through episodes. And those are these 2 lines over here. Then we're creating a new episode. New episode or game. We're checking that our game isn't finished. And so what we've written there is while not game.is_episode_finished, and then a set of parentheses and a colon. Then what we're doing is we're getting some information about our game. So first up, we're getting our game state. Now this should ideally be the actual frame from our game. Now I don't think our game is initialized. So if I run game.getState, we don't get anything back because we don't actually have a game currently initialized. So let's just clean this up a little bit. So if I delete that, let's actually go and create a new game. Now if I run game.getState, there you go. So that is our state. So if I type state equals game.getState and then state dot, there is a whole bunch of information that we're actually able to get from this state. Now, the most important one is the screen buffer. So this is actually the game frame, or effectively that image. So you can see that Vizdoom is back up and running. By running state.screen_buffer, we're actually able to get the image that you can see there. which is what we're doing over here. So state equals game.get underscore state. So state equals game.get underscore state. And then what we're able to do is actually get the image. So image equals state.screen underscore buffer is getting that specific image there. Then we can get some game variables from that state as well. So if I run state.game underscore variables, so you can see we're getting 50. Now that 50 maps to what we're actually setting in our configuration. So that is the ammo. So the info is actually the set of available game variables. So available underscore game underscore variables equals ammo, right? So that 50 that you can see there is the 50 that you can see. Let me zoom in so you can see it. Is that 50 over there. Now this gives us a lot of options, right? Because we can actually get a bunch of different game variables and use that to incentivize our agent, but we'll talk about that a little bit later. So we've got our game variables. So we've written info equals state.game underscore variables. And then we're actually going and taking our action, which is what we were doing before, right? So game.make underscore action, and then we're passing through random.choice, and then passing through actions. I'm going to show you one extra thing there in a second, but for now, let's keep taking a look at what we've written. So let's add some comments. So we are getting our state. Then we are getting the game image. Get the game variables. In this case, it's ammo. Then we're taking an action. And okay, so we're up to there for now. So reward is what we're going to get back whenever we make an action. So game.make underscore action, and then we're just taking random actions for now. And then we're actually able to print out our reward. Print reward. And remember, our reward is going to be defined over here. So you get 101 points for killing the monster, 5 for missing. So if you take a shot and don't kill, you -5, and that incentivizes us to conserve ammo, right? Then we can print out our reward, which is what I've written here. So print, and then I've passed through the string reward, comma reward. So it's going to print out a string reward and then the actual reward itself. We're then taking a brief break. So I've written time.sleep, and then we're taking a 0.02 millisecond break. And then we're printing out the full game reward. So this is the reward from taking one step. This is our overall points for the entire game. So to get that, we can type in game.get underscore total underscore reward. And that is going to give us the full game points. And then we can take a longer sleep between games. So this gives us a chance to actually take a bit of a break. Now, a really important thing is when you're actually going and building these environments or building these agents is a concept called frame skip. Now, keep in mind when you actually take an action, it might take a little bit of time for you to see the result of that action. So if we go and try to shoot at the agent, it's not immediately going, the bullet's not immediately going to reach the monster, right? So we can actually set a parameter called frame skip to actually give us a little bit of a buffer between when we take that action and the end results. Now, in order to do that, inside of game.makeAction, we can pass through this second parameter. So let me actually show you this. So game.makeAction. So it doesn't actually tell you, or well, I'm going to tell you. So the second parameter inside of make action is actually that frame skip. So this means that when we're going to take an action, we're going to skip the next 4 frames and then return that result. So this is actually going to give our agent or our bot some time to actually see the result of taking that action. So if we go and run this loop now, let's actually close that game that's up there. Let's reinitialize and then run this loop. So you can see it's a little bit more jittery, and that's because we're skipping frames. Make this a bit bigger so you can see it. And so by passing through that frame skip parameter, we're effectively going to see the result or result at least a little bit quicker than what we would have if we were to not frame skip. Because we'd take a shot and we wouldn't necessarily see whether or not that's gone and killed our monster. So this gives us a little bit of time to see that reward and associate that reward with that action. Cool. All right, so that's going on. Okay, so we've effectively gone and got Vizdoom up and running now. So it took a little bit of time and there's a bunch of stuff that you need to get your head around, but that is effectively Vizdoom up and running. So let's quickly recap. So we went and installed Vizdoom. We went and cloned down the GitHub repo. And remember, you've got those scenarios in there, which are really, really important. We've then gone and imported our dependencies. We've set up our game. We took a look at how we can specify our actions and what's actually available inside of our game configuration. And then we went and wrote this loop, which effectively allows us to play with a random agent inside of our Vizdoom environment. Let's go on ahead now and show Bob what we've done.
So what'd you think of Vizdoom, man? Yeah, it's alright, but the game itself isn't quite wrapped and ready for machine learning. What do you mean? Well, normally to be able to do cool stuff with games, we need to set up our environment to be able to apply reinforcement learning. Now, the most popular library for this is OpenAI Gym. Vizdoom by default isn't actually wrapped and ready for that. Think you can do it? Is that a challenge? Maybe. All right, let's do it.
So we've got it working, but as per usual, we've got more client requirements. In order to AI this, we're going to need to get it into an OpenAI Gym environment. We can wrap it inside the environment using the OpenAI Gym base class. This will give us a bunch more flexibility when it comes to pre-processing and working with the game frames and rewards. While we're at it, we'll also grayscale the game observations and cut out the game info bar at the bottom. This helps train the model faster as there are less pixels to process. So Bob's now interested in actually getting this set up to actually do a little bit of reinforcement learning. So this is where we're actually going to need to start using OpenAI Gym. Now there are different frameworks, but to be honest, OpenAI Gym is the best one that I've found. We're going to be using this and effectively wrapping up Vizdoom inside of that environment. Now I think there is actually a library out there that allows you to use Vizdoom with OpenAI Gym without doing much config, but I think it's really good practice to actually get your head around how to actually do this, because you're going to understand a little bit better how the OpenAI Gym framework actually works. Okay, so now we are up to step 2. So that is step 1 now done. We're doing step 2. Okay, so the first thing that we need to do is actually go on ahead and install OpenAI Gym. So if we take a look at our documentation, to get it up and running, we just need to run pip install gym. That's exactly what we're going to go on ahead and do. So inside of a new cell, I'm just going to write pip install gym. And you can see I've already got it installed, so it went relatively quickly, but the full line is pip install gym. So this is going to be what allows us to actually wrap our framework or wrap our Vizdoom environment inside of the OpenAI Gym framework. Cool. Now that that's done, the next thing that we need to do is actually go on ahead and import some dependencies. So the main dependencies that we're going to need is OpenAI Gym. We're also going to need to import a couple of things called spaces. So these are just the way that we define the shapes from our environment. Now, the two main ones that we actually work with are box and discrete. So box is effectively an array of any shape, and discrete is just a set of discrete binary actions. Okay, so let's go on ahead and import some dependencies. Okay, so we've gone and written 3 lines of code there. So from gym, import env. So this is going to give us our OpenAI Gym base class. We've then gone and imported our 2 different spaces. So from gym.spaces, import discrete and box. Now let me quickly give you an example of what these are. So if I type in discrete, 3. So that is our space. I can then type in sample. And so what this is going to give us is either 1 or 0, 1 or 2. Now, these represent the different actions that we've actually got available. Now, what this is going to then be used for is if we go and type in action, and then if I go and pass through this, it's actions. So this is effectively randomly sampling from our action space, which is what we had over here. So our discrete space is going to be what we define our action as, and then we're actually able to sample from these different actions. So we're actually going to be using this to select a specific action. So you'll actually see this in more detail, but just know for now that discrete is effectively an identifier or an index when we actually go and define that as a space. Box is a little bit different. It can be an array of any shape. So typically when you define box, you define a low value. So we'll say, let's say 0, a high value, let's say 10, and then a shape, let's say 10 by 10. Need to close that. And then we can type in sample. So So you can see we're now getting an array, and that array is going to be of the shape 10 by 10, and our low value is going to be 0, and our high value is going to be 10. We can also specify d type, I think. So np.uint uint8. Right, so now we're getting an array which is 10 by 10, which has a numpy or a d type of a numpy unsigned integer of 8 bits. So you can see that we've got all of these values. Now, when we actually go and define this for for our Doom space, I think it's, what is it? I think it's 320 by 240 or something along those lines. So this just gives us a much bigger image, and rather than our low value being 0, our low value stays as 0, high value is then 255. So this is then an actual image. Cool, but you'll see this in more detail in a sec, so let's get rid of that. Okay, so those are our dependencies imported, that's spaces. Then we've also imported OpenCV, so I've imported CV2. So this just gives us our, or this is going to be used for grayscaling our observations. That actually makes it faster to actually go and process our Doom environment. Okay, so I think those are our 3 key dependencies now imported. So we've imported the environment-based class, discrete and box, and we've also imported OpenCV. Okay, so now that that's done, the next thing that we want to do is start defining our Vizdoom environment class. So let's go on ahead and do this. So I'm going to set up a base class, and then we can start filling it out. So let's do it. Okay, so that is our baseline framework now set up. So again, I've just gone and defined the functions and the class. We haven't actually gone and filled this out yet. So we're going to do this step by step. So what I've written is class, and then I've defined that as Vizdoom Gym with uppercases or camel case. So Viz in caps, Doom in caps, and then Gym in caps. And then to that, we're going to be passing through our OpenAI Gym base class. So the full line is class, Vizdoom Gym, and then inside of parentheses env, and then colon. Then what we've gone and defined, so that is our base class defined over here, right? So that is the main line. Then what I've gone and defined is, what is that? 1, 2, 3, 4, 5, 6 different functions that we're then going to fill out. So the first one is init. So this is what happens when our environment is initially started up. So the function, let's actually add some comments. Function that is called when we start the env, right? So inside of our init function, we are going to do all of the stuff that we need to effectively start our game. So it's really going to be game.new episode. It's going to be setting up our different spaces, so on and so forth. Then we've defined a step function. So def step, and then we've passed through self and then action. Again, don't focus on this for now. I'm just going to give you an understanding of what each one of these functions or each one of these methods are used for. So this is how we take a step in the environment. We've then got close. This is a little less important. So I'm just going to put this down here for now because we can come back to that later. So then what is the next most important? So let's put that down there as well. So I'm just going to reorder some of these. Okay, so then we've got our render function. So I've just defined this for to ensure that we meet all the requirements for a Vizdoom or an OpenAI Gym environment. We don't actually need to define the render function because that's already predefined inside of Vizdoom. So this is going to stay as a pass for now, but this is where you'd normally define how to render the game or environment. We don't really need to do this for now because Vizdoom actually does it for us. Reset is what happens when we start a new game. So the init function is what happens when we create the environment. Reset is what we call to start a new game. Grayscale is a custom one, so we don't need, this isn't typically included inside our OpenAI Gym environments, but we're going to create it. So we are going to use this to grayscale the game frame and resize it as well. and then close. So this is what we're going to call to close down the game. So you saw how we have the frame that sort of pops up. So we're going to define a method that allows us to actually close that game down so that it's not floating there the entire time. Okay, so the first thing that we need to do is actually go and define our init function. Now, the nice thing about this is that we've pretty much got a lot of that code already floating around over here. So specifically, we need these 3 lines of code. So I'm just going to copy these over. So the setup that we had over here, and we're going to bring this into our init function and clean it up a little bit. So let's actually go on ahead and do that. Okay, so we've gone and brought in those 3 lines into our init function, and I've got rid of the pass line. So I've written self.game equals Doom game. So this is going to create our new game instance. Then I've written self.game.load_config, and this is going to be passing through our basic config. So later on, when we want to use different environments, we could change that line there. Then I've written self.game.init, and this is going to create or initialize our initial game environment. So now that that's done, the next thing that we actually want to do is create our action or our observation space and our action space. So we are going to create 2 new variables or 2 new properties to self.observation space. And we're going to set that equal to box. And the low value is going to be 0. High value is going to be 255. And then we need to define the shape. So let's go and take a look. Do we have a game running? Yep. Okay. So game.getState. Got screen buffer. Okay. So it's not currently running. That's fine. So let's go and create a new game. And then we're going to create a new episode. Wait, do we have the game frame up and running now? Okay. So what I'm trying to do at the moment, let me actually explain the theory behind what I'm doing, is I'm trying to get how big the actual game frame currently is. So we actually want to be able to pass through the shape down here. So let's go and get that. So game. Let's actually do it here. So we've got a game running. So I can type in game.getState. All right. And then to get our image, we can type in screen buffer. And then just dot shape. Okay, so right now our shape is 3,240 by 320. So we can pass that through. So is that right? Yeah, let's try that. It should be 240 by 320 by 3. And then we're going to pass through dtype equals mp.uint8. Okay, so that is our observation space now defined. Now, the nice thing about this is that there's actually a environment checker that you can actually use from stable baselines, which is something we'll talk about in a second, that we can actually use to validate whether or not we've defined our environment correctly. So don't fret if you're not too sure how this is actually working. We can actually check it out later on. Or we can actually check that our environment is going to be correct. All right, now that that's done, the next thing that we need to do is actually define our action space. So self.action space equals discrete, and it's just going to be 3. Pretty straightforward. Okay, cool. So this is set up the game, create the action space and observation space. All right, I think that's okay for now. Let's actually test this out. So if we go and create a Vizdoom environment, there's still going to be a bunch of stuff that we need to initialize. But if we now go and type in env.observation space, we've actually got the shape of our environment. So we've got 0, 255, 240 by 320. We can take a look at our action space, and this is discrete. Let's just double check our observation space shape. So .sample. Sometimes the order is a little bit weird. All right, so 240 by 320 by 3. Is that matching what we had up here? 240 by 320 by 3. Okay, so we're good. Does it need to be... I wonder if we need to have the channels first. We can actually rechange it, so we'll just put the channels first. So you can see there that the shape that we've got is 3 by 240 by 320. We had 240 by 320 by 3. So I'm just going to rearrange that. So now you can see our observation shape is the exact same as what we've got from over here. Cool. So we've now got self.observation space equals box. And then we've specified our low value, which is the pixel minimum. We've got our high value, which is our pixel maximum. We've then got our shape, which is equal to 3, 240, 320. And then we've also gone and specified our data type, which is going to be a NumPy unsigned 8-bit integer. Then we've gone and defined our action space, a self.actions underscore space equals discrete 3. Cool. All right, now let's take a look. So you can see that each time we're creating one of these Vizdoom environments, we're going and spinning this up. But we want to have some sort of way to close it, because now that we've gone and encapsulated it inside of our Vizdoom gym, I don't know whether or not we can just run game.close. I might close one of them. So it's closed one of them, but if we go and run it again, not happening, right? So we want to have, let's go on ahead and define our close function so we can actually close down our game. Okay, so that is our close function now done. So I've gone and passed through the self, so they're our own instance, and then run self.game.close. So that should effectively allow us to go on ahead and close our instance. Now let's go and hard shut these ones that we've already got up here. So if we go into our task manager, and you can see that I've got all these Vizdoom instances or Zdoom instances up and running there. So you can see those. We can just end those tasks. So end, where's the next one? End. Cool. All right, so those are now closed. So you can see that they're done there. So let's go and create our next Vizdoom instance. So that's up and running. You can see we've got it over there. Now if we go and run let's actually run env.close now. You can see it's shutting it down gracefully. Okay, so that is that part of the environment now done. So we've gone and done the init function, which we've gone and set up how we create a game and how we create and define our observation and action space. There's actually one more thing that I want to do inside of this init function, and that is define whether or not we want to render our game. Now, the reason that we define this is when we actually go and train our environment, rendering is going to take a lot more compute away from our training. So if we disable rendering while we're actually training, it's going to train a whole heap faster. So let's go and pass through an argument to our init function. So we're going to specify render. And by default, we're going to set this equal to false. And then we just need to have some conditions inside of this init function to define whether or not we want to spin it up or whether or not we don't want to actually render. So let's go ahead and define this. Okay, that is our render frame logic now applied. Now, the only other thing that we need to do is we just need to move the self.game.init method or function call from up here to below this. Cool. All right, so let's take a look at what we wrote there. So I've written if render equals false, and this is a new argument or a new keyword argument that we're going to be passing through to our init method. So if render equals false, self.game.set_window_visible equal to false. So this is basically going to say, hey, don't pop up that window. We don't want to see that. So just start up the game in the background so we can actually go on ahead and train. Else self.game.window or self.game.set_window_visible equal to true. So one is going to enable us to see the window. One is going to, or this is going to disable us seeing the window. This is going to allow us to see the window. And then we're moving this down because we only want to start it up once we've actually gone and set that parameter. So start the game. Cool. I think that is that now done. Let's just make sure we don't have any instances running. So we're good there. Hold on. This should be, God, rookie error. It should be equals false, not equals. God, Nick, terrible. All right, so now if we go and start up our instance, get rid of that. Oh, wait, why did I close it? Start up our instance. So you can see it's not rendering, right? So we don't actually have Vizdoom running down here anymore. But if I go to our task manager, it will actually, in fact, be running in the background. So it should be Zdoom. So you can see that we've actually got an instance over there. right? So it is running, it's just not rendering. So if we go and close it, and if we go and pass through render equals to true now, you can see we've got this little bad boy running. Right? So all well and good. So we've now got the ability to enable render and disable render. Okay, we're going to set that equal to, let's leave that as true for now. All right, so we're going to close it. All right, so what have we gone and done? So we've now gone and fully completed our init method. We've also gone and set up our close. So now what we need to do is finish off our step function, our reset function, and our grayscale. So let's go on ahead and do our step function. Okay, so the first thing that we want to do is we want to define our actions that we're actually going to be able to take. So we're going to create actions equals mp.identity. And we're going to set that equal to 3, which is effectively what we had right up here. So we can actually just copy this line. Paste that there. And then we want to define what we're actually going to do. So we can type in reward, or we actually want to take a step, equals env.makeAction. Actually, it should be self.game.make action. And then we are going to be passing through actions, the specified action that we want to take. So when we actually go and pass through this action here, it's going to be either 0, 1, or 2. Now, we need to convert that into those arrays that we had, remember? So the arrays that we had from over here. Let's take a look at actions. So we are going to be getting either a 0, a 1, or a 2. So a 0 is going to give us this action. A 1 is going to give us this action, and a 2 is going to give us that action. So either move left, move right, or shoot. So what we are doing here is we are taking the action that comes through in our step function. We're passing it through our actions identity matrix, which is going to be those arrays, and we're going to be making that action. So remember self.game.makeAction, which is exactly how we took an action over here. And remember, we need to set our frame skip parameter. So we are going to do that. So comma 4. Cool. All right, so that means we've now got our action, we've done our reward. What else do we need? So we need our next observation, and we need our game info. So what we're actually going to be returning from this function, so we want to return normally we return state, reward, and then what else do state, reward, whether or not we're done, and our info. Okay, cool. So that's what we need to get out of this step function. So to get our game state, we just go state equals game dot state get state. Self.game.get is a get state. Yep. And then to get our image, we get image equals state.screenBuffer. So our image is what we're going to be passing back through to here. So we actually want this to be our image. And then we want to check whether or not we're done. So we can check whether or not we're done by grabbing this parameter here. So game.isEpisode finished. So done equals self.game is episode finished. And then what else do we need? So we need our info. So we need info, and that's going to come from our state. State. How do we get our game variables again? It's game.game variables. There we go. Okay, let's check that. So what have we gone and done? So we've gone and defined our actions. So let's add some comments. So take or specify action and take step. So that's what these two lines are doing. So we're specifying our actions. We're then taking a step within our game. So our actions are defined as actions equals np.identity3, because we've got 3 different actions that we can take. And then we'll specify dtype equals mp.uint8. We've then defined our reward. So reward equals, or we're defining how we get back our reward from our game. So reward equals self.game.make_action. And then to that, we're passing through our actions array, which is being filtered by our action index, comma 4, which actually gives us our frame skip parameter. Okay. And then here we're getting get all the other stuff we need to return. And so the first thing that we're doing is we're getting our game state. Now this includes this doesn't actually return back the screen buffer. So we could actually just grab this, but we need our info. That's fine. We'll leave it as is. So our state equals self.game.getState. And then what we're doing is we're grabbing back our observation back. So image equals state.screen_buffer. This is actually the next frame that we're getting back from our game that we're getting in this line here. Then we're grabbing our info. So info equals state.game_variables, which we're going to be passing back through to here. And then we're getting whether or not we're done. So done equals self.game.is_episode_finished. Okay. So that is that now done. So let's test this out. So if we go and run this, okay, so that all looks good. So we can type in emb.step and we should be able to pass through 0, 1, 2, or 3 and this return back all of that info. All right, that's looking good. You can see we're getting our game frame, we're getting back our reward, we're getting back whether or not we're done, and we're also getting back our ammo percentage. So if we go and take a different step now, so let's take step, let's actually shoot. So if we go and take step 2, so that's us shooting. So you can see that he's shooting over there. Trying to get it to expand. No, doesn't want to expand. All right, whatever. All right, so we can keep shooting. Okay, so now it looks like we've got a bit of an error. So it looks like at the moment we don't actually have a screen buffer. So what we should do, and this is because we've got to the end state, so we should actually apply a little bit of logic to ensure that we don't get this error, because that's going to cause issues when it actually comes to training. So let's close this for now. And what we're going to do is when there is no screen buffer or state actually available, we're just going to return back 0 so that we don't throw an error and crash the entire training cycle. So let's actually fix this up over here. Okay, so that is looking okay. I'm not liking that we've got this image over here. This is kind of killing me that we've got this line and we're not really using it. So what we can actually do, given the fact that we've gone and cleaned this up, so we're going to change state equals to self.game.getState. We're just going to append .screenBuffer to it. That's going to clean that up. And then, so we can get rid of this image line. And then our info can just be self.game.getState.game variable. So that just makes it a little bit cleaner there. So then we're going to return back state down here, and this is going to be state over here as well. So that looks much cleaner. So state equals self.game.get_state.screenBuffer. Info equals self.game.get_state.game variables. Okay, now let me show you what I've actually gone and done for this logic bit here. So if we don't have anything being returned from game.getState or it's zeros, what we're then going to return is a numpy zeros array. So np.zeros, and then the shape that we're passing through to that is self.observation_space.shape. So rather than returning through an actual game observation, it's just going to be an array filled with zeros. And our info is just going to be a value of 0. And then I've moved done a little bit further down. So done equals self.game.isEpisodeFinished. Okay. So now if we try running this, let's have a look. So we're going to render again. Let's keep going. Okay, so it doesn't look like it's throwing errors. So we're good now. Cool. Okay, so now we know that we're done. So we're returning back true. We've got our reward and we're not getting any errors. So that is all looking much better. So we can close that down. That is our step function now defined. Now, the next thing that we're going to need to do is define our, let's actually do our reset function. Okay, so inside of our reset function, we are going to run, so we need to pass through self. And we're going to say self.game. What is it again? It should be... How do we create a new game? New episode. So let's pass that down here. Self.game.new episode. And we are going to get back our state from here. And we should just return state. I think that's good. Okay. So if we create our environment, env.reset, should actually get our state. That is not returning anything. Close this down. Oh, because it's not actually going to return that state. So this is going to create a new instance. So we need to run self.game.getState .screen buffer. Let's try that now. Okay, that looks much better. So we've now got our frame. It's all looking good. If we take a step, close. We're getting controlled Vizdoom. Oh, we've gone and closed it down. Now we're getting thrown a bunch of errors. So if we go and create a new instance, reset, state, step. Just test this out. This looks like it's working fine. Okay, you sort of get the idea. So that looks like it is running successfully. All right, what else is left to do? So we've now gone and returned our screen buffer. We've gone and defined our reset function. The next thing that we should probably do is define our grayscaling function. So what we're effectively going to be doing here is we are going to grayscale our image and we're also going to resize it. So by doing that, we're also going to need to reshape our observation space. All right, so the last thing that we need to do is go on ahead and grayscale our image. So at the moment, we are capturing all of the colors and we're also capturing the bottom bit of the game. That's not actually going to add value when we actually go and train a reinforcement learning agent. So we can actually cut that bit out. So that's exactly what we're going to do inside of our grayscale function. So let's actually go on ahead and do this. So we are going to be passing through self so we can grab our own instance, and we are actually going to be passing through our observation. So this is effectively our game frame. So let's go on ahead and grayscale this, and then we'll take a look at what we wrote. Okay, that is our grayscaling done so far. So we're going to do this step by step. So rather than just doing the resizing, we'll do this step by step. So first up, what I've gone is I've written def grayscale, or the full function is def grayscale, and then to that we're passing through our own instance. So self, comma, observation, which is going to be our gray game frame. Then I've written gray equals cv2.cvt color. If you've watched any of my OpenCV tutorials, you know that you have seen this a ton of times before. This allows you to change the color channels and the color orders. And then we're using np.moveAxis, and we're just reshaping the actual array. So if I go and do we actually have a frame? So state, yes, so state.screen buffer. Actually, we can just use this. So let me show you the shape beforehand. So state.shape equals 3, 240 by 320, right? So if we go np.moveAxis, 0, -1, this is going to reorder where our channels are. So you can see that it's 3 right now. We've now gone and moved it to the end. And this is the format that the BGR or the CVT color method actually expects our image to be in. The image is still going to work. It's just that the color channels are going to be at the end now when we go and apply this cv2.cvt color method. So the full line is gray equals cv2.cvt color. And then inside of that, we've written np.moveAxis, and then passing through our game frame observation, 0. So this is saying grab the first axis or the first channel, which is going to be our colors, and then move it to the end. So -1. comma, cv2.color underscore bgr to gray. So this is effectively going to be grayscaling our image. Now, what we actually need to do is actually apply this method. We actually haven't actually gone and used it yet. So what we can do is find wherever we're actually grabbing our game frame, and we just need to apply that grayscaling function. So over here under step, we need to get state and run self.grayscale and then pass through that state. So this is effectively going to apply our grayscaling there. And we should also do this inside of the reset method. So we're going to say gray or state equals, how should we do this? Let's grab this. And then we are going to return self.grayscale state. That should effectively work. Let's actually run this. So what I've gone and done is we've gone and fleshed out parts of the grayscale method. And then what we're going to be doing is we are going to be running, or we've added an extra line inside of our step method. So state now equals state.self.game.getState.screenBuffer. And then we're applying our grayscaling here. And again, all this code is going to be available in the description below. So let me zoom out so you can see it a little bit better. Right, so this is our full class. What we're doing is we're applying grayscaling here, and we're also applying grayscaling down here. So if we go and run this now, so run our environment, let's take a look at our state. So you can see that it is now grayscaled. So it's just 240 by 320. We don't have the color channel anymore. So this effectively means that rather than having all of the other components to that, or all of the other color channels, we're not actually going to have that. Now, we can actually go and try to visualize this, because right now we don't actually know what that frame looks like. So what we can do is we can actually go on ahead and install matplotlib. So pip install matplotlib, and we can actually try to visualize this. It looks like it's already installed. So we can run plot.imshow and then pass through that state. Oh, we haven't imported it. So from matplotlib, import pyplot as plt. And we'll clean up this code in a sec. I'm just getting it working. Okay, cool. So that is our image at the moment. Now you can see it looks kind of weird and bluish, and that is because it is using an OpenCV color. So if we type in cv2.color, actually cv2.cvt color, and then we can type in cv2.color. I wonder what we actually need to convert this to. What would it be? BGR to RGB. And we need to close that. Okay, there you go. So you can see that it is in fact gray at the moment. So we don't have a bluish tinge. We've actually gone and grayscaled our image. So we have now gone and successfully done that. Now, what I've gone and done there is I've just gone and imported matplotlib, which is a really great graphing library, which just makes it a little bit easier to actually visualize what's actually happening. Okay, so we've gone and grayscaled. The next thing that we want to do is we want to get rid of this bottom buffer here. We don't actually want that. So we are just going to add in an extra step inside of our grayscale method to do that. Okay, so that is our frame now resized. So what I've gone and done is actually, I don't think we've actually gone and cut off. I don't end up cutting this, the game frame off at the bottom here. So let's actually just go and test this out. I think that might be the next tutorial that I'm working on. Hold on. So let's actually take a look. Yeah, so we don't cut it off. We just make it a little bit small. So we compress that frame down. So what I've gone and written is gray equals cv2.cv. Oh, the new lines that I've gone and written are resize equals cv2.resize. And then we're passing through our gray image, and then we're just making it smaller. Sorry, my apologies. I thought we were going to be cutting off that game bar. You definitely could. In order to preserve what I've actually gone and built here, I don't want to go and rip it out now. But what we've got is 160, 100. And then we've gone and specified interpolation equals cv2.intercubic. So this effectively resizes our image and scales it down. So we've got less pixels to process. So again, same sort of theory. So we could take the game bar off, and that's going to effectively take out any extraneous information which isn't adding value. In this case, I'm just making it a little bit smaller. And then what I've gone and written is state equals np.reshape. We're passing through this resize variable here, and we're specifying it as 100, 160, 1. So if we go and run this now and create our new environment, you can see our shape is now 100 by 160 by 1. So this has effectively gone and cut down the number of pixels that we now need to process. You can see that we've still got our image down here. Okay, so now that that's done, so we can get rid of that, we can get rid of that, we can get rid of that, and we can get rid of that. And we've already got that matplotlib now installed. The one thing that we do need to fix now, though, is that we've actually got this shape here defined incorrectly inside of our observation space, because we've actually gone and grayscaled and reshaped it. So we now need to reflect that change up here in this observation space up here. So we are going to change it to 100, 160, 1, which is effectively state.shape. 100, 160, 1, 100, 160, 1. So that is our environment now effectively set up. So I don't think we've got anything left to do. Let's actually take a look. So we've gone, oh, we need to actually inherit from the base class. So we can run super.init inherit from env. Hold on. Wait, we don't need env here. Cool. All right, that's good. All right, so what we've gone and done, I just added super. This is going to be inheriting from our env class. Okay, so we've gone and defined our init function that has a ton of stuff happening. So we're setting up our game, we're setting up our render logic, we're setting up, or we're starting the game, we're creating our observation and our action space. We've then gone and defined our step function. So this defines how we actually take steps, how we do our pre-processing. We haven't done anything on render because that's sort of handled by Vizdoom itself. We've gone and defined our reset method. We've gone and defined our grayscale method, and we've gone and defined our close. So now let's just kill off any Vizdoom instances that we've got running so we can end that task and that task. Do we have any others? Nope. Okay, cool. So if we go and run this, that is our environment now up and running here. And if we go and reset our instance, now if we go and take a step, so we can type in env.step 1. So right now our monster is sort of to the left. So if we go and type in step 0, that's moving us to the left. Step 0 to the left, step 0. Now if we go and shoot, pass through 2. No, don't go to the left anymore. Boom. So it's gone and killed it, and the game episode is done. Then we can run env.reset. Boom, new game. All right, so that is all up and working. We can now go and run env.close. Okay, that is our game up and effectively running. Let's jump back over to Bob and have a chat.
It's done, dude. Sweet. So what's next? Well, given that the model's now in a standard format, we can actually start building some models to play the game. Nice. So you gonna start basic or what? Yep, I think we'll kick off with the basic environment and then build up from there.
So we got the game working, but now we got to apply some AI. For this, we're going to be using reinforcement learning, and specifically the PPO algorithm like we did in the Mario vid. But this time, I'm going to explain it a little bit more. First, a quick refresher on reinforcement learning. RL has 4 key elements: agent, reward, environment, and action. The Doom guy in this case is our agent. He can take some action, for example, shooting, moving left, moving right, and so on, inside of the game environment. Then, depending on the results of his action, he might get a reward. The AI controlling Doom guy learns what actions to take inside of the environment in order to maximize that reward. Now, how exactly does this happen? The PPO algorithm is what allows us to perform reinforcement learning. It's built on top of an existing high-performing algorithm called actor-critic. In a nutshell, there are 2 neural networks inside of PPO: an actor, which controls our actions, and a critic, which tries to predict the future returns from the current state. So how does it work? Step 1. First, we get an observation from our game. In this case, it's the current frame from Doom. Step 2, that image is then passed to the actor and critic networks. The actor outputs a set of probabilities for which actions to take. This is referred to as the log probability. At the same time, the critic outputs the expected future returns from the current state. Think of this as a prediction of the sum of all of the rewards from here on out. This is referred to as the value. Step 3. Now that we've got a selected action, we can use it to make a move in our game. So our player moves, and in return, we get the next frame from Doom. We also get the reward, whether the game is over, and other game info. All of this information, the observation, reward, action, value, and log probabilities, are then stored in a temporary buffer. Step 4. This continues onwards until the game is done or we hit the max game length. This parameter is set by the algorithm. Once we've gone through the game and collected all the outputs, we can then train the actor and the critic to perform better. The outputs from one whole game or episode is called a trajectory. Step 5. Once we've got all this good data, we can get to training. First, we calculate the advantage our agent generated. This tells us how much better our agent performed than expected by the critic network. This is calculated as the discounted sum of rewards minus the discounted value from the critic network. Now you're probably thinking, why do we calculate this? Well, if the agent performed better than expected, we want to incentivize it to take the same action again, and vice versa if it performed worse. So, we define the loss to include the probability of taking that action multiplied by the advantage. This means that if the probability was low and it generated a positive advantage, the probability of that action will increase after applying gradient descent. The full PPO loss function isn't just the probability multiplied by the advantage. It actually uses a clipping parameter and the ratio of the current probability versus the probability from the old agent to stabilize learning. I've simplified it a bit here to make it easier to understand. Step 6. Now that we've trained the actor, we can train the critic to better predict future rewards based on the state and action. The loss here is defined as the mean squared error between the discounted actual rewards and the predicted returns. A lower number here indicates that the model is performing better and that it is able to better predict future returns. That's one full training loop. The buffer is then cleared, a new game is played, and the training loop is run again. Ideally with the goal to increase the probability of taking actions that create the highest possible total reward for the entirety of the game. That's how our little old agent learns. So we've got the majority of the hard bit now done. We've got Vizdoom installed, we've actually gone and visualized it, we've actually gone and created our OpenAI gym framework. Now what we can actually get onto doing is the good bit. So actually training our deep reinforcement learning model to be able to use it. Now I just realized I deleted a section from this. So this should actually be section 3, view environment, view state. Cool. All right, so the next thing that we're actually going to go on ahead and do is set up our callback. Now this callback is purely optional, but it effectively means that you're going to be able to save the reinforcement learning model as you're going through and training, so you don't need to manually go and save it. And it also means that if anything goes wrong, you've actually got different versions of the model saved at different states of training. So first things first, what we need to go on ahead and do is install a couple of things. Now, the first thing that we need to install is PyTorch. So to install PyTorch, we can just go to pytorch.org and then hit install. And then if you scroll on down, we are going to be using the stable build for Windows. We're going to be installing it by pip, Python, and we're going to be using CUDA 11.3. So if I copy that, now again, if you're using a different environment, Mac or Linux or Conda or libtorch or one of these others, you just need to select the different options that you want, and you're going to have the command down there. So I'm going to choose stable, Windows, pip, and then Python, CUDA 11.3. So if I copy that, jump back over into our notebook, and then drop the 3. And if I run that command, that's going to go on ahead and install PyTorch, which I've already got installed here. So we are now good to go. Now, the next thing that we need to do is actually go on ahead and install Stable Baselines. So Stable Baselines is the framework that allows us to use the algorithms like PPO and all of the other cool stuff that happens, or all the other cool algorithms available for reinforcement learning. To install this, we just need to run this command here. So pip install stable-baselines 3, and then inside of square brackets extra. Now again, I'm going to include this documentation inside the description below if you want to check it out. But for now, just know that that's the pip command you got to run. So if we copy that, exclamation mark, paste that in, and run that, that will install stable baseline. So that means we are now, doesn't look, let's check. So we're just getting that pip warning again. That's perfectly fine. Don't worry about that. All right, so we've gone and installed PyTorch. We've now gone and installed stable baseline. So the stable baselines line is !pip install stable dash baselines 3. And then inside of square brackets, we've got extra. Okay, so what else do we need for this callback? First up, we need to import some dependencies. So let's go on ahead and do that. Okay, that is, I don't know what's happened there. That's kind of weird. That is those are the two dependencies that we need now imported. So we've gone and written 2 lines of code there. The first one is import OS. So this is just importing the operating system module for Python, which just makes it easier to navigate through different folder structures and save stuff. It's going to be important when we actually go to save our different models. And then we've gone and imported the base callback class. So from stable underscore baselines3.common.callbacks import base callback. Now, rather than writing this callback from scratch, I'm just going to be copying it from the Mario tutorial. And again, this is the stock standard train and logging callback that I tend to use. So we've got that now set up. But to that, we need to pass through how frequently we want to save our model and actually log and where we're going to be saving stuff. So let's go on ahead and define those 2 paths. Okay, so I've gone and defined my 2 different directories. So the first one is going to be my checkpoint directory, and this is where we're going to be saving our trained reinforcement learning models. So the reason, these should actually be the same, so .. The reason that I've actually gone and created or save these inside a folder called train basic and log basic, I'll explain this in a sec, is we're actually going to be training different models later on in the tutorial. So just bear in mind that this is purely optional. You could change these directories to whatever you want, really. So what I've written is checkpoint underscore dir equals ./train underscore basic. So this means that when we start up our training, it's going to create a folder called train. It's going to create a folder inside of that called train basic. And that's where all of our saved models are going to be loaded. Then I've created a new folder called log underscore dir, and I've set that equal to ./logs/log basic. Cool. Now what we can do is we can create an instance of our train and logging callback. So let's do that. Okay, so that is our callback now instantiated. So I've written callback equals train and logging callback. And then to that, what I've done is I've passed through the check frequency to check underscore FREQ equal to 10,000. So this basically means that after every 10,000 steps of actually training our model, we're going to save a version of those PyTorch weights for our reinforcement learning agent. So this means that if we wanted to go and reload it from that point onwards, we could definitely go and do that. Then I've gone and specified my save path. So save underscore path equals checkpoint dir. So that's that over there. Our log dir is going to be used in a sec when we go and create our agent. Okay, so that is our callback now done. So we've gone and installed PyTorch. We've gone and installed stable baselines. We have also gone and imported those dependencies, gone and copied over our train and logging callback, created our checkpoint directory and our log directory, and we've gone and set up our callback down here. Now, remember when we were creating our environment, I said that there was this environment checker that you can actually go and use. Let's move this down. This should be down here. There's an environment checker that you can actually go on ahead and use to see whether or not your environment is in the right format. Well, I found this super useful when I was actually testing this out. So let's go on ahead and try this out. So I'm just going to go back to section 2 for a sec, and let's actually test out our environment checker. So this is actually coming from stable baseline. So we can actually import it, or first up, we need to import it. Okay, that is our environment checker now imported. So I've written from stable underscore baselines 3.common import env checker. This is super useful, particularly when you're creating your own environments, because it checks whether or not you've got a valid environment. Super, super useful. So in order to use this, we can just run env checker, and then let's double check. So what do we need to do? We just need to pass through, doesn't actually give us that greater documentation. We just need to pass through our environment to it. So let's create an environment. So env, we don't need to render in this particular case. Oh, let's leave it. So it's the same. So that's our environment. To that, we can pass through that. Module object is not callable. We actually need to run .check env. And we've got some errors. All right, so let's have a look. So the info returned by step must be a Python dictionary. Okay, so we've actually got a valid error here. So this is telling us that what we actually need to do is we need to reformat our Python dictionary, or the info that we're getting from our Python dictionary, to be in a slightly different format. So we can actually do this if we go back into here. So rather than just returning back our baseline game variables, we can actually just grab the value from that and we can specify. So let's call this ammo for now. And then rather than just returning back the array, we're going to be grabbing the specific value, and then info can be a dictionary. And we're going to call that ammo. And then to that, we're going to be passing through ammo. Let's try that now. Go and pass this. Okay, so we've got rid of that error. So this is really, really good, particularly when you're getting your environment set up, because it actually allows you to see whether or not you've got a valid environment to actually work with. So in this particular case, we already saw that we had that error there. So by quickly reshaping what info is actually returned from our environment, this is going to save us from a lot of heartache later on when it comes to training our actual model. Okay. So that is looking good. Now the next thing that we need to do is actually go on ahead and train our model. So let's get started on that. Okay, so in this particular case, in order to go on ahead and train our model, what we are going to be doing is we're going to be using the PPO algorithm, which we talked a little bit about in the animation, or the sort of breakdown of how this actually works. Now, what we need to do in order to do that is first up, import the PPO algorithm from stable baselines 3. So let's do that. So we're going to import PPO for training. And to do that, it's pretty straightforward. So from stable baselines 3, import PPO. Cool. Now, in order to keep things nice and neat, I'm just going to close down any environments that I've got currently running so we can end those tasks. And we're going to create a new environment. So env equals Vizdoom gym, and we don't want to render. So I'm going to set, by default, it's not going to render, right? Let's double check our class. Yeah, so render is false by default. So we don't want to render because that's going to slow down our training. So we're going to create a non-rendered environment. And then we are actually going to go on ahead and create an instance of the PPO algorithm. So we're going to call this model, and we're going to specify PPO. And then first things first, we need to define what type of policy we're going to be using for our policy, or what type of neural network we're going to be using for our policy. So we're going to specify CNN policy because we're passing through an image. We then need to pass through our environment. We also need to pass through our TensorBoard logging DR. So this is going to be where we're actually going to be logging out our information. So we are going to be logging that to our log directory out here. And then we need to specify a couple of other parameters. So we're going to specify verbose equals 1 because this is going to give us information while training. We also need to specify our learning rate. So this is effectively how fast our algorithm is actually going to learn. So we're going to set that equal to 0.0001. Now you can play around with this. In some certain circumstances, you could actually increase the learning rate. In other circumstances, you might want to decrease it to ensure that you're effectively actually going through and learning the right things. Now, the last thing that we need to do is set end steps. So let's just double check how many frames, or what's the maximum number of frames that we have for our basic environments. If we go to YouTube, Vizdoom, and then inside of GitHub, Vizdoom scenarios, if we go to basic, okay, so make episode finish after 300 actions. So we've only got a maximum of 300 actions that we've got in here. So we can set end steps to, I don't know, let's set it to 256 for now. You could definitely increase this or decrease this. I think good practice is to set it not to the entire length of the game, but ideally somewhere pretty close. We're going to set it to 256 in this particular case. And this is effectively how many frames or steps that our agent is going to take and store in the buffer before it actually goes and runs through training of our actor and our critic. So that is what that parameter actually is there. So it's either going to run until the episode is done or to that maximum level, which is 256. Okay, so that is that now specified. So if we go and run that, it doesn't look like we've got any errors. So it said using CUDA device, so it's going to be using my GPU. It's wrapping it in a monitor wrapper. So this means that we're going to be able to get, I think, episode rewards and episode lengths. And we're also getting our dummy vectorized environment and it's transposing our image. So these are just transformations that's stable baselines. 3 goes and applies. So let's quickly go through this line again. So I've written model equals PPO, and then I've specified that we want to use a CNN policy because we're going to be passing through an image. Now remember that our PPO algorithm has an actor and a critic. This basically means that it's going to be using a CNN or convolutional neural network type policy for each of those in order to go on ahead and train our agent. We're then passing through our environment, which is a non-rendered environment. So this means that it's going to train faster. We're specifying our TensorBoard log directory. So this is where all of our logs are going to be saved. We've specified verbose equals 1. So this means that we're going to have some information appearing as we're actually going to go on ahead and train. And I'll talk you through some of those in a little bit more detail. We're specifying our learning rate and we're setting that to 0.0001. Yep. And then end steps, we've set that equal to 256. So this is effectively how many ticks or how many frames we're going to be storing, or what is our maximum trajectory length for PPO. Okay, so that is all well and good. Now what we can actually go on ahead and do is actually train our model. So to do this, we can type in model.learn and pass through how many time steps we want to run for in total. So total time steps, we're going to set that to 100,000 for now. We could probably train for longer, but I think this environment isn't super complex, so the agent's actually able to learn it relatively quickly. And in order to ensure that we actually go and save our models, we need to pass through our callback, which we had down here. So we can run callback. We can set that equal to callback. And if we go and run this now, all things holding equal, this should effectively go on ahead and run. So this first bit is saying it's logging to ./logs/log basic/ or /PPO1. So if we go into it now, go to YouTube, Vizdoom, logs, we've got log basic, we've got PPO1. So that file there is our TensorBoard log file. So that's going to allow us to monitor the training and the performance of our PPO algorithm as it's actually going through and training. Now, what you would have also noticed is if we go in, we've now got a folder called train basic. This is where all of our saved models are going to be saved as the algorithm actually goes through and trains our model. Now let's see, it looks like we've got an error. What's happened there? Into object does not support item assignment. Okay, let's actually read through this. All right, found the error. So what was happening was inside of the logic, inside of our game environment, what was happening is we just needed to do a couple of bits of tweaking to the info section. So let me actually Control Z this. So rather than specifying or passing back, let me undo that. All right, so rather than passing back a dictionary here, what would happen if we actually had an error in our game state or we reached done, we'd be returning back an integer, which the stable baselines algorithm doesn't necessarily like. So what we need to do is just create a new dictionary. So info equals dictionary. And in this particular case, we're not actually going to be using this information. It's purely just a descriptor. So we're going to set it equal to info and then info. And so what I'm going to do is out of here, we are either going to be returning this ammo value. So let's just return that, or 0. So this will mean that we effectively return a dictionary regardless of whether we have a valid state or whether or not we have an invalid state. But otherwise, it was going to throw that error which says you cannot assign a value to an integer. It's going to throw an error. So in this particular case, this is going to be fine. So we've changed it from displaying a... so in this particular case, if we didn't have an error in our game environment, we would be returning a dictionary. If we did have an error, we'd be returning a integer, which is not going to play nice. So in this particular case, this should effectively work. Let's run it through our environment checker. Again, still no errors. So that's one that apparently managed to get past our environment checker in this particular case, but that's fine. So let's just go on ahead and close down my Vizdoom environments because I think I got a ton. Z, or should be Z. Okay, so it looks like they're fine. Okay, let's go and kick off training again now. So I'm going to clear this cell. How do we clear this cell? Here we go, clear outputs. Okay, so let's go and create a new environment, kick this off, and then start training. Okay, so now it's going to be logging out to PPO4 because I ran it twice to debug. In this particular case, it's going to be going to PPO4 now. So if we go to PPO4, Vizdoom logs, log basic, PPO4, it's now there. Cool. But you can see that we're already starting to get some information back. So we are getting our episode length mean. So this means how many frames that our agent is able to survive on average or how long it is on average. We're getting our episode reward mean. So this is the total or the sum of total reward on average per episode. And then we also get back a whole bunch of additional information. So for once, I'm actually going to go into a little bit of detail for this here. So I've explained the length mean and the reward mean. So that's pretty straightforward. FPS, that's the frames per second. So effectively how fast our Vizdoom environment is actually processing. The iterations, I don't actually know what this one is. I think that might be the number of episodes, but don't quote me on that. Time elapsed, so how long it's actually gone for. Total time steps is how many time steps our agent has actually seen. So how many frames it's actually processed. Okay, now to the good bit. So prox KL. So the way the PPO works is by looking at the previous agent and looking at the previous probabilities from the old agent versus the new agent. So as it goes and trains through, it actually looks back at what it was predicting previously. Now, this is a measure of how different the current agent is from the old agent. If you see this spike massively, then it means that we have unstable learning. So ideally, this should vary and not be the same, but it shouldn't spike because otherwise that means that we've got huge divergence and we have effectively unstable training. Now, if we do have unstable training, the way the PPO works handles this is by using something called PPO clipping. So this means that if we've got a huge change, PPO clips that change so that it doesn't throw out our training a whole heap. This clip fraction tells us whether or not it was able to take the base ratio, so whether or not it was able to not have to clip and go on ahead and train versus the amount of times it did have to clip. So right now it looks like it had to clip 13.9% of the time. This tells us the range that it has to clip, so how much it's actually going to clip by if it needs to clip. Entropy loss, I didn't actually go into this one into too much detail because what I actually found is that that is particularly important if you've got shared weights, but there's more important metrics to pay attention to here. Explained variance is a measure of how well our critic model is able to explain the variance in our value function. So ideally, you want this to be positive because that means that our critic model is able to predict the value of the current state in a lot more detail. Learning rate, that is just a hyperparameter, so we can set that. Clip rate is a hyperparameter as well, so these aren't going to fluctuate. They're set unless you use a schedule. Loss, again, this one isn't as important as these two down here. So N updates is how many updates we've actually gone and made to our actor and critic policy networks or actor and critic networks. All right, policy gradient loss. This one is super important. So this one tells us how well our agent is able to take actions to capitalize on its advantage. Ideally, you want to see this decrease, which means that the loss is decreasing, which means our agent is able to better capitalize on advantage. Value loss tells us how well our agent is actually able to predict the current return based on the current state and action. So again, you want this one to decrease. Now, what you're going to notice is that the policy gradient loss is going to fluctuate quite a fair bit in the start, and then it's eventually going to head down. So let's actually take a look at what these look like when we plot them out. So I'm just going to open up a new terminal, and I'm going to go to that log directory, which at the moment is inside of PPO4. So let's go to it. So CD, I'm going to go into my YouTube directory and then go into Vizdoom, which is in folder 26-05. And then I'm going to activate my environment. Don't worry if you don't have this, just go straight into your logs, Vizdoom, and then scripts, activate. Then we're going to go into our logs directory, which is here. And then we are going to go into our log basic folder, which is there. Remember, we defined this. And then we're going to go into our PPO4 folder, which is there. And then we're going to start our TensorBoard logging capability. So to do that, we just type in TensorBoard --logdir equals dot. So the full command, let me move that over here so you can see it. So the full command is TensorBoard --logdir equals dot. And that assumes you're in the current folder where your model is actually logging out to. So if I go and run that now, this should start up TensorBoard. Cool. So if you get this warning, that's fine. It just means that you don't have TensorFlow installed in your current environment. You'll still at least able to log out. So if I go to, it'll also tell you where it's going to start up the server. So here it is running at http://localhost:6006. So if we go to there, we get our logs. So let me zoom out a bit. Okay, so what this is telling us is that we are, so our length is increasing. So this means that we're living for longer. Our reward mean is dropping. So that means that we are not capitalizing on reward, which is a little bit strange and probably not so great. If we go and take a look at our model, our explained variance is going up, our value is going down, our policy gradient is looking a little bit low at the moment. So we will let that train for a little bit longer. Ideally, you want the explained variance to keep going upwards. You want your value loss to near zero a little bit more. So right now we can see that down there, it's looking like the value is the number to pay attention to here is 2084. What's our policy gradient loss at the moment? So right now it's looking like it's pretty low, but that is not all that great. So we'll let that run for a little bit longer. And ideally what we should do is we should see these metrics eventually sort of stabilize. So our value loss should eventually trend back towards zero. Policy gradient loss should spike up a little bit more and then trend back down to zero. But if you hit refresh up here, you'll actually be able to see what the performance is like over time. This isn't looking so good at the moment, so we might need to do a little bit of additional training. But for now, let's let that run and then we'll see what that looks like.
A few minutes later.
Alrighty, so at the moment, I haven't stopped training yet, but it doesn't look like this is actually performing all that well. If you start to see policy gradient loss going to almost zero really, really quickly, that's an indicator that your model isn't actually learning all that well. And it's effectively just taking the same action every single time. This is also indicated by this approx_KL function here as well, which basically means that there's no divergence from the previous policy to the current policy. So this means that it looks like we've got a couple of issues here. So what we can actually try to do is I'm actually going to stop this training. So just by hitting stop, that looks like that is completely finished. Yeah, no, this isn't actually improving. So we should see this episode reward mean start to trend upwards rather than just go straight downwards. What I'm going to try to do is let's actually change the number of steps that we're actually going to take. So let's bump this up significantly. So the other parameter that I actually tried previously was significantly higher. And I wonder whether or not that 300 ticks represents the number of frames or whether or not there's multiple frames per tick. So let's actually change that. So I'm going to set that to 2048, create a new model, and then we're going to start learning again. So this is now logging to PPO5. So down here, and this is a pretty common process, guys. So when you're training these models, they can be very finicky, and sometimes you do need to change hyperparameters to effectively get better training. But this is an indicator that this isn't performing well. You shouldn't see episode reward mean just tank and stabilize there. It should effectively fluctuate a little bit. And you definitely shouldn't be seeing this. So policy gradient loss, let me move my head so you can see it. Policy gradient loss should not be trending towards zero. Bad indicator. That looks like it's not performing well. So let's go into, opening up random stuff. Let's go back in now. So I'm going to go back out of PPO4. I'm going to go into PPO5. Let's see what that looks like. So that's just an indicator really on that you can see that these models aren't actually performing well. Okay, so this is only going to give us some information back once it's started training. So once we get that first little block of info coming back from our model.learn function, we'll have an idea of how this is actually performing. This is way too small. Okay, so that's started. So we should get our first log out of here. Cool. All right, let's give that a sec and then we'll come back and we'll take a look at our logs. Okay, that's at least our first log now displayed. So we've got, how's this looking? So explain variance looking like it's trending towards 0, which is okay for now because that's going to increase over time. That makes sense. KL, so that looks like 0.03. So there is at least some variance between the current policy and the previous policy. Policy gradient loss, that looks okay. Value loss is pretty high as well. So if we go and refresh this, so that's fine if our episode reward mean goes down, as long as it doesn't just go down and keep going down. It should fluctuate a little bit. So let's wait for another log to come out and we'll see how that's going. Okay, that is looking much better now. So we can see that our episode reward mean is increasing. So rather than having 75.6 and just tanking downwards, we are now at least heading towards positive. So if we go and refresh this, you can see that that is looking better already. So even though our episode length mean has decreased, that is perfectly okay. We actually expect the length of the episode to decrease because our agent is able to more closely go head straight to that monster and shoot him down. And we can see that our episode reward mean is increasing now, which is another much better sign. So in this particular case, increasing that n steps hyperparameter gives our agent a slightly larger buffer to learn, which means that we're not going to head straight down towards 0 for our policy loss. So this is looking better already. So we're going to give this a little bit of time, let this train, and then we'll come back to this and I'll walk you through it and we'll see how our model is actually performing. And then we'll jump back over to Bob and see how that goes.
A little longer than a few minutes later.
Alrighty, so increasing the number of steps that we run our agent for was a great move. So you can see now that we have significantly better performance. Now you're probably thinking, Nick, you're just showing me a bunch of graphs. What the hell does this mean? Well, let me walk you through it. Okay, so the most important graphs, or the two most important plots here, are these two. So the first one, this is the episode length mean. This is how long on average every single game took. Now, the faster the game in this particular case means effectively how long our agent has taken to complete that level. Now, this might either mean that the agent has either died really quickly or it's actually completed the level really, really quickly. Sometimes it takes some visual analysis to actually see what this actually looks like. But one good indicator that we actually have good performance in this particular case is that we have our episode reward mean that has increased significantly. So you can see over here that our episode reward mean has hit a average of about 85.89. So you can see that in that value metric. So if you look at value down there, we've got 85.89. That is a really good score in this particular case because the maximum score that we can get is 101, and that can only effectively be achieved if the monster is right in front of you and you've actually hit it the first time. So in this particular case, that is looking pretty good. It looks like we have had some divergence and now our agent, or now the existing or the current policy, is pretty close to the latest policy. So our approx KL is reduced. So remember, this is a metric of how different our old policy is from, or how different our new policy is from the old policy. So you want to see this increase and then come back down. But if it increases too much, then it's going to get clipped. So you can see that that clip fraction is increasing up there. Our explained variance, why won't this move? Our explained variance has got up high. So right now it is at 77.38, which is a good sign. It means that our critic is able to accurately, or closer to accurately, predict what the future sum of returns is going to be given the current state in action. And you can see that that value loss has decreased. So this is a good sign. Policy gradient is sort of fluctuated, and you can see that it's increased as our value loss has decreased. And this is effectively because as our critic is better able to predict its discounted future sum of rewards, the ability to determine advantage is decreasing. So this means that this might increase a little bit whilst this decreases. But the fact that our episode reward mean has increased is a really, really good sign. So that is effectively our agent now trained. Now, another thing that I wanted to show you is that because we've now gone and finished training, I've actually stopped this a little bit early, by the way. So if I actually go in and show you, we've gone up to 51,200 time steps. So I didn't need to go all the way to the end. 51,200 got us to an episode reward mean of 85.9. an explained variance of 0.774, a value loss of 38.4, which is a mean squared error, which is very, very tight, or a very tight tolerance, and a policy gradient loss of 0.176, which is looking pretty good as well. Now, what I wanted to show you is that we should effectively have our trained agents in here. So these are our historical trained policies. So in this particular case, we are good to go. Let's jump back over to Bob and see what he thinks.
So the model's trained and tuned, Bob. You want to check it out? Yeah, let's see it. All right, so I'm actually going to show it to you at different stages of the process and show you how and what it's learned. Cool? Cool.
Alrighty, now as expected, Bob wasn't going to let us get off the hook by just saying the model is trained. He wanted to see how that model actually performs. So let me actually show you how to do this, and we'll actually be able to test it out. So the first thing that we need to do is the first thing that we want to be able to do is have the capability to reload a model from our disk. So we can do this using model.load. So if I type in model.load, or we could even go ppo.load. So let's do ppo.load. So I'm going to create a new instance. I'm going to say model equals ppo.load. And then we just need to pass through where our current model is currently stored. So in this particular case, it's in train basic, and over here. So we just need to reload that. So train basic. And then the name of our latest saved model is best_model 70,000. So that is our model loaded. Now what we can also do is we can import a function that allows us to test and evaluate our model. Let's make this a little bit bigger. So let's first up go and import this evaluate model function, and then we'll actually be able to test it out. Okay, so that is our evaluate policy method now brought in. So I've written from stable_baselines3.common.evaluation import evaluate_policy. So this will allow us to actually test out our model. So let's actually go on ahead and test this out. Now, rather than doing it non-visually, let's actually render it. So let's create a new environment. So I'm going to type in env equals Vizdoom gym, and then we're going to set render equal to true. So that's our environment we can now use. We can now store our mean reward, comma underscore equals, and set that equal to evaluate policy. So this is effectively how we can use the evaluate policy method. So to that, we pass through model, the environment, and then how many times we want to evaluate. So we're going to run it for 10 games. Okay. So let's take a look at what we've done there. So first up, we've gone and reloaded our model using ppo.load. So I've written model equals ppo.load. And then I've passed through the full file path to that model that we want to reload. So let's add a comment, reload model from disk. Then we've gone and created a rendered environment. Then we're going to go on ahead and use the evaluate policy method to actually test this out. So evaluate mean reward for 10 games. And to do that, I've created two variables that we're going to unpack. So mean_reward, comma underscore equals evaluate_policy. And then to that, we'll pass through two positional arguments. So model and the environment. So this and this. And then we specified how many games we want to evaluate our policy for. So if we go and test this out now, let's minimize all this stuff. Let's close any instances of Doom that we've already got running. So that's our environment now up in there. Now, all right, cross your fingers, guys. Let's see how this actually performs. All right, you can see it literally just smashed through that. So that was actually 10 games. But you saw how fast it was actually moving towards and actually killing that agent. Now, let's actually run it for 100 games rather than just 10. So you can see it's moving, it's killing that agent. Let me make this a bit bigger. Like, it is literally moving so fast, you can't actually see it. It is shooting the monster in this particular case. So let's take a look at our mean reward. 86.72. So you saw how fast that was actually going. So that is how to actually run it using the evaluate policy method. Now we can also do it inside of a loop. So let's do it using that method as well. Okay, so that's the loop that we can use to run to actually test out our agent without actually just using the evaluate policy function. So let me walk you through this. So we're going to loop through each game, and in this case, we're going to be playing 5 games. So 4 episode in range 5. So this is just going to be incrementing 1, 2, 3, 4, 5. And then we are going to first up reset our environment. So we're going to run env.reset and store the game frame inside of a variable called OBS for observations. We're then going to set a parameter done equal to false. So this is going to state that we haven't actually completed the episode as of yet. And then we're going to run while not done. So while our episode isn't finished, we're going to use our model to predict what action to take. So model.predict, and then by passing through our observation, we're going to get our action back. So either 1, 2, or 3. So once we've got that action, we can then go and take that and pass it to our env.step method. And out of that, we're going to get our observation and reward, whether or not we're done, and any info. We're then going to use time.sleep to take a little bit of a break. So this loop is very similar to what we did right at the start. So once we've gone and slept for, 0.05 of a second, we're then going to accumulate our total reward. So we can see what our total reward is. We'll print it out. So I've just got a print string method or print formatting method here. And then we're going to sleep between each game for 2 seconds. So you can actually see what that performance is like. So if we go and run this now, what do we do? So time.sleep. We've got an error there. We need another set of brackets there. What's happened? Number of dimensions larger than 1. What are we getting back from? So if we run model.predict OBS, so we get this first value, which should be our actual action. So let's unpack that. So all right, let's try that. Nope, still got an error. Total reward is not defined. Okay, so we need to instantiate our total reward. Set that equal to 0. You can see it. It's heading towards the monster every single time. Boom. Boom. So you can see that it is actually moving toward... Let's actually slow it down even more. So let's give it 0.25. So because the monster is like pretty much directly in front of our agent, it doesn't actually need to move all that fast. So there it's moving, shot. So you can see how much better this agent is performing versus the random one. Now let's quickly take a look at each one of the different stages of how this model performs. So we're going to jump over to a montage and I'm going to show you it at 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, and you've already seen 70,000. So let's jump over to that. But that in a nutshell is how to train your reinforcement learning agent to be able to play Doom. After this, we're going to go back and have a chat to Bob. Alright, so first up's the model trained on the basic environment for 10,000 steps. At this stage, it's still pretty crap and still pretty random. 10,000 steps later, this brings us to our next model, and you can see the Doom guy is now at least shooting. Still pretty inaccurate at this stage, but at least he's progressing and getting a little bit better. What do you know? He also manages to score a kill towards the latter stages of this episode. Still, I think pretty random at this stage. $40,000 steps. Here's where things really start to shake up. You can see the Doom guy is progressively getting closer towards the monster each and every time. Still not super accurate at this stage, but definitely getting better. And 50,000 steps. Here's where Doom Guy's really started to lift his game. He's progressively heading towards the monster each and every time, and you can really start to see that the reinforcement learning model has started to do its work and has started to converge towards an optimal solution. I threw 60k steps in here as well. This isn't necessarily all that much better than the 50k model, but you can start to see that the model starts to really fine tune as it gets towards an optimal solution and isn't necessarily going to get that much better once it's achieved its goal. And just for shits and gigs, I figured I'd throw in a full speed run as well. This sort of shows just how fast this model is able to process and run through the environment. And that's our basic model now all done and dusted.
Hey Nick, do you think you could train the AI to play other levels? Sure can, although it kind of depends on the complexity of the environment. Right. Going super complex from the get-go can be pretty difficult for the agent to learn. There are a bunch of techniques that we can actually use to beat that though. For now, what do you say we try a slightly harder environment? One where the monsters actually fight back. Yeah, cool.
Alrighty, so now what we got to do is play some other levels. This is pretty easy in this case because we've already set up the OpenAI gym environment. All we have to do is change the game configuration file and update the actions that are available. We should then be able to use the same training flow to go on ahead and train our model. Alrighty, so Bob was pretty impressed, but to his point, it was a relatively simple environment. So there wasn't a ton of stuff that the agent had to do. It just had to move to the monster, shoot it, and then it was sort of done. Now, we can make this a slight bit harder. So rather than just training on the basic environment, remember right at the start, what we took a look at were all the other different environments that we had available. So if we go back in and we take a look at our GitHub repository, Vizdoom, and then scenarios, we had all these others. So we've got basic, deadly corridor, deathmatch, defend the line, defend the center, health gathering, so on and so forth. So if we actually take a look, the next one that we're actually going to take a crack at is defend the center. So this is let me actually just read out the scenario. So the purpose of this scenario is to teach the agent that killing the monsters is good, and when the monsters kill you, that's bad. In addition, wasting ammunition is not very good either. Agent is rewarded only for killing monsters so that he has to figure out the rest for himself. The map is a large circle. Player is spawned in the exact center. There's 5 melee only. Monsters are spawned along the wall. They're killed after a single shot, and after dying, each monster is respawned after some time. The episode ends when the player dies. Now, it is inevitable because of the limited ammo. So we get 1 reward for killing a monster. We've got 3 available buttons: turn left, turn right, and shoot. So the same buttons that we had when we were going and training our current model. So all that we really need to do here is we just need to change the map that we're using. So this is relatively straightforward. So what we can do is save this. And what I'm going to do is, let's just refresh that. So what I'm going to do is I'm going to make a copy of this basic environment so we can save that one. And we are going to, which one are we in now? So that's the copy. And what we're going to do is let's rename this first up. So we're going to rename this Defend Center. Rename. Oh my God. Rename. There we go. I'm going to call this Defend Center. You can name or whatever you want, not purely optional. Okay. So what we have, so we've got our basic tutorial, we've got our Defend Center tutorial now, or we've got our Defend Center notebook. So what we can do is import Vizdoom as per usual. All we really need to do is change what game config we load up. So we want Defend Center. So that is this one here. Let me zoom in so you can see it. Right, defend the center. We can grab that and replace that over here. So inside of the game.load config method. So now let's close down Vizdoom. We don't need that. We can end that task. So if we go and run this now, you can see completely different game environment, right? This is completely different to what we had previously. Before we had the slightly different environment, and it's a different shape as well. So keep that in mind. Now what we can do is we can go and run this action. This is going to do something. We can get our state, we can get game variables, so on and so forth. What we can go on ahead and do is run our loop as we did before and see how that actually performs. We can see that our agent is able to shoot. We've got monsters coming at him, and eventually he'll die because he runs out of ammo and there's just people coming at him, and right now he's not shooting anyone all that effectively, right? So we want to be able to train our agent in this particular case to shoot all the different monsters that are coming at him. Okay, so you sort of get the idea of how this is actually going to play out, right? So that is our new map now loaded. Let me expand that again. Don't know why I closed that one, but we don't need that. So what we want to do first up is get this into a similar shape to what we had inside of our Vizdoom basic environment. Because right now you can see that the shape of the actual game is significantly larger. This is just because of the parameters that we've got inside of our configuration. So what we can actually do is we can actually fix that. So let's actually close this. I'm just going to close Vizdoom and we are going to reshape this. So if we go into YouTube and then where is it? Vizdoom, GitHub, Vizdoom. And if we go into our scenarios, let's open up our basic one. I'm just going to zoom out of this a little bit. And let's open up our, what are we doing? We're doing defend the center. Okay. So here's where we're going to do a little bit of magic. So right now, the screen resolution, you can see it's definitely different, right? So over here, our line 12 for our basic environment, we've got a screen resolution of 320 pixels by 240 pixels. We're actually going to copy that over and use that for defend the center as well. So that means we're going to have frames of the exact same size. So rather than having a significant larger or different shaped game observation coming back, we're going to have the same game observation coming back now. So all I've done is I've copied this, so the screen resolution parameter from the basic.config, and I've pasted it over to here. So the screen resolution is the same for defend the center. Now, if we go and create our environment, so let's go and start it up again. So if we go and load this, you can see it's already much smaller. And this is more like what we had previously. So rather than having the huge frame, we've got it cut down. So now if we go and run it, you can see it's just a much smaller game environment, which if you wanted to train on a larger game environment, it's perfectly fine. You could definitely go and do that and just resize the frame, but it just makes it a lot faster when it comes to actually processing your game. So right now, we're pretty good. This is going to be how we actually go and train our model. Now, the cool thing is that we've pretty much already got the workflow now set up. I'm just going to close this frame down. We've pretty much already got the framework set up to go on ahead and train this. The only thing that we need to do is copy this, scroll on down, and paste it over here. And this is in our Vizdoom gym class. So we don't need to do very much else. We just need to paste it into there and we should kind of be good to go. Let's just double check our buttons. So remember, we had 3 buttons configured in the previous environment. Let's just double check it is still the same case inside of this scenario. What are we doing? Defend the center. Yep, we've got 3 buttons. So turn left, turn right, attack. We've now got 2 game variables. So we've got ammo and we've also got health. We're not going to do too much with those for now, so that's perfectly fine. Okay, so we can save this. And if we go and run at this Vizdoom environment, what's happened? All right, we've got to go and import our dependencies. So let's run that. That's perfectly fine. We don't have a game running at the moment, so we can delete that. Okay, so that looks fine. So all we've gone and done is we've gone and changed. Let me zoom out so you can see it. All we've gone and done is we've gone and changed this line here. So this is going to give us a different environment, or it's going to load up a different config when we actually go and instantiate our Vizdoom gym environment. Now you could actually set this up so that it's a parameter inside of your class. Perfectly fine. Okay, that is working. Let's go and test it out. It starts up. We reset. Let's view our game state inside of matplotlib. Let's not delete it yet. So if we go and import our environment checker, looks like we've got no issues there. You go to matplotlib, got no issues there either. Cool. This looks like it's all ready to go. So we can actually close down this environment. Say env.close. And then let's go through our stable baselines walkthrough. So we're going to set up our callback. And this time, rather than saving it inside of our train basic folder, we're going to save it in a slightly different folder. So let's call it train defend and log defend. So this basically means we aren't going to overwrite the models that we've trained for our basic agent. We're going to have it inside of a separate folder. We're going to set up these new checkpoint directories and log directories, set up our callback by running that line. So we're going to run this import. We're going to set up our new instance. And remember, we're going to have a non-rendered environment when we're going to go train, because it's going to train a whole heap faster. So we set that up. And this time, should we increase end steps? Yeah, so because this environment is slightly more complex, let's give it a bit more time to actually learn about the environment. So we're going to increase this from 2048 to 4096, and we're going to leave our learning rate the same for now. So we shouldn't need to change that. So let's actually start up with those parameters. If you've got a really complex environment or a long running environment, so say you're tried and trained for Dota or something, or CSGO, you'd be increasing that end steps parameter pretty significantly and probably dropping the learning rate as well, so that it learns a little bit slower. So there's so many nuances in those games, so you're going to need to give it time to actually learn. Okay, but in that particular case, that is fine. It doesn't look like we've got any errors there. We're also going to need to train for significantly longer. So right now we've got it set to 100,000. Is that going to be enough? Let's leave it at 100,000 for now, and then we'll see how performance actually looks like. So if we go and run this, you can see it's logging to logs, log defend, PPO1. If we go and take a look at our logs, D, YouTube, where are we? Vizdoom, logs, log defend now. We've still got a PPO1 folder. So let's go and start up TensorBoard in that folder. So I'm going to cancel this. I'm going to stop the server. I'm going to go out of this. Let me just bring this up. So I'm going to go out of logs basic. I'm going to go into logs defend. So that's CD log defend. So that's going to go into that folder. And then I can go into CD PPO1, which is going to be our latest logging file, and then start up TensorBoard against TensorBoard -- logdir equals dot. So that's running. And if we go and refresh TensorBoard, how are we looking here? Nothing run yet. Okay, so this might take a little bit of time because it's going through and learning that particular environment and running through each one of those steps or each one of those game frames. So this might take a little bit of time for you to get your first result from stable baseline. So let's give that a sec, and then we'll be able to see model performance.
Moments later.
Okay, so this is model performance as it's training. So we can see that right now after, I don't know, let's take a look. After about 24,576 time steps, we have an episode reward mean of 3.03 and then average episode length of about 108 episodes or frames in this particular case. So we are looking pretty good. So we can see that we've got an upward trend. Our episode length mean is increasing, which is a good sign in this particular case, right? Because we want to last as long as possible versus the previous scenario where the only goal was to shoot the monster. Here, we want our agent to be able to last for as long as possible and try to shoot down as many monsters as possible. I mean, we know that eventually he's going to die because he's got a fixed amount of ammo, but that is still perfectly okay. So in this particular case, we want to see both of these increase for this game. We can see that our agent or our current policy is diverging from the historical one, which is okay. We're still clipping a little bit, perfectly fine. Our explain variance, these things don't go down, go away. How do we refresh this? So our explain variance is increasing. So this means that our critic is getting better at predicting the future sum of returns. We also have our policy gradient loss decreasing and our value loss increasing as well. So this means that it's probably finding advantage and it's being able to capitalize that by increasing the probability of taking those actions which are doing so. So we want to see this keep increasing to as high as possible, and we want to see this keep increasing as high as possible. But we'll let that train, and then we'll come back and take a look before we go back to Bob with our montage.
5 minutes later.
Okay, that is the model finished training. So you can see we've gone for the full 100,000 total time steps. So you can see that there. So our final episode length was about 189 steps. We had an average episode reward of about 10.7. Frames per second was about 53, whole bunch of other information here. If we take a look at the TensorFlow log, so you can see that the length definitely increased upwards, and we eventually ended up with a pretty good model, or at least I think based on these metrics. Our reward mean increased. We were getting some divergence between the old and the new policies. What else? Explained variance was hitting 93.2. So this means that our critic definitely understood the variances in how we were generating rewards, or was accurately able to predict what our returns were likely to be based on the current game observation and action. So again, if we wanted to go ahead and try these out, We definitely can. So we can run our evaluate policy method. And let's import our 50,000 model, for example, in this particular case, because we'll save the 100,000 for the montage. So let's go on ahead. What we now need to do is import the train defend model though. So it's not basic anymore. So if we load that, create our environment, go on ahead and test it out. So you can see it's already performing way better. It's actively shooting agents, shooting monsters. Look at that. Insane. Not too bad, right? So again, if we wanted to go and test this out, we can go on ahead and stop it in this case because you sort of get the idea. We can go and run it using this framework, which slows it down a little bit. But you can see it's still kind of wasting ammo on stuff that might not potentially be there. Like that was a wasted shot. That's a wasted shot. That's a wasted shot. So it could definitely still be better. You can definitely see it's performing significantly better than our baseline agent. All right, let's take a look at our montage. So now we're taking a look at the model trained for the defend environment for about 10k steps. So it looks like he just killed one of the pink monsters and he's randomly sort of shooting around. Not all too accurate at this stage, but as we progress, we'll definitely see some improvement. And as you can see, all the monsters are running towards him now, and you'll start to see health drop off pretty rapidly, and the game will end. And now we have the model trained for 20k steps. Looks like he's scoring a couple of hits pretty early on. You can see he's starting to accurately identify that he needs to be shooting the enemies. Oh, he's got that guy there. Progressively getting a little bit better. As you're starting to see these red flashes, what's basically happening is he's losing health quite rapidly. Now, because he's got a fixed amount of ammo, that will eventually be his demise. 50k steps. Early shot, looks like he's managed to take out that dude, and you can see he's definitely way more accurate now. He's progressively taking out enemies, he's spinning around, so he's at least got a little bit of a strategy to actually go out and win. And as I said that, he just starts randomly shooting at stuff, but look at this, bang, bang, actively taking them out. So you can see that he's definitely progressed from our initial 10k model. Now we'll let this run and see how he eventually performs. $80k steps, and my dude is a Terminator. You can see he's actively taking out enemies, spinning around, has lost 0% health. As that pink monster is heading towards him, he's taking him out. So you can see that this reinforcement learning agent has learned quite a fair bit about what is actually influencing the reward. In this particular case, taking out the monsters before they start to degrade your health. I think in this particular episode, Doom Guy actually manages to go all the way to the end, and the only thing which eventually catches him up is the fact that he runs out of bullets, so he can't actually defend himself anymore. You can see he's actively spinning around, taking out different enemies. And yeah, this is 100k steps. So again, not a huge improvement over 80k, but definitely has managed to converge to an optimal solution. Our reinforcement learning agent has learned that it needs to be taking out the monsters in order to win. And yet again, here's a full speed run, just so you can see how quick this is actually running.
So, thoughts? Yeah, that was awesome, but Doom Guy kept dying at the end. That's kind of inevitable in this case. He's got a fixed amount of ammo, so eventually the monsters are gonna get him. Got it. You mentioned before that there was some stuff that you could do to train agents to play harder games. You got any examples of that? Well, there's two techniques that I found work pretty well. The first one is reward shaping, which sort of helps ease the sparse reward problem. Let me give you an example of this. Now, imagine you need to navigate through a maze and you only get a reward once you finish. Well, the agent is going to find it tough to learn how to navigate through without constant feedback. One way we can help this though is to use reward shaping. So rather than giving just a reward for getting to the end of the maze, we can provide incremental feedback and incremental reward for completing sub-goals. For in this case, just getting closer to the end of the maze, not just completing. The second technique that we can use is something called curriculum learning. This is where we train the agent in an easier environment and then progressively increase the complexity and/or difficulty so the agent learns to play in a real-world scenario. For Doom, we can set this using the difficulty setting in the game config. Nice. Now, not to be pushy, but are you gonna give it a go? Yeah, all right, let's do it.
First things first, the sparse reward problem. I talked a little bit about the maze example, but how does this apply to Doom? Well, the next problem that we're going to be taking a look at is the deadly corridor level. In this level, the agent needs to get to the end of the corridor to get some armor. If he does this, then he gets 1,000 points as a reward. He also gets a point for every step he takes towards the armor, which reflects an additional potential 1,312 possible points. The problem is that without shooting the monsters in the corridor first, he'll die before he gets anywhere near close to the armor. The reward function doesn't take this into account, and in some senses has sparse rewards for this part of the problem function. So how do we solve this? Well, first things first, we can use reward shaping to incentivize our agent to kill the monsters. We can add rewards for killing each monster, preserving our own health, and having accurate shots. Second, we can use curriculum learning to help the agent learn. Rather than making the monsters hyper aggressive, we can make them a little bit softer. This means that the agent will have a chance to kill some monsters and learn that this yields a positive reward. Once it's running along the right trajectory, we can increase the difficulty and keep training. This should hopefully be enough to teach our agent to play. Alrighty. We're in the end game now. So Bob's asked us how we might go about dealing with harder environments. There's two key things that we can do to effectively deal with harder environments that our agent is struggling to learn in. These are through reward shaping, and the other one that I found most effective is curriculum learning. Now, in order to do this, we actually need a harder environment because so far we've smashed through basic and we've smashed through defend center. So where is our difficult environment? Well, the one that we're actually going to be using is called Deadly Corridor. So the purpose of this scenario is to teach the agent to navigate towards his fundamental goal, the vest, and make sure he survives at the same time. The map is a corridor with shooting monsters on both sides. A green vest is placed at the opposite end of the corridor. The reward is proportional, negative or positive, to the change in distance. If you get closer to the vest, you get more points. If you don't get closer to it, you get less points. So if you get close to it, that's going to be a good thing. Now, if the player ignores monsters on the sides and runs straight for the vest, he'll be killed somewhere along the way. Now, the way that they ensure this, or they enforce this, is by setting the monster skill really high, which is this Doom skill equal to 5. Now, we can actually tweak that to make our environment a little bit easier. So that is how we're going to go on ahead and perform curriculum learning, which is that increasing type difficulty. So what are some other penalties? So we've got 5 available buttons. So left turn, right turn, move left, move right, and shoot. We've got a timeout of 4,200. I don't know if that's seconds or frames. I'll have to dig into that a little bit. With death penalty is 100 and our doom skill is 5. Now we can actually dig into this a little bit more. So what I'm going to want to do, let me actually show you the baseline environment to begin with. So what we can do is we can duplicate our defend center. Yeah, let's duplicate our defend center notebook to keep it nice and separate. That's the copy. So let's rename that. We are going to call it, what are we going to call it? Deadly Corridor dash tutorial. Cool. Okay, and then we'll open that one up. Okay, so what we're going to do is first up, we're going to load up the Deadly Corridor scenario. So let's grab, just going to go into there. So YouTube, Vizdoom, where our current environment is. And then if we go into GitHub, Vizdoom, scenarios. All right, this is the one that we want, Deadly Corridor. So this one here. All right, so you can see deadly corridor.config. That's the environment that we actually want to go on ahead and load up, or the scenario that we want to load up. I'm just going to copy this, close that. And remember, it's reasonably straightforward to change levels inside of our flow. So all we need to do is change the level that we're going to be loading into our Doom game. So if I paste that in there, so Deadly Corridor, this should effectively load up our new level. And I'm just going to close the existing Doom game. So if we go and load this one, all right, cool. So you can start to see that here, right? It never seems to want to drag. All right, that's a bit better. No, okay, it's not going to expand. But you can see that we've got a monster there, we've got a monster there. Now, if we run straight forward, we're going to die because these monsters are set to difficulty 5 or Doom skill 5, which is the hardest possible difficulty. And the only real reward that we're getting is heading straight towards the vest, which is right at the end there. You can't really see it at the moment, but when I make it bigger, you'll be able to see it. So if we bang straight forward to that, we're going to die straight away. That's just the way the game is set up. So if we actually take a look, actually, what am I doing? We don't need to take a look at that. If we run straight towards it, we're going to die. No questions asked. Now, again, that's because of that Doom skill setting. So if we go into there, so GitHub, Vizdoom, and then go into scenarios and what is it? Deadly Corridor. You can see Doom skill is set to 5, which is the hard, I think that's the highest you can actually go. So if we try to run straight forward, we're going to die. Now we also have 1, 2, 3, 4, 5, 6, 7 different moves that we can actually make. So move left, move right, move backward, forward, and attack. So we also need to change the action space that we're going to be working with. And what we're also going to be doing is adding some additional game parameters down here when it comes to actually performing our reward shaping. So we'll come back to that in a second. So for now, let's actually just test this out and see what it looks like. So remember, we have to change our action space. So we've got 7 different actions. So let me show you what that looks like. So we've got just an identity matrix. So there's a 1 in each consequent position. So 1, 1, 1, 1, so on and so forth. And then what we can do is get our game state, get our game variables. So right now we've only got 1 variable. And then we can loop through our different environments, or like actually going ahead and test it out. So if we do this, you can see we're dead. Right? You can see our health dropping. Let me make this a bit bigger. So health is at 4%, we're dead. That's the vest right there, that weird thing over here. You can see we're running forward, health's at 40%, we're dead. Got shot again, dead. 28%, we're dead. It's frame skipping as well at the moment. All right, we killed someone, so you can see that we probably should have got a reward. But again, the reward's pretty low at the moment, and it doesn't really highly incentivize our agent for killing them. So what is the reward for killing a monster right now? Death penalty. See, we don't even get any reward for killing a monster at the moment. So how would our agent actually be able to know that it should kill these monsters before going ahead? So that's really where reward shaping is going to come in and help us out. So we're going to fix that up, or at least tweak it. Okay, so we know how to actually play with our environment now. So that's all well and good. Now what do we need to do? So we are going to close this game, and we're going to go on ahead and configure our environment. Now, the first thing that I want to do is I want to get some additional game variables. Now, this is somewhere in the documentation, but I can't remember where I found it. So if I can find a link to that, I'm going to give it back to, or send it to you. So there's 3 additional parameters that I want to bring in here. So these are damage taken, hit count, so that's how many times we've gone and hit a monster, and then I want to bring in selected weapon ammo. So the reason that I'm going to bring in those specific ones is we're going to use damage taken to negatively reward our agent for getting hit by the different monsters. We're going to positively reinforce our agent for actually hitting a monster and killing a monster. And we're also going to negatively reinforce our agent for wasting shots effectively. So effectively, if you actually go and hit a monster, that's going to give you a high reward. If you go and use a bullet, we want that to be negative, right? So you don't just waste bullets. So ideally, those should level off against each other. And we're going to weight each one of them so that we effectively get, I guess, the right type of reward. Okay, now in order to get these parameters from our game environment, what we need to do is go on ahead and change our config. So if we go into YouTube and then, or we go into wherever you've gone and cloned the GitHub repo. So I'm going to open that up, scenarios, and if we go into Deadly Corridor, we need to paste those parameters in. So I'm just going to copy that. And this is without any commas. So you just basically paste it in. So it's a space, they're space separated. So I've got health, I've got damage underscore taken, I've got hit count, and I've got selected underscore weapon underscore ammo. So now our game variables should actually include each one of these. So health, damage taken, hit count, selected underscore weapon ammo. Okay, so that is the first thing. Now, what I'm also going to do is while we're here, I'm actually going to make a copy of this and paste it in. So you can see it. Let me zoom in so you can see that a little bit better. So right now, our Deadly Corridor skill is still set to 5. So I'm going to set it down to 1. So I'm going to call this file S1. And I'm actually going to make 5 copies of this. So 1, 2, 3, 4. That's 5. All right. And in each one of these, I'm going to sequentially increase the difficulty that our agent encounters. And this is what we're going to use to actually perform our curriculum learning. So in S1, I'm going to set Doom skill to 1, so make it super easy. Let me open all of these. Let's actually rename them first. So this is going to be S2. This is going to be this is probably super small on your screen right now if you're watching this on your phone. Let me make it a bit bigger. Okay, so this is going to be S3. This is going to be S4. And this is going to be S5. So effectively the full level of difficulty. Okay, so now what I'm going to do is I'm going to open all of these up inside of VS Code. So we're going to tweak them a little. Okay, so which one are we on right now? So let's go to S1. So we've set Doom skill to 1 there, and we've got our new parameters. Let's go to S5. So we're going to leave, so on S5, that's effectively max difficulty. So we're going to leave the Doom skill as 5 there. On S2, we're going to set Doom skill level to 2. On S4, we're going to set the Doom skill level to 4. And where's S3? Let's just close one. All right, close that. Don't save. S3. All right, so on S3, we're going to set it to 3. And save that. So S3 has a Doom skill of 3. S5 has a Doom skill of 5. S2, let me reorder these so it looks a little bit more congruent. There we go, that's better. All right, so S2 has a skill of 2. S3 has a skill of 3. S4 has a skill of 4. And S5 has a skill of 5. And if I go and open up S1 as well, S1's got a skill of 1. All right, cool. So that is all of our different configs now ready for our curriculum learning. So the nice thing about this is that all we're going to need to do is spin up a new environment with the slightly different config, and we're going to be able to use that then and there. Okay. Now, in order to make that a little bit easier, what we're also going to do is we're actually going to create a new parameter inside of our Vizdoom class. And inside of init, I'm just going to create a keyword parameter called config. And I'm going to set that, initially, I'm just going to set it to the S1 config. So if we go to this, I'm just going to copy that over. Paste that there. And then inside of this line here, so self.game.loadConfig, we're just going to change that to be config. So what's effectively going to happen is we're now going to be able to pass the different configurations directly to our environment. So we don't need to come back here and change the class. We can just pass that through to make our lives a little bit easier. Okay, so what else do we need to do? So that is now... So we've gone and got ourselves set up for curriculum learning. Now let me also show you S1, right? So if we go to deadly_corridor_S1, that should be our really easy level. So let's set the default one to S1 over here. This should be really easy, right? So we shouldn't see our monsters going like ham and trying to kill us super quickly. Right, so we're lasting a lot longer. Let me show you this. Even though we're taking random actions, we're lasting way longer, right? Still dying, but lasting longer. You've actually got time to shoot the different monsters if you want to. Like, if this was on max difficulty, he'd be dead by now. So this is going to give our agent time to actually learn that he should be shooting the monsters. So right now, shooting a wall. So great, right? Okay, we can stop that. We get the idea. And if we go to S2, you'll see increasing difficulty again. So if I change that to S2, right, so getting a little bit harder. You know what? Let's comment out this so we actually see the real reward. So let's go back to S1. So all I've just commented out is this line here, which is printing out the reward per frame. So that's limiting us from actually seeing the total reward per episode. All right, so nothing's really happening there. He's lasting pretty long. All right, so he's managed to shoot both monsters. So in this particular case, if we were training our agent, he would have just got whatever the hit count value multiplied by the weight for killing a monster is. So he's going to learn that that is a positive action. But right now, he doesn't really know. I mean, there's no real smarts on here. I'm only going to wait for one game because this is taking way too long. And he's not really dying. Hopefully he gets into this area here because there's a monster with a... Oh, he's managed to kill that monster. All right, so you can see there that our result is 336. So that's for the first... That is with difficulty 1. And now if we go and set difficulty to 2... So remember, let's just write that down. So for S1, we had a difficulty... we had a reward of 336. Now, if we go and do S2, and again, I'm not doing this perfectly here because ideally you'd want to run it over a set of episodes. So let's see what our reward is over here for S2. All right, so that you can see, all right, so we only got minus 29. So again, you can see it's already becoming harder. So for level 2, what was our reward? It was minus 29. Let's do level 3 or skill 3. Right, so minus 20. But you can see it's progressively becoming harder. And what I'm showing you here is just the impact of increasing difficulty. So if we go to S4 now, ideally this should be lower again. Right, so he's dying pretty quickly. All right, so minus 95. And again, these are all a little bit random, but you can see he's definitely not achieving 336. S4, it's minus 95. Oh, he got 52 that time. All right, let's do S5. Right, so minus 98. So he's not getting anywhere close to what he got in S1, minus 99. Right, so you can progressively see that it's becoming harder and harder for the agent to learn and to get positive rewards. So that is what we're going to effectively incentivize using curriculum learning. So we're going to make it easier for him to learn what yields a positive reward, and then we're going to increase that difficulty. So he's already got an idea of what to do. He just needs to go and apply it in a slightly more difficult environment. Okay, cool, but that is all well and good. So we know how to go on ahead and apply curriculum learning. I'm going to show you how to actually do it properly in a sec, or pseudo properly. What we now need to do is fix up our reward function and perform our reward shaping. So first things first, we need to change our action space. Remember, we've got 7 actions now. So in this line, self.action underscore space, we're going to set that equal to discrete 7, because remember, we've got 7 different actions: move forward, move back, left, right, turn backwards, turn left, whatever was in the config file. You know. All right. And then in this line here, so action, let me actually show you. I feel bad saying, you know, go into D, drive, YouTube, Vizdoom, GitHub, Vizdoom, scenarios, Deadly Corridor. I always remember when I used to watch tutorials and the tutor will go, you know, and it's like, no, I don't know. All right, so here I'm showing you. So these are the different actions: move left, move right, attack, move forward, move backward, turn left, turn right. So these are going to be the 7 actions that you're actually able to work with. Okay, so what's happening here? So we've gone and updated our action space, and this means that when we go and sample our actions, we're going to see that we've got 7 discrete actions. We went and updated our identity matrix over here. Now what we need to do is we need to create... Oh, actually, let's also take a look at our game variables as well. So game.getState .game variables. What was it again? Yeah, it should be game variables. Have we closed our game? Let's just reinitialize our game. I'm just thinking, yep, let's reinitialize that. Okay, so you can see that we've got all of our game variables down here. So I've just got state.game variables. The first value, these are all going to map through to what we've got. I wish I'd stop closing that config. YouTube, Vizdoom, GitHub, Vizdoom, scenarios. And if we go into here, let me bring this over here and this on this side. Okay, so what are we looking at here? So this first value is going to be health. This second value is going to be damage taken. So how much we've actually been hit. The third value is going to be the hit count. So this is how many times we've hit a monster. So it's going to be 1, 2, 3, 4, so on and so forth. There's max of 6 monsters, but they do respawn. And then our selected weapon ammo is how much ammo we've effectively got on our gun or whatever it is that we're shooting. Cool. So what are we going to do? We're actually going to extract each one of these, and we are going to create a set of properties in our class to hold them. So let's go on ahead and do this first up. Okay, so we are going to create some, let's just find our init section. So, all right, so we're going down here, we're going to create, let's just copy this just so we know what order they are. Okay, so let's create our properties. Okay, so I've created some initial game variables. So this should be self.damage taken. So inside of the init method, I've written self.damage underscore taken, and I've set that equal to 0. Self.hit underscore count. This should just be, let's just make that. So self.hit count, that's fine. And we set that equal to 0. And then we've also set self.selected underscore weapon underscore ammo, and we've set that equal to 60. So now what we need to do is extract these. And what we actually want is we want the change, because what we're going to get back from the game is the current value at a point in time. This isn't the change that we're getting. This is the current value. So if we've taken damage in one frame and we've taken damage in another frame, it's going to be the cumulative value. Now we want a reward based on the deltas. So we actually need to calculate the difference each and every time. And so why we've created these is we're going to store the previous state's value inside of this and update it each time to be able to calculate our change. Okay, so on that note, let's actually start doing that. So inside of this section here, so if self.game.getState, so right over here inside of our step function, we are going to define or perform our reward shaping. So let's get started. Okay, so before I go any further, let's actually take a quick break and see what I've actually gone and written here. So I've written inside of if self.get inside of if self.game.getState. So right down here, I've created 2 additional lines of code. Ignore this for now. Let's delete that. So I've written game_variables equals self.game.get_state. And then inside of parentheses, so this is going to get our state, .game_variables. And then we're unpacking each one of those values. So let's actually take a look at what this would do. So do we have game? We've got our game variables up here, right? So what we're effectively doing is, let me copy this. So health, comma, damage taken, comma, hit count, comma, ammo. So we're unpacking these variables so that we've got them each stored in its individual variable. So now if we take health, we've got health, which is equal to 100, damage taken, that's 0, hit count, that's 0, and then ammo equals -1. Cool. So we're just unpacking those values and grabbing them into individual variables so we can calculate our delta, which is this over here. Now we can actually get rid of this ammo line here. We're not going to use that again, so we can delete that. Okay, now what we're going to do is we are going to calculate the delta. So the change in, I don't think we're going to use health. We're not going to use health. We're going to use damage taken. So we're going to use the damage taken value, the hit count value, the ammo. So we're going to calculate the change in damage from the previous frame to the current frame. So let's go ahead and do this, and then we'll put together our final reward function and we should be done. Okay, so those are our different reward parameters now created. So I've gone, let me calculate that, calculate reward deltas. So delta is just change, right? So what did it change from the previous frame to the current frame? So I've gone and written 6 lines of code. So let's take a look. So I've written damage_taken_delta equals minus damage taken plus self.damage taken. So this means that if we've taken more damage, oh, well, let's actually think this through. So if, let's say, for example, in this particular, or in the previous frame, what we'd taken is 10 damage points for it. So 10 DP. Then in the current frame, we've now taken 20. Let's add some comments, right? Then what this is effectively going to do is it's going to say, so minus 20 plus 10, that means that our reward is going to be -10. So that is disincentivizing us from actually taking damage. Kind of makes sense, right? So damage is going to go up, so it's going to be an incrementing value. All right, hit count. So let's just walk through this example again. So let's say our hit count, let's say we haven't hit any monsters in the first round, so that's set to 0. Then we go and hit, let me actually make this a bit bigger so you can see it. Then we go and hit 1 monster in the second frame. So this means that we are going to have a hit count of 1 and then -0, which is hit count minus self.hit count, because that's the previous. This means we are going to have a reward of 1. And again, we're going to weight these. So we're going to have specific weighting parameters. Cool, makes sense. All right, so ammo, which is this line over here. So let's say our ammo starts out at 60, which I think it does for the pistol. So ammo starts out at 60, we then take a shot. So it goes down to 59. This means that we are now going to have 59 minus 60, which means we are going to have a reward of -1 because we are disincentivizing ourselves from taking shots that miss. Now, keep in mind that if we hit a monster, we're effectively going to get a +1 and then we're going to get a -1 for ammo. So they're going to negate each other out. So it's perfectly fine. All right, cool. So that sort of explains the logic for those, right? So we're just calculating the change. Let's actually take a look at how we've done it. So I've written damage_taken_delta equals negative damage_taken plus self.damage taken. So current damage, or minus current damage plus the existing damage we had from previous frames. And then we're going and resetting the property that we initialize right up here. So self.damage_taken equals damage taken. Doing the same for hit count. So hit count_delta equals hit count minus self.hit count. So current hit count minus what we had in the previous frames. Then we're going and resetting our property. So self.hitCount equals the current value. Ammo delta, so ammo underscore delta equals ammo minus self.ammo. So the current ammo utilized minus, or the current ammo available minus the ammo that was available in the previous frame. And then we're going and resetting our value. Now what we need to do is just pack this all together into our reward function. So I'm going to type in reward equals. Now what we want to do is we still want to utilize that movement reward, because right now there is a reward for moving around or moving within the game. So we're still going to use that. So we're just going to call this movement reward. And we're going to set our initial reward value here, reward equals 0, so that we've at least got it initialized, right? So then inside of here, we're going to reset it and we're going to weight this. Now, I've gone through a little bit of tweaking to find out which of these parameters work well. You might need to play around if you're dealing with different games, but these weights actually work well. So we're going to bring in our movement reward, plus our damage taken delta, plus our hit count delta, plus our ammo delta. Now, what were our parameters? So for hit count delta, I multiplied that by 200. So this basically means we want to really incentivize someone for hitting a monster. Our damage taken delta, we are going to set that to 10. So we're taking the change in damage and we're multiplying it by 10. And our ammo delta, I set that to 5. So in total, our reward is now reflected as, let's go back to this. It's reflected as minus 100 for dying completely. That's perfectly fine. Plus whatever movement we make towards the vest, minus whatever movement we make against or away from the vest, plus all of our specific values. So that movement reward is encapsulating all of this stuff here. Then we're adding in our own special stuff, which is our reward shaping. So we're going to be adding an additional 10 points multiplied by any damage taken. We're going to be adding, or this is effectively subtracting. We're going to be adding an additional 200 points for every monster killed. And we're going to be subtracting 5 points for every time we take a shot. So this disincentivizes us from taking shots that aren't going to be hitting monsters, right? Or should effectively do that. Okay, and that reward value should be feeding back down to here. So I think that is our reward shaping now done. Let me double check. That looks good. Okay. Health, and I don't think we're actually using this health parameter. We could actually take that out of our configuration. So let's run that. Let's see if this all works. Okay, so no errors there. So we've gone and added all of our reward shaping over here. So let's just quickly go through what we've actually gone and done here first. Let me zoom out so you can see it all before we test it out. So we've first up gone and created our new reward parameters, so damage taken, hit count, and the selected weapon ammo. We have then gone and renamed our existing reward value to movement reward, and we've initialized a value or a variable reward and set that equal to 0, so that when we go and reset it inside of our if statement, we don't get uninitialized errors. All right, then what we've gone and done is we've gone and written all of this, which is our reward shaping. So we've gone and extracted our game variables. We've gone and calculated our deltas and reset our properties. We've then gone and created a new reward function, which is a weighted sum of our movement reward, our damage taken delta, our hit count delta, and our ammo delta. And we've multiplied them by specific weights to be able to influence how our agent actually operates. Cool. I think that's all that we need to do. So if we go and run this, and go and initialize our environment, no issues there. So you can see they're going and spinning up. Let's just go and kill those off. So end task, end task. And then let's go and test out this environment. So if we go and reinitialize it, so you can see we've got our Doom guy. Close that, we don't need that anymore, close that. All right, so that's our environment there. If we go and import our baseline environment checker, all right, we've got some errors. What's happening? Vizdoom object has no attribute ammo. Okay, so what's happened there? So ammo delta. So ammo, we are unpacking ammo from here. 0, 1, 2, 3. Hold on, what's the error? Vizdoom object has no attribute ammo, but we've unpacked ammo. Oh, because we've gone, sorry, we're looking at the property here. So we've actually gone and named our property not ammo. We've actually gone and named it self.selected underscore weapon ammo. Let's just call it ammo to make our lives easier. All right, so that should sort that out. So if we go and run that again, no issues when we go and reset, run it through our baseline checker. Okay, no errors there. So that is all looking good. So if we go and take a look at our state, no issues there. Can minimize that. And then if we go and close it, we're closing successfully. So we can go and close this one as well. Okay, so that is looking good, guys. So we've managed to successfully create our new environment. We have gone and updated the config so we can actually pass the config in this time. And what else have we done? We've gone and reshaped our reward. We've gone and updated all of our different configs. So we've actually got a number that we can use for our curriculum learning. So let's actually take a look at how we might go and apply curriculum learning now. So we're going to change this, train our model using curriculum. And there are other ways to apply a curriculum, guys. This is just the way that I found is easiest to implement. You could definitely try other stuff. Okay, so in order to do this, we are going to import PPO as per usual. We are going to specify our config explicitly. So let's go and grab, this is just good to remember what config you're actually using. So I'm just going to grab this. And I'm going to paste it down here. And what we're effectively going to do now is, let me walk you through. So we're going to load up our first environment, which is this. We can then go and run our model, train it for X number of time steps. We can then go and change our environment. So we go and update this to be S2, for example. We pass through that new environment to our model policy or our PPO policy over here and then train for longer. But for now, what we're going to do is we're going to start off easy and we're going to use it on the S1 environment, so the skill level 1. And this should at least give our agent a chance to learn in an easy to learn environment. So we're going to leave this the same for now. We might drop the learning rate. No, we're going to keep the learning rate the same. All right, let's run this. So that's all well and good. We have end steps equal to 4096, same as what we had before. And then we have a model. Actually, wait, hold on. Ooh, that was close. So what we need to do is we need to change our checkpoint directory and our log directory. So this should be going into corridor. And then this should be corridor as well. Perfect, that's much better. So we are now going to have 2 new folders when we kick this off inside of Vizdoom. Train, we're going to have one called train corridor. And we're going to have log corridor down there. Okay, so let's run this, run our PPO. We are going to set up our new environment, create our PPO model, and train for 1,000 time steps. So let's kick that off. Okay, so we can see that we're logging to log underscore corridor and then PPO1. So as per usual, let's start TensorBoard in that directory. I'm going to close down the server. So we need to get out of PPO1. Get out of log defend, and we are going to go into log corridor. And then if we take a look at what we've got in there, we've got PPO1, so we can go into there. So CD PPO1. And then we want to start TensorBoard. So TensorBoard equals dash log dir equals dot. Cool. So it's running on localhost 6006. Good to go. Let's refresh it. Okay, so it looks like it's still training. All right, so let's give that some time and we should effectively be able to see the results of our model pretty soon. So I'll come back once at least the first initial instance has gone and logged to TensorBoard. But this is good progress, guys.
11 minutes later.
Alrighty, guys. So I ended up training and the results were pretty bad. Now, when it comes to actually going on ahead and training using reinforcement learning, things aren't necessarily always all that stable. And what I actually noticed was that when I trained it using those existing hyperparameters, the model would work and then there'd be a sharp drop off. So in the interest of helping you effectively get successful results, I wanted to share a little bit about what I learned, at least going through that initial first phase. Now, this actually took a couple of days. I dug into it a lot more to see what it was that was happening. Now, there were a couple of things that I changed that definitely improved my results. I've also got a model that is performing really, really well. So I'll actually share that end model with you. Now, that being said, when I went to try to repeat some of these processes, it wasn't necessarily always all that stable. So just take this with a grain of salt. You might still need to do a little bit more tuning to ideally get that final end model, which is absolutely perfect. Okay, so let me share with you what I ended up changing and some of the findings that I actually found. So first things first, I went and set the self.ammo variable to 52. It didn't start out at 60. I think it actually started out at 52. The other thing that I noticed, I'll actually talk about this a little bit later, but that was the main change. The other thing that I was also thinking is that this should potentially be replicated inside of the def reset method. So that effectively resets our initial properties. I didn't do this, but I think that that is actually best practice. That being said, it's just going to be a continuing value. So it will calculate the delta. The next main thing that I changed was the hyperparameters. So initially, we kicked off our training with a learning rate of 0.0001, so 0001, and we had the end steps parameter set to 4096. Now, let me explain what end steps actually is, because I got a better understanding of it. So this is actually the batch size that you're going to be passing through to the actor and critic neural network. So it's effectively how many time frames you're going to be passing in total as part of one training run. So the larger this is, the more information we're going to be passing per epoch. Now, what I noticed after doing a bunch of hyperparameter tuning was that there was a bit of a relationship between that end steps value and the clip range. So just increasing that by you're probably thinking, oh, Nick, just increase it, it's going to yield better results. That wasn't necessarily always the case. Let me zoom in on this. Why is this not zooming? There we go. That's a bit better. Okay. So what I actually found was that when end steps was high, you wanted to have a lower clip range, and GAE lambda, which is effectively a smoothing parameter, didn't really influence it as much. Now, when you had a lower end steps value, you definitely needed to have a significantly higher clip range if you weren't going to change your GAE lambda, and then vice versa. So if we had a relatively low end steps number, so a small batch size, then we could set our clip range to a little bit lower, and we could have GAE lambda a little bit lower. So the way I actually did this was through a library called Optuna. I originally had this as part of this tutorial and took it out because I thought it wasn't that important. Turns out it is relatively important, and I'll share some information about that inside of the description below. So what I actually ended up doing is I took parameters which more closely approximated what you're seeing here. So end steps, gamma, the learning rate, clip range, and GAE lambda. So that's what I ended up doing here. So I changed this parameter. So the new training line, or the new model initiation, looked like this. So we had PPO, still our CNN policy, environment, tensor board log directory, verbose equals 1. And this is where the changes came. So I set the learning rate to 0.00001, set end steps to 8,192. This should be a function of 1024. So it's based on your mini batch size. So if your mini batch size is 64, which I think is the default. So let me show you this. PPO stable baselines 3. Where is it? So batch size is 64. So it needs to be a function of 64. If you don't have it set as a function of that or a multiple of that, you're going to get this warning, and it's going to say that the batch size is going to be truncated. So ideally, make sure it's a multiple of 60 of your batch size. So 8192 divided by 64, in this case 128 perfectly. There's no remainders, so we're good there. The other thing that I did is I changed the clip range and I set that to 10%. So this effectively clips our gradient. So it ensures that we don't have too significant of a change in the gradient that we're actually passing through as part of our PPO algorithm. I talked a little bit about this in the explainer. So 0.1 seemed to be an okay parameter. Gamma, this is our discount factor, so I set it to 95%. And GAE lambda is a smoothing parameter, which is used to calculate our advantage. I set that to 90% as well. Then I actually ended up training for not 40,000 steps or not 100,000 steps. The initial phase, I trained for 400,000. Now, you might want to train this for significantly longer, significantly shorter. This is an example of what your logs might look like. This isn't necessarily my award-winning run or the run that produced the best results, but this is effectively an idea of what you can expect to see. So our episode reward mean is sort of trending around. If I go and smooth this out a bit, let's smooth it to the max. So you can see it's trended up and then it's sort of heading downwards. Our episode reward mean, so this is episode length mean. Our episode reward mean is trending upwards, which is looking good. Now, one thing that I noticed is that if you see episode length mean tank really, really fast and episode reward mean shoot up really, really fast, what that effectively means is that your agent is just running straight forward. So it's bypassing all the enemies and it's running straight forward. So that probably means that you've maybe overfit the model a little bit too much. And what you can do is reload the model from a previous set of weights, which isn't going that far. So that's one thing that I noticed as well. If this tanked and this spiked really high, then you've maybe gone a little bit too far and your agent's just running straight forward. So it's not necessarily going to lead to good results when we go and apply curriculum learning. So we've got some divergence. That means that our model is still changing and learning. Clip fraction, so it's clipping about 37% of the time. Looking like it's okay if I smooth that out. Yeah, around 30, what is that? Around about 35% of the time. So not too bad. Our entropy loss is going up. That's fine. Explained variance is going up. This means that our critic is starting to learn the determinants of future reward. Policy gradient trending around. So you can see that this is the reason that I'm showing this is that when I started learning reinforcement learning, I didn't really know what these charts should look like. This is a good example of training, which is kind of going okay at the moment. Now, again, this might spike out and blow out completely, but this is a good example of what should happen. This should keep going down, but not too fast. This should keep going up and again, but not too fast. Because if it goes really fast, it means that we potentially have unstable training on our hands. Okay, so what have I talked about? So I've talked about the changes to the environment, the effects of hyperparameter tuning, as well as the training length. The other thing that I wanted to talk to you about is I actually noticed that there is a little bit of a bug inside of the Vizdoom environment. So one of the things that we used as part of our reward shaping was the hit count. Now, the thing is that if we actually go into game variables, so Vizdoom game variables, and again, I'll include a link to this. So we used hit count. Now, if you pay attention to this really closely, it says it counts the number of hit monsters, players, bots during the current episode. Not necessarily the number of monsters, players, or bots that you have hit during the episode. So this might mean that we're unfairly rewarding or incorrectly rewarding our agent, depending on what's happening in the state. Because if one monster kills another monster, let's say even by accident, it's going to get a reward based on our reward function from that. So that's something to keep in mind. I actually tried using damage count, and this I think was a little bit better. And again, don't quote me on this, but I think that was a better metric because it's the damage that you have dealt, not necessarily just in general. So if you're getting poor performance, that might be another thing to take a look at as well. Okay, so assume that our model's gone and trained. We've trained for 400,000 steps and we wanted to go and apply some curriculum learning. Let me show you how to actually do this. So the first thing that we need to do is recreate the environment and now pass through a new level of difficulty. So we can actually copy this environment creation bit or environment creation code up here. And the thing that we're going to do is we are going to change this to be difficulty 2. So remember we set up our config. All we need to do is change the config that we're going to be passing through so that we've got the config with difficulty 2 or skill level 2. So let me show you this. If we go into D, YouTube, Vizdoom, and then where was it? GitHub, Vizdoom, scenarios, S2. So this is with Doom skill 2, right? You can see that there. Another thing to keep in mind, let me actually show you as well how to change that damage count parameter. So all I did was change the value from hit count to damage count. I don't have this in this particular folder, so you can ignore this for now. This is just something that you could potentially try. So this is still hit count. If you do change it from hit count to damage count, you should probably change the weighting as well, because that's probably going to play a factor. Okay, so back to curriculum learning. So we've gone and changed our environment. Then what we need to do is we need to reset the environment that our model is using. So we can use model or type in model.setEnv. We have a model, we've got one. And then pass through env, and then we can type in model.learn total time steps equals 40,000, for example. Let's see if that works. Okay, what's happened there? Callback equals callback. Okay, that's looking good. Model is not defined. Okay, so we need to reinstantiate it. So let's create that. So then we'd go and trigger model.learn here, and then we'd go and run this effectively. But actually, one good thing to note is like, how might you load up the model again if you've actually gone and trained already? So what we can do is we can type in model.load, and then we can load from our best model effectively. So we remember it was inside a train, and then train corridor. And then we can pass through the model that we want to load. So in this case, I've got a bunch floating around here. So let's say I wanted to load up the 70,000 model. And let's say that our model spiked, right? So over here, we had a spike. We had a drop off after 272. So we might want to reload from 262. So the closest one to that is probably going to be 260. So I think I've actually got this in a different folder. 260. Oh, different folder. I've saved some of these inside of different folders as well. Just keep that in mind. So it's not going to be inside a corridor test. So I'd pick up 260, load that model. So this is effectively preloading our model with weights. Give that a sec to load. Cool. So that's loaded. We could then kick off our curriculum learning. So this is going to load the new scenario. We're going to set the model environment to be this environment. So we've typed in model.set_env and pass through this new environment with the harder difficulty. And then we're able to run model.learn again. So we could run that, and that will go and kick off our curriculum learning. Then once that's trained, and assuming we're getting good performance, we could grab this, paste that there, and then we could change it to difficulty 3. So paste in 3 there, kick that off. And again, likewise, copy it, paste it there, kick it off. And again, for the last level, so this will be Doom skill level 5, paste 5 in there, and then kick that off. Now, again, pay very close attention to your logs. So if you get those massive spikes, or if you get tanks, then you might want to reload from a previous set of weights which was performing well, and then re-kick off from there. I'm going to do a lot more research into how to improve stability on reinforcement learning over the coming weeks and months, because it's something that I'm super interested in. Let me know if you're interested in it as well, because I'd be more than happy to share my findings. But based on that, once you've gone and finished training, you're going to get all of your weights saved into the train and then train corridor folder. So you'll effectively have a ton of weights here that you'll effectively be able to pick up and then go on ahead and test out. Now, I'm going to do my best to share some of the best model weights that I had with you as well, so you can actually pick those up and try them out. So you'll actually be able to see the high performing 560K model that I show in the results coming up soon. But on that note, that is how to go on ahead and perform your curriculum learning, and just a couple of key tips on hyperparameter tuning. So the few things that I changed, just to recap, are that we went into our environment, we went and reset the self.ammo property, and we set that initially to kick off at 52. And then I went and changed a number of the hyperparameters inside of our model. So I changed the learning rate, the number of end steps, the clip range, gamma, and then GA lambda. So remember, the learning rate is how fast our model is going to learn. The end steps value is effectively our batch size. Clip range is how much we want to clip our gradient by. Gamma is our discount factor, and GA lambda effectively acts like a smoothing parameter. Then the other thing that I went and did is I went and changed total time steps to 400,000. And again, you might want to play around with this, increase it, decrease it, just pay very close attention to your logs, because you want to monitor performance and see how it's actually performing. Then we can reload our model from an existing trained set of weights and then kick off our curriculum learning. So remember that the core thing with curriculum learning is that you're just going to reload the new environment with the new difficulty. So remember, we changed it to S2. We went and then set the new environment and then kicked off training again. But on that note, that about wraps it up. I'll share those final weights with you. Let me know how you go and what your performance is like. And if you see that there's anything else which influences the results, do let me know. Let's jump back over to Bob and check out our results. Alrighty, and we're now on to the third and final level, which is the deadly corridor environment. Up first is the 10K model, which absolutely sucked. And then we're moving on to our 100K model. So he's at least managing to shoot some of the enemies, and he's starting to get stuck inside of that initial bottleneck. He sort of gets up to there and kind of just freezes when he really should be shooting the enemies there. 200k steps, looking a little bit better now and starting to progress a little further forward. And 400k steps, he's actively pursuing these enemies now. You can see he's got this bit of a strategy as he approaches the first bottleneck. He slows down and positions himself to one side of the corridor in order to be able to protect against the other enemy. And he's getting pretty close to that final armor now. And so we're jumping up to the model that's been trained for 560,000 steps. This is probably the best model that I ended up training. He's actively going out and taking out his enemies, and he's about to get the armor, and he successfully completes that goal. And as you can see, he's progressing further forward. He's actively doing way better than he'd done before. But you can see that if he doesn't take out those two final enemies, he won't actually make it to the end. So sometimes he gets pretty close. Other times he just sort of skips through. So definitely getting better. We're now upping the difficulty. So this is on Doom skill level 2. You can see he's progressively moving further forward. He's definitely getting there. And what do you know? He manages to clear the level again. Not too bad. But you can see he's not necessarily clearing the level every single time. Oh, and he manages to get a shotgun and kind of goes a little crazy with this. And now gets a machine gun and decides he doesn't really want the armor, just would rather go around like a crazed maniac. And we're now running that 560k model on skill level 3, manages to get a shotgun again and kind of goes a little crazy here. Oh, he's back on track, manages to take out the enemies, and he still forgets to take out that final enemy on the left there. But you can see that he's definitely built up a strategy. The reinforcement learning model is definitely working and gets the armor. Oh no, he turns around and decides he doesn't want it. So we're now up to Doom skill level 4. So again, this has been fine-tuned on the increasing level of difficulties using curriculum learning. So even though the levels are harder, our agent is still performing. He's now managed to get, I don't know what this is, a shotgun and just sort of start spinning. He's aggressively taking out these enemies, manages to take out the last one. And that, I think, is one of the deciding factors. If he manages to take out both enemies in that final sort of antechamber of the corridor, he successfully gets to the armor. If he doesn't get there, then there's really no chance. So he takes out the first two, takes out the nope, see, missed the second one and wasn't able to actually get there. But still definitely better than what we had at our 10,000 step model. And this is where it all comes to fruition. The 560k model on Doom skill level 5. So he's actively strafing through those different bottlenecks to be able to take out the enemies before they see him. And let's see if he manages to get the armor here. Manages to take out the last one. That's the deciding factor. And successfully gets that armor. So you can see that as we use that curriculum learning, our agent is able to fine tune and definitely get better. Now, I'm going to share these weights. So if you want to try this out yourself, you can definitely do that. But you can see he's getting there. He's run out of health. So he must have been shot in the back there. Shot that first enemy, second enemy, third, fourth. This should be pretty successful. Oh no, and he turns around and decides he doesn't want it, but he goes back and tries to take out that last enemy. But you can see it's definitely getting a lot better than what we had through that first 10K model. The agent is definitely progressing further forward as our reinforcement learning model learns. And that's a wrap. So you were able to see how our agent progressed all the way from our initial 10K model, which was trained on skill level 1, all the way up to the 560K model that was fine-tuned on skill level 5.
Dude, that was insane. I know, cray, right? I can't believe how fast the agent was. Like seriously, I was surprised. Yeah, that was nuts. Wonder if there's any other techniques that could be used to improve performance further. I think reward shaping and curriculum learning are great first starts. I think we could also look at training the model on auxiliary tasks like enemy detection and using curiosity-driven exploration to improve exploration of the environment. Huh, cool. Thanks, dude. And thanks for checking this out. I really appreciate you sticking around to the end of the video and let me know what you thought and whether or not there's any other games we should try tackling. Thanks so much for tuning in, guys. Hopefully you enjoyed this video. I know it's been a little while since we posted the last one, but again, I'm just getting back into the swing of things this year, but I do have a ton more cool game-based AI and sort of more sophisticated state-of-the-art AI videos coming through for you. Thanks again for tuning in. Peace. If you're like me and absolutely suck at Street Fighter, then this is the video for you. This is how to build a Street Fighter AI. What's happening, guys? My name is Nicholas tonight, and in this video we're going to be going through, as I said, how to build a reinforcement learning model or AI for Street Fighter. This is slightly different to the games that we've played before in that we're going to be using the Gym Retro package or library to be able to do this. Let's take a deeper look as to what we'll be going through. So in this video, we're going to be very much focused on 3 key things. We are first and foremost going to be building the reinforcement learning model to be able to play Street Fighter. Now, in order to do that, first up, what we're going to do is we're going to set up the Gym Retro environment, and we're actually going to set it up to work with the Street Fighter ROM, or effectively the game cartridge. Then we're going to do something a little bit different. We're actually going to learn how to hyperparameter tune using a library called OpTuner. So if you've ever built any machine learning models before, you know that hyperparameter tuning is super critical when it comes to producing a really good model. We're going to do this for our reinforcement learning environment. And then last but not least, we're going to learn how to fine tune using stable baselines, which is pretty much what we've done in the Doom video and the Mario video before, but we're going to be doing it for Street Fighter in this video. Ready to do it? Let's get to it. Hey Nick, did you ever play Street Fighter growing up? Yeah, but I freaking sucked at it, dude. Yeah, you did. But anyway, you reckon you could build some AI for it? Maybe level up from your button mashing? Hey, button mashing got the job done, man. Okay, maybe not the greatest job, but it kind of worked. Let me dig into it anyway.
Well, all right. It's time to get started with setting up our game. In order to do this, we're going to be using the Gym Retro package. Now, in all fairness, it is a little bit old and a bit of a pain in the ass to work with. But once you got it working, it's great. All we need to do is load the game ROM, aka the cartridge, and then we can use it inside of an OpenAI gym environment using the retro.make method. Alrighty, ladies and gentlemen, so we are going to be building a Street Fighter AI in this tutorial. Now, I realized we didn't give our client a name, so we're going to go on ahead and name him, I don't know, Hector. Hector's going to be our client. Okay, so in order to build our Street Fighter AI, the first thing that we said that we're going to do for Hector is at least try to get Street Fighter up and running inside of Python. Now, this is relatively, actually, it is not relatively straightforward. It can be a little bit tricky at times. So I'm going to walk you through what I found. Hopefully that works. And again, I'm going to share all this code available, or that'll be available via GitHub if you want to pick it up. Okay, so the first thing that we need to do is install 2 dependencies. These are going to be OpenAI Gym and Gym Retro. Now, Gym is the base class for going on ahead and building reinforcement learning models. Now, keep in mind that the sort of foundation of reinforcement learning is area 51. So agent, reward, environment, and action. Now, the environment bit of this is handled by OpenAI Gym. That's why it's great, makes it easy to do. And there's a whole heap of integrations for it. Now, in this particular case, there is an integration called Gym Retro, which lets you play a ton of games. I mean, look at that over there. As if that is not a sick GIF. I should integrate that into one of those animated set of slides. Like, it looks sick. So we're going to try to build a reinforcement learning agent to play Streetfighter. Now, in order to do that, we're going to be using that package. So the first thing that we need to do is actually go on ahead and install it. Now, to do that, we can just type in pip install gym and then gym retro. So that should go on ahead and install our dependencies. So that looks like it's happened successfully. We've got a little bit of a warning there, but that's just telling us that our pip version is a little bit old. That's perfectly fine. You can keep going on ahead. So pip install gym and then gym retro. Cool. So that is now all well and good. Now that we've actually gone and imported that or installed that, the next thing that we need to do is actually go on ahead and import retro. So let's do that. So we can just type in import retro. And so if we add in a little comment, because that's good practice, always comment your code, guys. It's such a simple thing to do, but it adds so much value. All right, so what are we doing? So we are importing. And when you write a comment, actually, this is just pet peeve. Write why you're doing something, not necessarily what you're doing. Why are you doing? So we are importing retro to make the gym environment. That's a terrible comment. To just query that, not to make the gym environment, to play Street Fighter using a ROM. Right, so that's why we're importing retro. So we want to be able to play Street Fighter using retro. So we're going to go on ahead and import that. So I've written import retro. Now that that is imported into our Jupyter Notebook, the next thing that we need to do is actually install Street Fighter. Now, a core thing that happened with Gym Retro, and again, Gym Retro has been around for a while, and I don't know how much development has gone into it since, but one big thing that they did is they split the framework from the game. So just because you install Gym Retro doesn't mean that you're going to have Street Fighter already configured. Doesn't mean that it's going to be ready for reinforcement learning once you import it. So we actually need to go and bring in that ROM in order to get it to work. Now, I found this site that I think actually had a successful ROM, but I'm actually going to show you what it actually looks like. In the interest of transparency, you'll actually see what my setup looks like. So if you actually go to this site, Wow ROMs, I'm just going to hit refresh. This will download it and you'll get this ROM file here, right? So I've gone and downloaded a ton of them. Now, inside of my main folder that I'm working in, it's called Sonic. So I originally started developing this tutorial for Sonic, and then everyone on the comments or the community tab said, nah, Nick, we want Street Fighter. So I left the naming, but it was originally Sonic. It's now Street Fighter. Okay. So I've got this folder here called ROMs, and inside of there, I've taken the ROMs that I just downloaded, right? So you can see that I've got that USA 2 one. If I extract that here, I can go and overwrite. I don't need to go and overwrite. What we're doing is we're downloading that ROM, creating a folder called ROMs and pasting it in there, right? So this is just going to be a standard folder. You download your games, you put it in a folder. That is part one done. Now, what we actually need to do is associate and register that game cartridge. Think of Gym Retro as your emulator. It might be an Xbox, PlayStation, whatever. The ROM is actually the game, or the game cartridge, or the CD or DVD, Blu-ray, whatever you want to call it. So what we now need to do is effectively install the game into the Gym Retro emulator, which is effectively what we're going to do here. Now, rather than doing this inside, I think I downloaded that one over there accidentally. They should all be inside of ROMs. What we're going to do here is we're going to open up a new command prompt, and I'm going to navigate to the folder that I'm working in. So it is Sonic, because I was too lazy to rename that. And I'm going to activate my environment, which is also apparently is called Sonic. Now, if you are not working with a virtual environment, don't worry about activating it. Just run this command or similar to what I'm about to run. Can we make this bigger? No, it doesn't want to go bigger. All right, so what we need to do is go into ROMs. And from here, we can write python-m and then retro.import and then dot. So let me show you that full line. So inside of the ROMs folder, so you can see that I'm inside of ROMs, I've just written Python -m retro.import. Now, the reason that this is going to work is because from our Jupyter Notebook, the environment that is running in is the same environment that I've activated over here. So by installing Retro through my Jupyter Notebook, I've now got it available here. That's the advantage of working in virtual environments. Actually, if you guys want a tutorial on virtual environments, hit me up because I think it's super useful. It's definitely changed how I code. Okay, so because we've gone and done that, we can actually go and use this retro.import functional method. So what I've gone and written is Python -m retro.import, and then I've added this dot. That dot is super important because it tells us to import anything in the current folder, right? So don't forget the dot, otherwise it's going to throw a whole bunch of errors. But if I go and run this now, you can see that it's gone and said imported Streetfighter blah blah blah, imported Streetfighter blah blah blah, imported Streetfighter blah blah blah, imported 3 games. So this means that it has successfully gone and imported this and registered it to our specific retro environment inside of Python. This is super important when you're working with any of the retro games. Now, there are a ton of retro games, so that's our setup now gone and installed. If we wanted to go and see the different retro games, we can actually type retro.data. I think it's list. Yeah, list games. There are a ton. Now, you still got to go on ahead and set them up. You got to go get the ROM and import it exactly like what we did. I think Donkey Kong would be sick. That used to be like one of my favorite games. But you can see that there are a ton. Final Fantasy is on here as well. Wait, did I say that? No, fine. That was something else. Okay, I was about to say that'd be sick. I wonder if Pokemon's on here because there is a Game Boy emulator. No, it doesn't look like there's Pokemon, but there are a ton of others, right? I'm keeping on scrolling. All right, so there's clearly an absolute ton of different environments that you can actually, or games that you can actually go on ahead and play. So if you want to try this on something else, you definitely could. Pre-processing is probably going to be a little bit different, but you sort of get the idea. Okay, so what have we gone and done? We've gone and installed Gym and Gym Retro. We've gone and imported it into our Jupyter Notebook, and then we've gone and listed out the different games that are available through Retro. Then what we also did, I've gone and closed it now, but we went and ran, I'm just going to write this command here so you've got it in case you need it later on, but it's going to be Python -m retro.import and then dot. And remember, we need to run this from the ROMs folder, or where you have your game ROMs, right? So remember that, super important, because you actually need to attach the ROM to your retro environment. Okay, now that that's done, we can actually go on ahead and test this out. So let's go on ahead and spin up an instance of our Streetfighter environment and give it a crack. Okay, that is our environment instantiated. So I've gone and written env equals retro.make. So this is super important. The retro.make function method in this particular case allows us to go on ahead and create an environment using the retro framework, right? To that, we are passing through one keyword argument, and that is the game value that we actually want to spin up. So game equals Streetfighter 2 Special Champion Edition -Genesis. Wow, okay. That is, just make sure the name of this game matches what you've actually got in your list, right? So if I go here, we could just as easily copy it. So I could find Street Fighter. I spell out Fighther. Typing is not my strong suit. So if I copy that and enable scrolling, and if I go and paste that there, right? Okay, so it looks like we've got it named correctly. Can go on ahead and run this. All right, this is actually good that I'm showing you this now. Key thing about Gym Retro and one of my pet peeves, there is a way around it, but I'm going to show you this and get you to work with it because it's something that you're going to encounter. You cannot create multiple instances of the emulator. It's going to throw up this particular error that you're seeing on the screen right here. So it's going to say, cannot create multiple emulator instances per process. Make sure to call env.close on each environment before creating a new one. This is basically saying you can't run more than one game at the same time, because remember that we've actually gone and run this Hasn't popped up yet. We've actually gone and run this already. If we go and run it again, it's going to throw this error because we've actually got an emulator running in the background. I don't know if you can see it in the process monitor. Let's search for Python. That's probably, I don't think this is specifically it, but just know that right now we've actually got one up and running, which is why it's throwing this particular error. There is a way around it. So I found, what was it called? It was called Gym Retro Wrapper. I think that's what it was called. Yeah, it's Retro Wrapper. So this effectively allowed you to run it in parallel. So if you want to go and run multiple environments in parallel, definitely go on ahead and check this out. So if you go to github.com/maxstrange/retro wrapper, that is a way around this. But for now, we're not going to deal with that. I'm going to show you how to get around this. Okay, so we've gone and got this error. To fix this, all you need to do is type in env.close. So close the one that's already up and running. Then if we go and run this again, no error. So it's problem solved, right? That's just a really important thing to note with retro. It is a little bit clunky when it comes to opening and closing environments. Now, when you go and render it, even if you go and run env.close, it's not actually going to close the game frame. So you have to actually shut down your Jupyter Notebook or your command prompt if you actually want to go ahead and do that. Okay, what were we going to do next? All right, let's actually take a look at this environment. So if we type in env.observation space, let's just take a look at it. So it looks like we've got a box on our hands. Let's actually just type in .sample. Right, so we've got that big box. What's the shape of that? It's a little bit of a pain that it doesn't actually... All right, so we've got a frame which is 200 by 256 by 3. Let me zoom in on that. Very important to note. So basically, it's an image that we're getting back here of the dimensions 200, which I believe is the height, by 256, which is the width, by 3 channels, which is going to be the color. And then what else do we have? Action space. So our action space is multi-binary. So this is a little bit different to the other action spaces that we've taken a look at before. And basically, this means that it's going to be, so if I just type in np.zeros 12, I don't have NumPy imported. Let me just write it out. So we're effectively going to have 12 positions. What's the length of this? 12. Okay. Oh, wow. What a guess. Okay. So our multi-binary space means that we're going to have a varying combination or permutation of ones and zeros inside of this type of shape. So this might be a valid action. This might be a valid action. And this might be a valid action. So that particular action might correspond to a particular move that our character might actually be able to go on ahead and take. So that is what our action space actually looks like. Now, if I type in .sample, you'll see that there exactly, right? So that is an example. If I go and run it again, that's an example, that's an example, that's an example, that's an example. Now, this means that there are an absolute ton of potential actions that our agent can take. Now, the nice thing about retro is that there is a parameter you can pass through to the retro.make function, which filters the available actions, which is what we'll do when we go and set up our environment. But for now, just know that this is going to be the shape of our action space. Okay. So given that, so we've taken a look at our observation space. Let's add some comments. So this actually makes or starts up the game environment. This closes the game environment. Important, given we can only run one at a time. env.action space, sample the actions that are available. And note they're multi-binary. And we also took a look at our observation space as well. So we can write a comment, sample the observation space. env.observation.sample. Cool. All right. So that is, we've at least started exploring. And again, a big part of machine learning is exploratory data analysis. You got to know what you're actually working with. So we can enable, one of the cool things about Jupyter Lab is you can enable scrolling for outputs. I think that makes your life so much easier. Just keeps things a little bit cleaner. Okay. So we've gone and I'm just going to close that as well. What have we gone and done? So we've installed our dependencies, imported a bunch of stuff, taken or started up a game environment. We've closed it, taken a look at our observation space, and we've sampled it. Now it'd be really nice. Okay, so I've gone to run that again, throws an error, run env close, run it again. So that's running. Okay, so it'd be really nice to actually go and see what this actually looks like if we actually go and test it out. So let's actually go on ahead and do this. So we're going to write a bit of a loop to actually test out our environment in this particular case. So I'm just going to add another cell or a bunch of cells, and let's go and write a game loop. This is going to be pretty similar to how we write a game loop for, what we did for Mario, what we did for Doom, but we're going to do it for Street Fighter. So let's do it. Okay, I think that is our game loop written. So it looks like there's a ton of stuff, but this is, you guys have seen this before if you've watched one of the game tutorials. All right, but I'm going to walk you through it. Anyway, so the first line that I've written is obs equals env.reset. So remember, whenever we're starting a game, we need to first up call env.reset. This resets our game to our starting state. So let's add a comment. So reset game to starting state. Then we're also creating a done flag. So this tells us whether or not we've died or whether or not the game is actually finished. So we initially set this to false. Set flag to false. And then we're actually going to loop through one time. So we're only going to play one game. So for game in range 1, which is this loop here. So that kicks off our loop. Then we're just going to keep looping until we die. So while not done, and then we've got, let's actually skip this bit for a second. So while we're not done, we want to render our environment, and then we're going to take a step in our environment using env.step. Now, what we're passing to env.step is just sampling our environment at the moment. So I've written env.action_space.sample, right? So this is doing exactly as what we did over here. So it's just randomly taking actions inside of our game environment. Then in order to render that, we're using env.render. So we render, then we take an action, and then we're going to be printing out our reward. Now, if we do die, so if the game is done, then we're going to start again. So obs equals env.reset. So this allows us to kick off again. Okay, so that looks okay. Let's double check that looks fine. Let's actually give that a crack. So if we go, I'm just going to move this to the side so you can actually see the pop-up. We should get a little pop-up, and that is our Street Fighter game now running. I think we can make this a bit bigger. Much easier to see. All right, so you can see that we're obviously playing as Ryu. He's actually not doing too bad at the moment, taking random actions. Okay, now Ken's kicking ass. Okay, and that's one game done. So you can see that, like, if I can go, actually, one good thing is to try to slow down these, the actions, because you can't actually see them all that well. So if I go and import time up here, import time to slow down game, import time. So what we can do is between each one of these actions, we can take a little bit of a break. So it's almost like a breather. So time.sleep, we set that to 0.2. You'll be able to see it a little bit more effectively. So if we go and run that again, that's probably a little bit too slow. Let's set it to 1. All right, so you can see the game is just getting started. Okay, this is way too slow. Let's set it to 0.1. Okay, that's a bit better. All right, and this is purely with random actions at the moment. Ryu's managed to Hadouken, pretty sick. Actually managed to beat Guile, not too bad. Now, one thing to note is that even though we're playing, the way that we're getting reward right now is pretty sucky, because you can see how many zeros we're getting here. All right, there was occasionally a number. That's probably just because he's won the match. All right, so it looks like he's getting right now the reward function is set to 500 if you win, but he's not getting rewarded as he goes along, which is pretty tough when it comes to actually determining how to actually train this model. Because if he's only getting a reward for when he wins, then it's going to make it really, really difficult to actually train a reinforcement learning agent. So this is something really important to note. So we're getting really sparse rewards. Now we're actually going to configure this a little bit differently so that we can actually incrementally reward Ryu. But you can see that as of right now, we've actually gone and satisfied Hector's initial requirement, which is to get Streetfighter up and running. I'm just going to stop that. Cool. So that is at least the first part done. Now, remember how I said that this is a bit of a pain. So if I go and run env.close, it's not going to close down this frame. It's just going to shut down the kernel. So that's just a thing to note. If you go and close down that frame, it's going to kill your Python kernel. So just keep that in mind. But for now, that is at least our initial step done. So we've gone and set up Streetfighter. So we went and imported our dependencies. We took a look at how to list our games. We've gone and started up our Gym Retro environment, and we've also gone and imported our ROMs, took a look at our observation space and our action space, and we also started to see some of the rewards that we're getting, which at the moment look very, very sparse. This isn't attached to the points that we're getting in the game. It just looks like we might be getting points if we win, which makes it pretty hard to actually go and train a reinforcement learning agent, or AI in this particular case. We also went and wrote our testing loop, so that actually allows us to see how our agent is actually performing just using random actions, right? So env.actionspace.sample. I don't know if I went through this in great detail, but basically what we get back when we run env.step is we get back the next observation, the reward from that particular step, whether or not the game is done, and we also get back any info. Now, actually, info is probably a really important one for me to show you. So if I type in info, you get back the number of enemy matches that have been won. So this is how many matches your enemies won. You also get back the score. You get back the number of matches you've won, whether or not there's a continue timer set. You also get the enemy's health and your own health. So in this particular case, I think when we go and set up our environment, we're actually going to attach the score as our reward function rather than whatever the default is, because this should ideally help our agent learn what actions are performing better than others. Okay, but in that particular case, that is looking pretty good at the moment. So we've at least gone and set up our initial stages. This is all looking pretty good. And again, all this code is going to be available in the description below. But for now, let's go back and check in on Hector and show him what we've gone and done successfully.
So, how'd you go? Well, I got the game working, so it's a start. Yeah, right. I feel ya. We're on a journey. So what's next? Taking a quick look at it, I think what we're gonna need to do is tweak the game environment. So first things first, we wanna compress down the information that we're gonna have to pass to our AI to make it train faster. And then what we should probably do is tweak the reward function. So ideally, Ryu gets some reward every time he does something right. Got it. We'll get to it, man.
In the spirit of a journey, we're going to Candy Mountain. And what I mean by that is, I don't know where I was going with that. What we're going to be doing here is pre-processing the game environment. There's really three main things that we'll do. First, we're going to calculate the change in pixels from our current frame versus our last frame. This is in order to capture movement. And then what we're also going to do is put our game on a bit of a diet. We're going to drop some pixels to train faster by grayscaling and reshaping our frames to be 84 by 84 by 1 pixels. Alrighty, so Hector's pretty happy with how we've gone so far. But what we really need to do is get this environment ready for training. Now, we did notice that when we initially went and played that game, we were getting really sparse rewards. That's going to be an absolute pain in the ass when it comes to training a reinforcement learning agent. So we are going to do a couple of things. First up, what we're going to do is we're going to pre-process the game. Let's actually write some notes for what we're going to do here. So what we are going to do. Fun. Okay, so we are going to, let's actually make this markdown. What do we do? So we're going to pre-process. And as part of that, we are going to grayscale. We are going to capture the frame delta. And by this, I mean, we're going to take the current frame and subtract the last frame. What that's going to do is it's going to allow us to see the change in pixels. So rather than just giving it our agent the current frames, we're going to show the change. So this should effectively allow us to see how our agent is or what pixels have actually changed, because that's effectively what's relevant to our particular agent. So grayscale, frame delta, and then we're going to crush the image. So we're going to resize it. Resize the frame so we have less pixels. So that's what we're going to do for our observations. So observation pre-processing. We are also going to filter the actions. This is available inside of Gym Retro, so it's just a parameter. What else are we going to do? We are also going to change our reward function. Now, initially, I think for our reward function, I'm just going to set it to this score. You definitely could do some other stuff. Like you could do an enemy health function to go, you get a point for every time you take away the enemy's health. Yeah, you get a point or some sort of reward for every time you degrade the enemy's health, and you lose a point for every time you lose health. So, I mean, we could sort of have some sort of reward function on that. For now, I think I'm just going to go with the baseline score, but you could definitely tweak this. So we're going to set this to score. Okay, so I think that is pretty good. So if we go and do those, let's actually paste this inside of, so I'm just going to cut that, paste it in here. So we're going to need to go through these 3 different processes. And if you've done much machine learning or deep learning, you know that data pre-processing is the most important step. It is no different for reinforcement learning agent or no different for reinforcement learning. I think biggest thing that I had to pick up when I got started with reinforcement learning is that yes, the algorithms are sick, but they are commodities. What is most important is actually getting your environment in an appropriate state to actually be able to go and train your agent, and doing all that pre-processing to get it ready for doing stuff. Like half the time I would just go and bang through, apply a PPO model and try to get it to train, and it wouldn't do anything. But I mean, if you see that coming out of this environment, we've only got a single reward function, that's going to be really, really difficult for our reinforcement learning model to actually go on ahead and learn. So doing your pre-processing first up is going to make your life about 1 billion times easier. That is fact. Definitely 1 billion times easier. Okay, so quote me on that. Okay, so the first thing that we actually need to do when setting up our environment is we need to go and import a bunch of stuff. So we are going to need to import the base environment classes. We're also going to need to import a couple of action spaces as well. And we'll probably import NumPy and OpenCV. So NumPy is going to help us with just a little bit of data pre-processing, but namely it's going to help us do the frame delta. And we're also going to import OpenCV to do the grayscaling and the frame resizing, I think. So let's go on ahead and import a bunch of stuff. Oh, this is set to Markdown. So the first line that I've written is from gym import env. So this is our base environment class. The next line is from gym.spaces import, and I'm going to import multi-binary. And so this is just going to ensure that when we wrap our environment inside of this environment, we're going to pick up the correct environment or the correct action space type, because that's what our existing action space is. And we're also going to have box. Then we're going to import NumPy. So from actually import NumPy as NP. We're going to import OpenCV. If you don't have OpenCV installed, which is this line down here, so import CV2, it's just pip install, I think it's OpenCV-Python. Right, so if you don't have that installed, just go on ahead and run that line. So pip install OpenCV-Python. Okay, so what have we gone and done? So we've written 4 lines. So from gym import env. So this is importing our environment base class. Import environment base class. Then we've gone and imported multi-binary in box. Import. This is for a wrapper. So this is importing the space shapes for the environment. And the line there is from gym.spaces import multi-binary comma box. Then we've imported NumPy, so import NumPy to calculate frame delta, aka the change. And then that line is import NumPy as NP, and then we've imported OpenCV. Import OpenCV for grayscaling. Alrighty, that is all of our dependencies now imported. So we've gone and written 4 lines of code there, a bunch of comments. I think we're good to actually go and build up our custom environment now. So what we're going to do is we're going to create a new class, and we're going to call it Streetfighter. Streetfighter. And then to that, so this is, let's add a comment. So create custom environment. This is like a really, really powerful skill, guys. If you get good at creating these custom environments, it's going to make your skill level when doing reinforcement learning a ton easier, because that means that you're going to understand how to structure these environments for reinforcement learning, almost akin to being really good at EDA or exploratory data analysis for machine learning. This is a really, really powerful skill. Okay. So first up, we're creating a class. We're calling it Streetfighter, and this is with camel case, so capital S, capital F. That's just Python practice, I think. And then to that, we're going to pass through our base environment from over here. And then there are a number of methods that we need to go and initialize in order to create this custom environment. So the first one is init. And this is what gets called when our environment is created. So I've just written def __ init __, and then to that method, I'm passing through our current instance. So self : and then we're just setting it as pass for now. The next method that we need to define is going to be step. Again, we're going to pass through self, and this is going to be what we actually do how do we actually pre-process an action? What do we actually do inside of our environment? So this is probably going to take in an action. The next method is going to be render. Right, and this is what we do, or how we actually go about rendering and whether or not we render. What else do we need? So init, step, render. We need a reset method. And this is what we call initially when we actually go and reset our environment. So we effectively restart it to begin with. And then the last one that we're probably going to need is preprocess. And then to that, we're going to pass through our observation. Pass. Okay. Cool. So that is our template or shell environment at the moment. So if you remember that you're going to need those, this one is optional. So you don't necessarily need a pre-process method, but it's good practice to do some sort of pre-processing if you are going to be building a custom environment. Otherwise, it kind of defeats the purpose. Okay. So we've got 5 methods inside of our class. So we've created a new class called Streetfighter. And we've said that we're passing through our base environment, which is from here. We're going to inherit that inside of our init method. And then we've got a whole bunch of others. So we've got a step method, a render method, a reset method, and a pre-process method. Okay, so now that is at least created at a base level, the first thing that we should probably do is start on our init method. So inside of our init method, we're going to do a couple of things. We are going to first up inherit from our base environment. So we can type in super dot underscore init. So that will inherit from this base environment over here. And then there's a few other things that we need to do. So we need to specify what our action space and observation space are going to be. Specify action space and observation space. Okay, cool. So what are we doing here? So self.observation space equals, it's going to be a box. So if we actually take a look, this is sample. So if we actually take a look at our box over here, so think of your box as just like an array. So box gives you the ability to return any shape of array, and you can specify the data types and whatnot as well. So in this particular case, we have a box. Let me show you this. A box of shape 200, 256, 3 with the data type uint8. We're just going to initially recreate that before we go on ahead and do our pre-processing. So let me show you how to do that. So box, to that we need to pass through a couple of parameters. So our low value, which is going to be 0, our high value, which is going to be 255 because it's a color image. And then what do we need? Shape, I think. Shape equals, and then for our shape, we're just going to set it equal to this for now. So 200, 256, 3. Boom. And then D type, we're going to set that mp.uint8. And that is our box now created. So if I copy this, right, and take it out of here, you can see we are getting exactly the same shape as what we had when we were taking a look at our base environment. So over here. Cool. But now you're probably thinking, Nick, why the hell are you doing that? That's just a massive waste of time. We are going to reshape this. I think we're going to make it 84 by 84 by 1. So it's going to be a grayscaled frame which has a smaller number of pixels. But for now, let's leave it like this. We'll come back to that. Okay, so we've got our observation space set up. Now we need our action space. So self.action underscore space equals multi-binary. And to that, we can just pass through 12. Exactly the same as what we had over. Yeah, exactly. This is exactly this. So if we go and run this now, dot sample. Boom, exactly the same thing, right? This we are not going to change, at least initially, right? We're just going to leave, no, we're going to leave that the same. There is a way, I can't remember where I found it, but if I do share, I'll share it in the description below. You can actually switch over the action space from multi-binary to be a discrete observation space as well. There's a parameter that you can pass through inside of the game setup. Okay, so those are our action space and our observation space now set up. Now, the next thing that we want to do is start up an instance of the game. An instance of the game. And we're going to call self.game. And we are just going to copy this line over here. So retro.make. You can paste that there. But we are going to pass through one additional parameter. We are going to pass through use filtered actions. I think it's what is it? Use restricted actions? Yeah. Use restricted underscore actions. And then to that, we're going to set it to retro.actions. Let me open this up. Retro.actions. I think it's .filtered. Yeah, filtered. Okay. So this basically means that it's going to filter out the actions inside of this environment to only give us button combinations which are valid, rather than just having all of the multi-binary values available. So if I go and paste that there, that is all well and good. Cool. I think we're actually looking good now. So we've gone and specified our observation space, specified our action space. We've gone and created our game, and we've set use underscore restricted underscore actions to retro.actions.filtered, and filtered is in all caps. Cool. So that is our init method now done. So we've gone and inherited from our base class, which is up here. We've gone and set up our observation space. We've gone and set up our action space. We've gone and set up our game. We're looking good. Now, the next thing that we want to do is we want to go and set up our step function. So what it is that we're actually going to do actually, let's go and set up our reset function first. So rather than going to our step function, let's do reset. Let's bring that up and we'll come back to the others. Quickly hydrate. Now, the first thing, or the absolute basis of our reset method, is we need to return back our initial observations. Our observation is going to be set equal to self.game.reset. So we're just going to return back the initial observation. So return equals return obs in this particular case. So what do we write there? So OBS equals self.game.reset, which is going to return our first frame. And then what we're going to do is we're going to return our observation. Then what we also want to do is, because we're going to be calculating the frame delta, what we're going to want to do is at least set our initial previous frame, because our game delta, let me explain this, is going to be equal to the current frame minus the previous frame, right? And so as of right now, we're going to return the current frame, but we're also just initially as a placeholder, we're going to set our previous frame equal to this observation, this over here. So self.current previous frame equals OBS. And then what we also need to do is eventually we're going to need to pre-process this as well. So pre-process, we'll come back to this once we've written our pre-process method over here. Okay, so we have we've gone and returned our current observation. We've gone and set our previous frame equal to the current observation, or effectively our first frame. what we also need to do is create a variable for the score, because we're going to want to calculate the delta or the change in our score as well. Because when our basic info variable, which you saw from over here, is going to return this score, but this is the current score overall, so it's cumulative. We want to return the change in the score as our reward function. So we're going to create an initial variable to capture that. So we're just going to set it equal to self.score, and we'll set it to 0 initially. So create a placeholder attribute, or create, it's not really a placeholder, create an attribute to hold the score delta. Okay, and then all we're going to be doing is returning our observation. So I think that is our reset method now done. So what are we doing there? So we're initially returning the first frame. We are then pre-processing, or we're going to pre-process eventually. Let's just write to do. We are then going to return, set our previous frame equal to the current frame. This is just for the first initial part of the game. We are then going to create an attribute to hold the score delta, and we're going to return our observation. Okay, I think that's looking good. I just realized we also need a function to close. So def close. We'll come back to that. Okay, so that is our init method done. That is the majority of our reset method done. What we also now need to do, I think let's go on ahead and finish off our preprocess method, or do our preprocess method. So this is going to clean stuff up, and it's just going to make life a little bit easier once we get to our step method, which is probably the most hardcore of them all. Cool. So our preprocess method really needs to do 3 things. And remember, where are we? So observation preprocess. So we need to grayscale, and then we need to resize the frame so we have less pixels. The frame delta is going to be handled inside of the step method, so we don't need to do that just yet. So really just grayscale, and we need to resize. So let's go on ahead and do that. Let's actually just take a look. So we've actually gone and done the filter action bit. So this bit over here, filter action, now done. Cool. Because remember, we went and set use restricted actions equal to retro.actions.filters. So that bit's done. What we now need to do is go on ahead and pre-process. Let's just quickly take a look at what we said. We'd grayscale, and then we'd resize. Okay, so the first thing that we're going to do is we're going to grayscale. So let's create a new variable called gray. We're going to set that equal to cv2.cvt color, and we're going to pass through our observation. And we're going to pass through the color conversion code from OpenCV. So that will be cv2.color, and it should be BGR to gray. Yeah. So that is our grayscaled image. So this is grayscaling. Then the next thing that we want to do is resize it. And then in order to do this, we are going to create a new variable. I'm just going to call it resize. And then we're going to call cv2.resize, pass through gray, and then pass through the new shape that we want. So we want it to be, 84 by 84 by 1. And then we're going to type in cv2.intercubic. I think that should work. Yeah, let's just try that for now. So what have we gone and done? So we've gone and grayscaled it. So we've used cv2.cvt color, and we're grayscaling it using color BGR to gray. We've resized it using cv2.resize. So we're going to return a shape of 84 by 84 by 1. And then we've returned resize, which is that over there. All right, let's actually just test this out. I want to make sure that this is going to work. Actually, this should actually say interpolation equals that. So let's go and recreate it outside of this. So we've gone, what have we gone and done? So we've gone and grayscaled, and we've gone and resized. So first things first, I'm just going to import matplotlib. Matplotlib for plotting the image from matplotlib import pyplot as plt. What are we going to do? All right, so let's grab our last observation from our game. So remember, this was coming from over here. So if I type in plot.imshow and then pass through that observation, that's our last game frame, right? Then first thing that we're going to do is we're going to grayscale it. So if I type in gray equals cv2.cvt color, pass through that observation, set it equal to cv2.color underscore bgr to rgb. Yeah, that's fine. Okay, then if I go and pass through gray in here. Okay, so it's definitely changed color. The reason you're getting this bluish tinge is because OpenCV references colors in BGR, Matplotlib references them in RGB. So to actually be able to see this gray value in its true color, if I pass through gray here, let me actually type it out so you can see what I'm doing. So what we need to do is we need to convert this from BGR, or actually this should be gray, BGR to gray, my bad. So, all right, so that's the change color. Now, in order to get rid of this weird colorization or this weird coloration over here, not colorization, we can convert it from BGR to RGB. So if I type in cv2.color, and we don't need to do this inside of our pre-processing, it should be fine. So color equals cv2.color underscore RGB to, BGR. BGR being blue, green, red to RGB, red, green, blue. Boom. Okay, so you can see that that is definitely gray now. So we've gone and effectively done that. Let's just double check that we've got this code. So cv2.cvd color obs and then color to bg to gray. All right, so that bit's fine. Let's copy the next bit. So the cv2.resize. So if we are going to call it resize equals, and we're going to set that equal to cv2.resize, we're passing through this gray observation. We're reshaping it to be 84 by 1, and interpolation is going to be into cubic. All right, let's pass this resize. We need to run this, then this resize. Am I typing that wrong? Hold on, can't pass desize expected sequence length. All right, so let's get rid of this one. Okay, so then if I pass through resize here. Okay, so we've definitely gone and resized it. What would be the shape of this image now? Resize. Okay, so that's not going to work. So we're going to probably need to use NumPy to effectively encapsulate it in another array. But at least we know that we've gone and resized that image. So that is effectively what our reinforcement learning agent is going to get back to try to learn to play the game. So not super grainy. So I wonder if we probably could play around with this or change the shape of the environment later on. But keep in mind that our game is actually seeing every single individual pixel. So it's seeing a lot more than what we're seeing, at least initially here. Okay, so we know that we need to go and change this. So this should be that. So we're getting rid of the 1. And then what we're going to do is we're just going to ensure that we have a channels value. So add the channels value. And then for this, we're going to use NumPy channels. So np.reshape, pass through resize, and then we're going to set it equal to 84 by 84 by 1. That should be okay. And then return channels. Let's copy this. Paste this up here, see if this works. So if I go and paste that, call it channels or channel. Check the shape, channel. Okay, so we're 84 by 1. We go and pass through channel. This might throw errors. Okay, so that's perfectly fine. So we've got our shape successfully done. So we've got that final channel. We need this because this is the way that Stable Baselines, which is our reinforcement learning package, expects our observation. So that's looking all good. And we've got our frame successfully working. That is looking fine. Okay, so we've gone and let's go back and take a look at what we've written. So we've gone and grayscaled, and this is our pre-process function, remember? So we're going to need to go and use this inside of our reset method. So we're first up grayscaling. So I've written gray equals cv2.cvt color. To that, we're passing through our base observation, and then we're changing the color code. So we're going from whatever it is initially to color underscore BGR to gray. Then we're resizing it. So this is cutting down the number of pixels that our reinforcement learning model needs to go and train on. And I've set that equal to resize equals cv2.resize, passing through this gray value, and then we're converting it to 84 by 84 pixels. And we're setting our interpolation to cv2 to CV2, and we're setting our interpolation to cv2.inter_cubic. Then we're adding our channels value. So we're in channels equals np.reshape, and we're passing through our resize value, and we're setting that equal to 84 by 84 by 1. So we get that final channels value. And then to that, we're going to be returning that final channels value down here. So then what we can do is back inside of our reset method, we can run set our observation equal to self.preprocess, and then pass through the initial observation. So that is now a pre-process value that we're going to be returning back. Cool. I think that's looking good. There's one other thing that we also need to do in here. Because we've gone and reshaped our observation space, we need to go into our init method and change it up here. So rather than it being 200 by 256 by 3, we're going to be setting it to 84 by 84 by 1. So this is going to be 84 by 84 by 1. Cool. That is, what have we gone and done there? So we've now gone and finished off our init method. We don't need to come back to that. We've gone and done our reset method. We don't need to come back to that. And we've gone and done our pre-process method. So we don't need to come back to that. All right, let's take a look. We can actually delete this stuff here. Keep it nice and clean because we're going to be writing a ton of code. Okay, so we've gone and done the grayscale bit. So that's done. We've gone and done the resizing. That's done. We still need to do the frame delta, and we still need to do the reward function. So that is going to be done inside of the step method. Cool. Okay, so let's go to our step method. So first things first, we are going to take a step in our environment. So take a step. So we can run what we're going to get back. We're going to get back our observation, our reward, whether or not we're done, and any environment info. And then we're going to set that equal to self.game.step, and then we're going to pass through our action to that. So that will effectively allow us to use the base environment or whatever our game is up here, this line here, to take a step. And then to that, we're going to be getting back our unprocessed observation, our unprocessed reward, our done, whether or not we're completed, and our info value. So based on that, the next thing that we probably want to do is process our observation. So let's go ahead and do that. So obs equals self.preprocess, PROCESS, and then pass through this observation. So this over here. So that's going to take it down from the 200 by 256 by 3 to the 84 by 84 by 1. Okay, then the next thing that we're going to do is actually calculate our frame delta. So frame delta. Okay, so this is what we were describing over here. So we're going to take the current frame and subtract the previous frame so we can see pixel change. Okay, so we are going to, so let's go create a new variable, frame delta. And we're going to set that equal to the observation minus self dot, what is it, previous frame? Yeah, previous frame was our attribute from reset. And then we're going to set self dot previous frame equal to the current observation, right? So this means that we're going to be taking the frame delta. So we're going to take our current observation or current pre-processed observation, and we're going to subtract the previous frame. And then we're then going to set the previous frame equal to the current observation so that when we go and take our next step, we're going to be taking that observation as the last one. Cool. So that is our frame delta now sorted. There is one last thing that we need to do, and we need to go and reshape the reward function. So reshape the reward function. And this one's relatively straightforward. So we can go reward equals info, and we're going to grab the score value. So if we go and take a look at our info dictionary, we're going to get all of these values. What we want back is the score, which is this over here. And because it's just a dictionary, we can just use our key to grab it. So 17,200 was that last value. So we are going to get the info value from here. We're going to grab the score, and we need, because we want the change, right? We don't want the final score. We want the change. So we can subtract our self.score attribute from up here. Subtract self.score. We are setting this inside reset method. Okay, that's good. So info equals, so reward equals info, and then we're going to grab the score value. We're going to subtract the previous score. And then what we want to do is we want to reset the current score. So this means that we are going to be cumulatively calculating the delta. So self.score equals info score. Cool. And then we need to return a bunch of stuff because that's what the step method does. So return, we're going to return our frame delta. So this is going to be our pre-processed frames. Remember, we're going to take the current observation minus the previous observation. Remember, this is the current pre-processed observation. That sounded really confusing if somebody said, okay, so let me just quickly explain this flow. So we get the current frame, right? Get the current frame. We then pre-process it. So we go from 200 by 256 by 3 to, 84 by 1. What we're then doing is we're going to calculate the delta. So this is the change in pixels, which will be pixels, the current frame minus the last frame. And this shows us what pixels have changed between each one of those action steps, right? And that gives us a little bit more information, ideally. Okay, so, and that is what this frame delta value is over here. And then these down here are just resetting our attribute. So we're now going to set the previous frame to the one that we just saw, and we're going to set the score equal to the one that we just grabbed. Cool. So that's our frame delta. We then want to return our reward, and we're going to return the done value and the info value as per usual. No change there. Okay, I think that's our step method done. So we've gone and taken a step, we've gone and pre-processed it, we've gone and calculated the frame delta, reset our attribute, calculated the reward as the score delta, and we've gone and reset our score parameter. And we're returning all of that. Okay, we're looking good. Now, the last thing that we need to do in order to finish this environment, we've done a ton of stuff in here, is we need to go and set the render parameter. And so to that, that's expecting, so again, this is just part of the environment checker. So we need to unpack any arguments and any keyword arguments from stable baselines, and we're going to set that equal to self.game.render. Get rid of that. That one's just pretty straightforward. So this basically just means that if we call render from our environment, we're going to render the game, right? No different to how we were running env.render. And then close is just, again, pretty straightforward, self.game.close. Okay, I think that is our pre-processed environment done. So we've got a ton of stuff there. And that's pretty common when you're dealing with really sophisticated environments like this, right? So we've gone and written 1, 2, 3, 4, 5, 6 different methods. So we've gone and done the init method, and in that we're setting our observation space and our action space. We're going and starting up our game. We went and wrote our reset method, and in that we are creating our initial observation. We're pre-processing it, and remember we've gone and done our pre-process method here. We're setting our previous frame equal to whatever we've just seen. We're initializing our score variable, and this is to hold our score delta. We've gone and done some pre-processing, which is going and grayscaling our image, resizing our image, and then reshaping it so we have a channels value at the end. We're then going and we've gone and redefined our step method. And for this, we're pre-processing, we're calculating the frame delta, and we are reshaping our reward function. And then our render method is pretty straightforward. It's just running self.game.render, and our close method is just running self.game.close. All of this code is going to be available inside of the GitHub repository below. So if you want to take this and try it out yourself, or you haven't captured maybe what I've said, this is all going to be available. But for now, we've actually got this up and running. So what we want to go on ahead and do is actually test it out. So let's go ahead and try this. So we've gone and done a lot of coding, and we haven't tested too much just yet, but we've gone and tested incrementally. So what we should probably do now is close down any environment that we had. And then, again, we're going to run env.close, and then we're going to create a new environment, and we're going to set that equal to Streetfighter, which should be this class over here. Are we expecting, and we're not expecting anything in the init method, so ideally this should run. Okay, no errors there. So env.observation space. So that looks like we're getting our observation space successfully. .sample. Cool, we're getting our values. .shape. So 84 by 84 by 1, 84 by 84 by 1. That's looking good. Let's take a look at our action space. right? So it's still this is not zoomed in enough. So we're getting our multi-binary space. Take a look at our shape. That's looking okay. Let's actually go and run it using this loop over here so we can actually see some stuff. So I'm going to grab the loop that we wrote inside of the first bit of stuff that we did for Hector. Now I'm just going to grab it again, but we're going to use our custom environment. So we are not actually going to see the pre-processed values because we are rendering separately to the pre-process. But if I go and run at least one bit of this, we should be able to get back the last frame. So let's actually test this out. Okay, so we should be able to just run this. We're not getting any renders back. Why is that? So save. Yeah, okay. I don't know what was going on there. Looks like it wasn't picking up our last environment and kicking off the render. But all I had to do to fix this, right, is I just went to my kernel, restarted it. So this would shut down any existing game frames. And then we can re-import retro in time, re-import the environment, re-import our class or recreate our class. And then if we go and create our Streetfighter, again, this is no other change. It's literally sometimes the retro environment gets hung up. And apart from restarting the kernel, I couldn't really find anything else to do to fix this, really. This is in the interest of being completely transparent and showing you how to actually get started with this. So if you just restart the kernel, if it hangs up and doesn't actually refresh, then you should be able to keep on going. So if I go and create the environment now, observation space looks fine. Action space looks fine. So this is our, what is this? This is our starting state, or this is our loop that we had initially right at the top, right? So if I go and bring this over to the side and run this, again, we get our little pop-up. But this is our pre-processed environment at the moment. Now you're seeing the ungrayscaled version because this is just using the base render class. But if you actually take a look, you can see that we're getting a lot more rewards now. So every time that Ryu scores a hit, we'll actually get some values because that means that our score is going to increment. So you can see that we got some scores there. All right, we should have got a score there. So you can see that he just hit pretty hard. I'm trying to see, and there's 1,000. Let's actually stop this so we can see our reward a little bit better. So let me scroll up. Well, let's actually check two things here. So let's actually check our last frame. So remember, if we take a look at our observation, so this observation value should be the pre-processed value. So if I type in plot.imshow, pass through, did we import matplotlib? We should have. Yeah, we've got that imported. So if I go and pass that through, that is our pre-processed observation, which in this particular case is just purple. Why is that? Let's try that. Obs equals env.reset. Right, so that is returning the appropriate value, but what's happening here? We go and take a step. Let's copy this. Our observation is returning pure purple, which doesn't look all that right. Oh, okay. No, we're getting the frame delta, right? So you can see that right now, if nothing else in the frame changes, then we're just going to be returning back a black value. So hold on, let's go and this is okay. So if we type in env cv2.cvt color, and then we're going to pass through cv2.color underscore bgr to RGB, bgr to RGB, yes. Close that. Right, okay, so it is only seeing the pixel values that have changed. So if we keep going and running this, right, so nothing has changed when we go and initiate, nothing has changed when we go and initiate our environment. Go and take some steps now, right? So we can see the pixels that are changing. Right, so this is Ryu obviously moving. Again, we've got movement, no movement there. There we've got movement, so that is clearly our opponent. There we've got movement. Nothing. There we've got movement. So you can see that what we're actually returning back to our game is the pixel change. And this is the advantage of using frame delta, because it's not going to pick up all of this crap over here, which is just the health bars changing. We're actually going to see when our opponent is actually moving and use that to train our agent as to when and how to act appropriately. Cool. I think that is all well and good now. So it looks like we've gone and checked that. And this is really an important part of the process, actually going and validating that what our agent is actually seeing is going to make sense. So again, if we go and test this out, we can see what pixels are moving. I wonder whether or not just changing it and not using frame delta would have worked differently, because I did do this a bunch of times and when I was actually testing this out. But again, this is part of the process. We can see that occasionally we get some frame changes. What we're actually going to do when we actually go and train this is we're actually going to stack multiple of these frames together. So we're going to use frame stacking to be able to capture the changes as well. So we'll not only have the frame delta being captured, but we'll also have the last 4 frames being processed. So we'll actually see the movement on top of movement. So we'll have trajectories effectively. But in that particular case, that is the second thing that we told Hector we'd done. So we've gone and pre-processed our monster environment. So we went and wrote a ton of stuff there to be able to get us to this current state. And again, really important to actually go on ahead and check that your environment is actually working and that everything actually looks good. Let's actually just do one last thing. So if reward is greater than 0, then print reward. So let's actually just print it if it's greater than 0. So this should allow us to see, what we should see is that every time Ryu hits Guile, we see the value increment, because that's going to mean that our score up there increments. So let's try this. So if reward is greater than 0, yeah, this should make sense. Okay, so let's watch this. So right now, no change. Boom. All right, so we got some scores. Nothing. So we're not getting penalized for missing a hit. All right, there we got a score. So you can see that this is popping up here. Got some points. Blocking attacks would have been really interesting as well to reward that. Okay, but you can at least see that now we're actually getting some rewards specifically for when our agent actually takes away health from our opponent. So this is actually a good thing. And again, these are just random actions at the moment, so there's really, we shouldn't be expecting anything too great. Come on, do one. All right, we lost there. But you can at least see that our actions are at least corresponding to some sort of reward. So this is all looking good. Let's jump back over to Hector and show him how we're going in this particular case.
Alrighty, so that's the boring bit done, man. If it's so boring, why'd you bother? We got games to AI, man. I'm trying to make this PewDiePie money. Yeah, well, in this case, the AI or the reinforcement learning bit is the most interesting. But, a huge but. If you don't pre-process your data and get it ready for modeling, then legit, you may as well just throw the AI bit in the trash. Rubbish data is going to lead to sucky results every time. Alright, so you kind of have to do this. Yeah, but that's cool. I mean, it's time to start training our models anyway. We've gone and done the hard bit, now it's time to get into the interesting bit. In this case, we're actually going to train multiple models using hyperparameter tuning and pick the best one. Interesting. So you kind of tune it like you're tuning a radio to find the best station. Exactly. Once we've got a reasonable set of hyperparameters, we can fine tune from there. Let's do it.
AI ain't all sunshine and rainbows. It's a very mean and nasty place. You got to pre-process and work for them results. But we're done with that. So it is all sunshine and rainbows from now on. In order to train our models, we're going to be using OpTuner. This will allow us to train and tune at the same time. Think of hyperparameter tuning like tuning your car radio. You can tune certain parameters to improve the signal. For PPO, the parameters we'll be tuning are N steps, the number of frames to store in the buffer, gamma, which is the discount rate, the learning rate, which is pretty self-explanatory, clip range, so how much to clip our advantage by, and GAE lambda, the smoothing parameter. We can then save each model and reload the best one for fine tuning later on. Alrighty, so now that we've gone and pre-processed our environment, that is probably the hardest bit or the most coding intense bit now done. Now we've shown Hector that environment and we've sort of shown him how it works. Now the next thing that we're going to do is start training our model, but rather than just straight up training our model with hyperparameters that we've gone and defined, we're actually going to be doing a little bit of hyperparameter tuning. Now, hyperparameter tuning or hyperparameter optimization is super important when it comes to reinforcement learning because the algorithms can be a little bit finicky and can be very sensitive to different hyperparameters. So we're going to be doing a little bit of tuning. Now, in order to do this, we're going to need 3 libraries. We are going to need, or 3 modules. We're going to need PyTorch, so the underlying deep learning framework that Stable Baselines runs on. We're also going to need Stable Baselines, which is the package or library that we've done the majority of our reinforcement learning in. And then we're going to need Optuna. This is a new one that we haven't touched on yet, which is an optimization framework that works across a large number of algorithms, which definitely makes it a whole lot easier to actually go and hyperparameter tune. So I'm going to give you a little bit of an example as to how to actually go about doing this. Okay, so the first thing that we are going to do is install PyTorch. So I'm just going to head on over to the PyTorch website. So if you just go to pytorch.org, hit install, and then over here, you've got this little wizard. Again, I've shown this a few times. So if you just go to stable, whatever type of operating system you're running on, I'm going to be installing it using pip. We are installing it for Python, and I'm going to be doing it for CUDA 11.3. So if we just copy that command there, jump back into our notebook, hit exclamation mark, paste that in, and I'm just going to get rid of this 3. And if we go and run that, you can see PyTorch is all good and installed. I'm getting this warning, but that's fine. We can ignore that. All right, so that is the PyTorch bit installed. Now, the next thing that we need to do is install Stable Baselines 3, which is going to be the main reinforcement learning framework that we are going to be using in this particular case. So we're going to install that, and the installation is pretty straightforward. We just need to run this command here. So pip install stable-baselines 3 extra, and we're also going to be installing Optuna, which again is also pretty straightforward, which is just pip install Optuna. So we're going to be doing both of those in a single line. So we'll run pip install, and we'll run stable-baselines 3 extra. So if we copy that, paste that there, and we're going to go to Optuna, and we're going to copy that and paste that there. So the full line is exclamation mark pip install stable-baselines 3, and then inside of square brackets extra, and then with a space, we are going to be installing Optuna as well. So if we run that, that is Stable Baselines 3 and Optuna now installed. Let's just double check we don't have any errors. No, we just got a warning. Cool. So that's now installed. Okay, so now that we've gone and installed those 2 or those 3 libraries, the next thing that we need to do is actually go on ahead and import some dependencies. So let's go on ahead, import some dependencies, and then we'll be able to take a step back and take a look at what we've done. Okay, so those are our dependencies now imported. So we've gone and written 5 lines of code there, with the large majority of them coming from Stable Baselines 3. So the first one that we've gone and written, or the first line that we've gone and written, is import Optuna. So this is going to be importing the optimization framework, which is Optuna, which is what we've gone and imported here. And we're going to be using this to do our HPO. Then the next line that we've gone and imported is, or written, is from stable_baselines 3 import PPO. This is going to give us our PPO algorithm, or RL. And then the next 3 are really just, let's actually step through each one of these. So the cool thing about Stable Baselines 3 is that it actually has this method called evaluate policy, which allows us to test out and effectively calculate some KPIs for our specific algorithm attached to our environment. The method is called evaluate_policy, and that's exactly what we've imported that there. Now, the reason that we're going to be using this is that when we go and perform our hyperparameter optimization, we need some way to evaluate how well our agent is performing on that specific environment. We are going to be using the evaluate policy method to actually do that. So we've brought that in. So bring in eval policy method or metric calc. So the full line is from stable underscore baselines3.common.evaluation import evaluate underscore policy. Then the next line that we've written is monitor, or the next thing that we've brought in is the monitor. So import the SB3 monitor for logging. So the cool thing about the monitor is that when we actually wrap our environment inside of a vectorized wrapper, you don't by default you're not by default able to access the mean episode reward and mean episode length. By wrapping it inside of a monitor, we're able to use stable baselines to extract that out. And this is particularly useful if you're running multiple environments during training. So that is exactly what the monitor class does there. So the full line is from stable underscore baselines3.common.monitor import monitor, and the monitor is in capital to import that class. Then we've imported a couple of additional wrappers. So import the vec wrappers to vectorize and frame stack. So the next line that I've written is from stable underscore baselines3.common.vec_env import dummy vec env, comma vec frame stack. So dummy vec env wraps it's going to wrap our Streetfighter environment inside of a dummy vectorized wrapper. So this allows us to do some additional cool things with it. Namely, we are going to be stacking our frames. So we're going to be passing through 4 frames to our PPO algorithm to be able to give it some concept of time or transition. This is exactly the same thing that we did in the Mario tutorial to be able to get that effective trajectory or movement in terms of our game. So those are our dependencies now imported. So optuner, PPO, evaluate policy, then brought in the monitor class, dummy vec env, and vec frame stack. Cool. Now, the next thing that we need to do is we need to define a couple of directories. So we're going to define a log directory, and we're just going to set that equal to /logs. And we need an optimization directory as well. So this is where all of our saved optimization models are going to be saved. We're just going to name that opt. Now, the reason that the log directory is pretty self-explanatory. When we actually go and train, stable baselines 3 has the ability to log out to a TensorBoard log. I think you can also log out to 1DB, which is weights and biases. So that's another cool thing that you can take a look at as well. But the opt directory is the most important here. When we go and perform this hyperparameter optimization, I'm actually going to set it up so that it saves each model after every single trial, because that's what we're effectively going to be doing. This means that you'll actually be able to reload the model from that specific trial rather than having to go and train again all the way from scratch with those specific hyperparameters. So that's why we're setting these two up. So we're setting up a log directory, and that's going to go into logs, and an opt directory that's going to go into opt. And again, what I'm going to try to do is once I've gone and trained these models, I'll share the best weights that I've got as well and any specific hyperparameters that I use so you can pick it up and test it out yourself. But in this particular case, we've gone and set up our 2 directories. Okay, now the next thing that we need to do is actually set up our hyperparameter methods or functions in this particular case. So the first one that we're going to do is we're going to set up a function to return tested hyperparameters. Parameters. And we're also going to set one to run a training loop. Run a training loop and return mean reward. Return mean reward. Actually, I think it's just reward. Well, no, it's mean reward from the evaluate policy method. Okay, so the first thing that we need to do is we need to tell optuner what range of hyperparameters and what hyperparameters to actually tune. So what we can actually do is we can actually use some of the optuner methods. So there are a number of available. So if we actually go and take a look, so this is one example, right? So we're going to define an objective function, and through that, we're able to suggest certain hyperparameters that we actually want to use for our model. So you can suggest float. Let me see if there's the documentation or where the documentation is. So you've got the ability to suggest where is it? Optuner documentation. Here we go. So you've got a number of different types of ranges that you can actually suggest. So where is it? Suggest, let's try int. Here we go. It's under trial. So we're going to set up a set of trials, and each trial is going to have its own set of hyperparameters. Now, the nice thing is that you've got the ability to suggest a bunch of different hyperparameter types. So we can suggest categorical values, we can suggest a discrete uniform distribution, we can suggest float values, so values which have a trailing decimal place, integers, a log uniform distribution, and a uniform distribution. So we're going to use a bunch of these and set up our objective function, which is going to return these hyperparameters back. So the first thing that we need to do is define the objective function. Let's go ahead and do this, and we'll take a look. Okay, before we go any further, let's actually take a look at our template function that we've gone and defined. So I've written def optimize underscore PPO, so that's going to be the name of our function. This could just as easily be just a straight objective, or you could just name it objective, similar to what they've got in the documentation. So you can see that they've just written the function as being called objective. That is perfectly okay. You can name it whatever you want, because we're going to customize how it's called down here. So to that, we are going to pass through the trial. So the trial is going to be a specific pass through the hyperparameter optimization framework. And then once we pass through that trial, we are going to return back the hyperparameters that we want to use in our PPO model. Now, the hyperparameters that we're actually going to be tuning are the n steps value. So this is the number of frames, or the number of the number of frames that are actually stored within or used for one batch of training within our specific PPO algorithm. Gamma, which is the discount rate. So this discounts the future rewards that are attracted from the PPO model, or future rewards that are calculated as part of the PPO model. The learning rate, so how fast we tune our optimizer for the PPO algorithm. And this will train the, the critic and the actor neural networks. The clip range, so how much we want to clip or what the clipping parameter is for our advantage method or advantage value within the PPO algorithm. And GAE lambda, which is a smoothing parameter. Okay, I think it's a smoothing parameter. It's actually a specific parameter which is applied to when we actually go and calculate our advantage. So take a look at the Doom video. I explained that in a lot more detail. Okay, so now what we've gone and done, so we're going to return this dictionary. So you can see we've got some squiggly brackets, and we've got all of our keys that we're going to go on ahead and define. We're going to now specify what we want to return back as part of this trial. Do we want to return back integers? Do we want to return back floats? Do we want to return back a log uniform distribution? So let's go on ahead and define these, and then we'll be able to wrap up this objective function. Okay, that is our objective function now defined. So we've gone and specified the ranges and the hyperparameters that we actually want to return back. So for n steps, we're going to write trial.suggestInt. So we want to return an integer for our n steps value. And the range that we're going to be tuning is 2048 to 8192. Now, you want this to be a factor of 64 or a factor of your mini batch size that you're using for the PPO algorithm. By default, for PPO, that is going to be, where was it? I believe it's 64. Yeah, the batch size is 64. So you want it to be some factor of that. Now, by default, I haven't actually worked out how to get PPO, or how to get Optuner to return a specific factor. So you are going to get some warnings when you go and train. But you know that 2048 divided by 64, there's going to be no remainders. Likewise, 8192 divided by 64, there's no remainders. So we're okay there. Now, the full line is trial.suggest_int. The first value is the parameter that we're actually going to be tuning, so n_steps. And then the low value, so 2048, and the high value, 8192. Then we've gone and done something similar. for gamma, except here we're going to be suggesting a log uniform distribution. So trial.suggest underscore log uniform. We're passing through our hyperparameter gamma, which has our discount factor. Then the low value is going to be 0.8, high value is 0.9999. Then our learning rate, again, we're going to use the log uniform distribution or sampling distribution. Here we'll pass through our hyperparameter, which is the learning rate. Low value is going to be 1e negative 5, high value is going to be 1e negative 4. Then again, we're actually suggesting uniform distribution here. So trial.suggest uniform for our clip range. And the low value is going to be 0.1, high value 0.4. Similar for GAE lambda, with our low value being 0.8 and our high value being 0.99. Now, what's going to happen is that when we go and train, we're actually going to get a set of best parameters. So we'll actually be able to get back what the best set of parameters is for our specific algorithm. So we'll actually be able to write study.bestparams, and we'll actually be able to get that back and pass it through to our algorithm to fine tune down here. Cool. So that is our objective function now done and dusted. Now, the next thing that we need to do is actually set up our study, or effectively our experiment. So that's exactly what we are going to do here. Now, this code is probably going to be relatively familiar to you if you've seen one of the other reinforcement learning tutorials. But again, I'm going to go through it all in a reasonable amount of detail so you can see that. So let's go on ahead, suggest or create our template function, and then we'll go from there. Okay, so that is our template function now created. Now, again, I haven't really done too much here. I've just started setting this up. So I've written DEF to define a new method, and then I've written or define a new function. So DEF and then optimize underscore agent. Then we're going to be passing through our trial. Got a colon to wrap up that function definition. And then we're going to run a try except loop. So certain parameters are going to throw errors, and I don't want this to throw out our entire training run. So having a try except loop here is going to effectively allow you to run this without the worry that this is all going to go to crap overnight while you're training it. Because ideally you want to be able to give this a reasonable amount of time to train. So I've trained for 3 days, I've trained for 4 days before. We're going to keep this one short, but I'm going to tell you how to extend this further if you want to go harder. So what we now need to do is write up our training loop inside of this little section here. So we're going to define a new environment. We are going to wrap it inside of our monitor, wrap it inside of our dummy vec environment, and wrap it inside of our vec frame stack environment. So this will give us the stacked observations. We'll create a PPO algorithm. We'll train it for X number of time steps, and then we're going to run it through our evaluate policy method to get our episode reward back. And based on that episode reward, OpTuner is going to find the best set of hyperparameters to train or tune or use to actually go on ahead and tune our specific model going forward. Okay, so let's go on ahead and write up our optimize agent method function. I keep saying method. It's not a method if it's not inside of a class. Okay, our function. Let's go on ahead and do this. Okay, that is the beginnings of our optimize agent function now defined. So I've gone and written 5 lines of code there. There's probably one which is relatively new that we haven't actually gone through before. So let's actually walk through this. So first up, what we're going to do is we are going to get the set of hyperparameters from our objective method, which is this over here. Now to do this, we're going to write model underscore params, which is going to be our variable that we're storing those in. We're going to set that equal to optimize underscore PPO, and then we're going to be passing through our trial. So what we're actually going to get back from here is just a dictionary of these hyperparameters. So we're going to get a value for n steps, value for gamma, value for the learning rate, value for the clip range, value for GAE lambda. So it's a little bit different to how you might actually go about hyperparameter tuning when you're using like grid search CV and scikit-learn. We're actually going to be returning a specific dictionary back, and then we use that dictionary to pass it through to our algorithm. That's effectively how we're going to be able to do it using stable baselines 3. So this is just going to be a dictionary back. So let's actually test this out. So if we go and run that, we actually need to define that, and let's pass through trial 1. Is that going to work? into object has no attribute. Well, we're not actually passing through our trial. So no, it's not going to work outside of that loop. That's perfectly fine. We're going to run it down here anyway. So we'll actually create a trial using the optuner method anyway. So let's hold off for now and I'll actually show you this working. Okay, then the next thing that we've actually gone and done is we've gone and created our environment. So we've gone and written 4 lines there. So we've gone and created a new Streetfighter environment, nothing crazy there. We've gone and wrapped it inside of a monitor. This one is a little bit newer. So this is what allows us to extract our mean episode reward and mean episode length from a vectorized environment, which is what we're going to be doing down here. So env equals monitor, and then we're passing our environment to that. So this is going into here. And then we're going to be specifying where our monitor values are going to go or be exported out to, which in this case is going to be our log directory. And then we're wrapping it inside of a dummy vec env wrapper. So again, env equals dummy vec env. We're passing through our function creator, so lambda colon env. Then we're frame stacking it. So env equals vec frame stack, passing that into here. We're going to stack 4 different frames. And remember, we set up our channel, our environment so that we actually had a channels order or a channel. And this is, remember, when we went and defined our shape inside of our Streetfighter class, we had that up here. Okay, I think that is good for that. So we've gone and grabbed our hyperparameters, we've gone and created our environment. The next thing that we probably need to do is set up our PPO model and then kick off training, then calculate our mean episode reward. So let's go on ahead and do this. Okay, that is the, or at least part of the next bit of the optimization method or function actually gone and written. Keep saying method anyway, whatever. Okay, so what I've gone and done is I've gone and created a new instance of our PPO model. So I've written model equals PPO. And then to that, we're passing through that we want to use a CNN policy. So we're going to be passing through images as observations so we can use the CNN policy. Then to that, we are going to be passing through our vectorized environment, which is that over there. We're specifying where we want to log out our TensorBoard logs to. So TensorBoard underscore log equals logdir. We don't want it to be verbose. Otherwise, you're going to get a ton of information blurted out to you. So I've set verbose equals 0. And then this is the most important bit. So let me make sure that's in the center of the screen so you can see it. We are unpacking the model parameters that we're getting from Optuner and passing that through to our algorithm. So this bit that I'm showing on the screen, super important, right? That's the bit that allows us to do our hyperparameter optimization. So we actually take the model parameters that our objective function has actually gone and generated, so this over here, and we're passing it to our PPO model over here. I'm just making sure my head doesn't block that. So we need to get that value and we need to pass it through to our PPO algo. And again, this code is going to be available in the description below. Okay, so now that we've gone and done that, we can then go and train our model. So model.learn, and we've specified total underscore time steps equals 100,000. Now, you could do 100K, but keep in mind that this is going to take quite a while to train. So I've left it as 100K for now, but we might change it to actually train a little bit faster so I can show you some results. So let's set it to actually 30K for now. But when I actually went and did this, let me actually add a comment. So when I did this for a production-like model, I think I ended up doing it for 100,000, at least initially. And I think I did 100 individual runs. So I did 100 iterations of this hyperparameter tuning. We're going to set it to 30K so we've got a little bit more speed, so that it doesn't need to train as long. But ideally, you want to let this train for longer if possible, because that's going to give you a much better result. So we are going to let total time steps be 30K. Then we need to evaluate our model. So I've written mean underscore reward, comma, and then underscore. So we're just unpacking the results that we get back from our evaluate policy method. And then I've written evaluate underscore policy. So this is from this method up here, or this function that we've actually gotten imported. Passing through our model, which is what we had over here, passing through our environment, which is what we had over here, and then how many games we want to play. So n underscore eval episodes equals 5. So we want to play or evaluate our model on 5 different games. Then I'm closing down our environment and also returning our mean reward. So return mean underscore reward. Now, you will see some people referencing when you're using Optuna that you need to return the negative reward, but that is perfectly fine because we're going to change something when we actually go and train or start up our hyper optimization loop so that we can return the positive reward. And the reason that we're doing this is we want to optimize to get the highest possible reward possible. So when we actually go and kick off our training loop or our HPO loop, we're actually going to set the direction to maximize. So that's a key thing that we need to change. But there's one last thing that we actually need to do in here. So we actually want to save our best model as well. So rather than just having or actually just getting the best parameters back, we actually want to save each one of these models so we can come back to them if we want to pick them up. So we can define our save path. And we are going to save it in os.path.join. We're going to save it inside of our opt directory, and we are going to name it trial and then best underscore model format and then trial.number. So this is the reason that when we went and actually ran our optimized PPO method, we were getting some errors, because when we actually create our trial, I believe we're creating a trial instance. Yeah, so this is what is actually returned back from our Optuna method, hence why passing through an integer is not going to work. I don't know why I went and did that, but anyway, that shows you what not to do in this particular case. So what we're specifying here is what we want our save path to be. So we've written save underscore path and we've set that equal to os.path.join, pass through our opt directory, which is what we defined over here. And then I've gone and done a little bit of string formatting. So trial underscore and then set a squiggly brackets underscore best underscore model dot format. And then to that, we are going to pass through the trial number. So this is actually going to return what specific trial we're up to. Think of your trial as one pass through the hyper optimization framework. You can actually set this when we create our study. And what we also want to do is we want to save down our model. So we can write model.save and then pass through our save path. So that is going to save the model for the PPO instance at that particular point in time. So we can actually come back and reload it if we wanted to. And then we're going to return our mean reward. Cool. That is that done. Then if we get any errors, we're just going to return minus 1,000. So this means that rather than it throwing up errors and breaking our hyper optimization loop, we're actually going to be able to keep on going. And this is particularly important. So when I was doing this, like I'd be training and I'd kick off training the night before, come back in the morning and realize it had only run for 10 minutes. And it had been because there's a specific hyperparameter which had thrown an error. And rather than actually continuing training, the whole loop stopped. So this is a good thing to know. And this is the reason why I've gone and implemented this. Otherwise, it's a massive pain in the ass because you come back the next morning, it's not trained and you're like, I wanted to actually go and test this out. So that's why I've done that there. Okay. Let's take a step back so we can see this from a bird's eye view. So we've gone and written two main functions. So we've gone and defined our objective function, which is actually going to return back our different hyperparameters. So we're going to get a dictionary back with n steps, gamma, learning rate, clip range, GAE, gamma. And then we've gone and defined our hyper optimization function, which is called def optimize underscore agent. To that, we're going to be passing through the trial that we create from Optuna. And then we've gone and done a bunch of stuff in there. So first up, we go and get our model parameters from this objective function over here. Then we create our environment. There's nothing crazy happening there. We create a new Streetfighter environment, set up our monitor. We then wrap it inside of a dummy vec environment and frame stack it. We then create our algorithm. So remember, we're going to create a new instance of the PPO algo. Pass through that we want to use the CNN policy, the environment, and all of those other bits. And the most important bit is passing through this model parameter or model params dictionary here. So this is going to unpack it and push through the specific hyperparameters that we want into our algo. Then we're specifying how long we want to train for. So in this case, 30,000 steps is not long at all. Full disclosure, that is really, really short, particularly when training a reinforcement learning agent. Last night, I actually trained something else and I trained it for 5.5 million steps. So 30K, very, very short. So it's probably not going to give you the best example of actually hyperparameter tuning, but I'm sort of giving you the framework and then I'll show you final results later on, a little bit later. But ideally, I'd set this to 100K to actually be able to get some valid results. But I'll show you what it looks like at 30K anyway. Okay, and then we're evaluating our model. So we're using the evaluate policy method for that. We're specifying where we want to save our trained model to using a model.save, which is going to be using this instance to save it down. And then we're going to be returning our mean reward, which we get back from our eval policy method. And if we get any errors, we're just going to return back 1,000. So I think that is that done now. So if we save that, let's go and kick that off. So that is probably all of the hard work done when it comes to hyperparameter tuning. And key thing to note, if you wanted to go do this for different RL algorithms like DQN or SAC or some of the others that are available inside of stable baselines, so you know that you've got a whole bunch of others over here, you're going to need to change which hyperparameters you return from this objective function. If you'd like to see me doing some HPO on some of those, let me know in the comments below. Okay, this has been a lot of coding to get to this point. So let's go on ahead and actually kick this off. So there's only 2 more lines that we need to write, and these are going and kicking off our study or our experiment and then training. Okay, those are our last 2 lines done. So the first one is creating the experiment, or in this case, they call it a study, same sort of thing. So over in study equals optuna.create_study. And then this is the important bit. And so remember, I told you that we're specifying or returning a positive value. If we are going to be doing that, we need to make sure that we set the direction that we want to maximize, or the direction that we actually optimize to be maximized. So I've passed through direction equals and then maximize over here. By default, I think this is going to be minimize if you don't actually go and override this when you create the study. Then we're actually going on ahead and optimizing. So over in study.optimize, pass through the optimize agent method or function from over here. God, that's driving me insane that I keep saying that wrong. Anyway, and then we are going and specifying how many trials we want to run. So this is effectively how many different sets of hyperparameters we're going to tune or pass through our PPO agent. So I've specified 10 here. When I actually went and did this properly, or outside of this, which obviously takes quite a fair bit of time, I set this to 100. So what I had originally, these are the 2 things that I changed between this tutorial and actually going and doing this for real. So I had model.learn set to 100,000. So I actually trained for 100 time steps. And I went through 100 different trials. So I trained for a lot longer. That took me on the GPU that I'm using, which is a 2070 Super. That took me, I think, 22 hours. So again, it's going to take a bit of time if you're going to do this properly or completely from scratch. But in the interest of showing you this in a timely manner and not taking 22 hours to make this tutorial, I'm going to show you it a little bit faster. So we've written study.optimize, pass through our optimize agent function, function. And then we've specified how many trials we want to run. So n_trials, set that equal to 10, and then set n_jobs equal to 1. I think this is going to be deprecated soon, but this basically defines how many parallel environments to train at the same time. Because Gym Retro by default isn't up for parallelization, it's going to throw errors if you set this to any higher than 1. But if you were to do this for, what's a good example? If you're going to go and do this for Doom, or if you're going to do it for, I think it might work on Mario as well. Maybe. Anyway, if you were going to go and do it on those environments, you could set this to a higher value, and this would actually train or run through multiple trials at the same time. So if I set n jobs to 12 and we're running 10 trials, well, it's going to be doing them, all of them at the same time, right? We're going to set it to 1 for now. So, okay, so that is our hyperparameter bit. Now up and running. So what have we gone and done? So we've gone and installed PyTorch, installed stable baselines 3 and Optuna, imported our dependencies, defined our logdir and our opdir, define our objective function, which is going to return back our hyperparameters, and then set up our optimize agent function. Yes. Okay. And then we've got 2 lines here to actually kick off that hyperparameter optimization. So let's start this, see if we get any errors. Okay, so this is looking okay. So if you get anything which says, if you get the error about having multiple environments running at the same time and you can only run one emulator, you know what to do. You just shut down the environment, env.close. If you get any other errors or stuff which throws out or blows out of proportion, let me know in the comments below and I'll see if I can help you out. But this is good. So if you get this green information block, that basically tells you when your training has started. And this basically said a new study is created in memory with name, whatever. This user warning here is, remember how I said that when you actually specify the end steps parameter, it needs to be a factor of the mini batch size, which is what we had over here, right? If we take a look at this error, it's saying that we've gone and specified end steps as 4083. This is not going to work in here. Let me just quickly create a new notebook. If I go and pass through, there's no kernel. Let's set a kernel, change kernel. We'll just set that to Python 3 for now. Because we've got this set to 4083, 4083 divided by 64, we've got a remainder, which is basically what it's saying is the last mini batch, when it actually goes and divides that 4083 into individual mini batches, is not going to be a full mini batch. So it's going to be 51 frames. That's basically saying that it's not a specific error, but the last one's going to be truncated, which you can see over here. All right, cool. No need to worry. We're just hyperparameter tuning at the moment. But ideally, if you find out how to actually specify a specific factor over in here, let me know, because I'd love to actually get an idea of how to actually do that properly. You could actually, I wonder if you could just return back a specific value and then multiply it by 64. That might be one way to do it. I wonder if that messes around with Optuner. Anyway, that's the explaining that particular error there. All right, so what we're going to do is we're going to let this kick off and train. So this is going to train for 30,000 steps multiplied by 10 trials. So in total, we should be training for 300,000 steps. We'll get back 10 different models as a result of this. And each one of those models is going to be stored. Let me zoom in. It's going to be stored inside of our Sonic folder. I'm still laughing about that. It'll create a new folder called, what it'll be called? It'll be called opt. And inside of that opt folder, you'll actually be able to see each one of those train models. So I've got some extra notebooks in there. I'll give you those as well in the GitHub repository. So I actually set up, I think last night, I actually went and created a new sort of pipeline without the delta training, because you saw that we weren't getting too many pixels back. So maybe that might have thrown off training. I wanted to test that out. And I've also gone and got some weights for that as well. So I'm going to share those with you in the GitHub description, which towards the end of the tutorial, you'll see that as well. Okay, that is all looking good right now. This untitled one here is just what we've gone and created here. We can go and delete this. We don't need this. We can delete untitled. Get rid of that. Okay, so for now, we're going to let this go on ahead and train, and eventually you'll get back a value which says a trial is gone and finished, and the mean episode reward for that is X, Y, and Z, blah, 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 blah. Okay, we're going to let that train, and then we'll be back once it's done, and we'll be able to take a look at how to use it going forward.
A little longer than a few minutes later.
All right, guys, so I just got the first set of results back, and I realized that we've actually got an error here. So what's actually happened is, and the reason that I've picked this up, so you can see that we've got trial 0 finished with a value of minus 1,000 and these parameters. Now, I'm pretty sure that the actual loop works, but what is getting, or what is throwing a specific error is that we haven't actually imported the OS value. So let's actually just quickly double check this. So if I go into the folder, so that hasn't created the optimization folder. So if I go and run this line here, I'm pretty sure this is going to throw an error. Let me just pass through a random number there. Okay, so OS is not defined. So because we've got a try-catch loop that's going to not actually train anything. So in this particular case, I've stopped it early to actually be able to go and fix this. So let's just import OS. Import OS to deal with file paths. Import OS. Let's make sure this runs. Okay, so that looks okay. Okay, that's looking good. Now, this might throw some errors. So before we go and run it inside of the try-catch loop, let's actually try running it without that. Just to make sure this actually runs successfully. And let's just set the total time steps to, I don't know, like 300 for now. Just to make sure that this is actually going to run, because the last thing that you want to do is kick it off and again, it not actually run. So I'm going to set it to 300 over here temporarily. And we're just going to set end trials to 1 for now. Let's just make sure at least one iteration actually works. So again, we've got that truncation warning. That's okay for now. Okay. Let's actually stop this again. So let's run eval episodes to 1 as well. So rather than it training for or evaluating for 5 games, let's just allow it to evaluate for 1 game. Okay. All right. So here we've got an error. So trial 0 failed because of the following error. Runtime error, cannot create multiple emulator instances. That's okay. So we can run env.close to sort that one. And we don't have an environment specified. All right. Let's try running that again. It's looking positive so far. Let's see if it's gone and created our opt folder. Not yet.
5 minutes later.
Okay, that's looking good. So you can see that we've gone, 1 trial is finished. So this is just what you're expecting back. So trial 0 finished with a value of 2000. So that means that our average episode reward was 2000. And these parameters. So you can see that we've got our n steps value, our gamma value. It's probably, my head's probably going to cover that. N steps value, gamma value, learning rate, our clip range, our GAE, lambda. And what the cool thing about this is that you can get those best parameters back. So study.bestparams, that is going to return back that set of hyperparameters, which we can then go to pass through to our PPO model when we go and fine tune. So that sort of gives you an idea of how this is actually going to work. And then we've also got our fine-tune model or our hyperparameter tune model over here. So if we wanted to go and reload this, relatively straightforward, we can just run ppo.load, and then we pass through the full file path. So os.path.join. Is this zoomed in? Yeah, okay. os.path.join opt_dir, and then it's going to be the name of that file, which is going to be trial0.best. It should be a string.zip. What have we done there? Close that. That is our best model now loaded. So that sort of gives you like, and we can define model equals whatever. So that sort of gives you an idea of how to actually go and reload this, right? So that is our one hyperparameter model So that is one hyperparameter tuned model now reloaded. Now, in that particular case, we were just getting this set up, so we don't need to leave that as it is. All right, so let's go back and change some of these values. So we're going to set n trials to 10, and just to make sure everything works, let's close our environment. So env.close, delete env. Cool, it's fine. All right, now if we save that, what were we doing? So we're going to set total time steps 30,000, and we are going to set n eval episodes 5. So that means we're going to train for 30,000 time steps, or our model should see 30,000 frames in its lifetime, and we're going to go and evaluate it on 5 different games. And we are going to put our try-catch loop back and tab this in and uncomment that. I think that's looking good. All right, so what have we gone done? So we've gone and wrapped it inside of our try-catch loop or try-except loop, whatever we've got there. We've gone and set total time steps 30,000. We've gone and set n eval episodes to 5. I think that looks good. Go and run that. So that's fine. And then we've gone and set n trials back up to 10. Let's run that. Okay, so we don't have any errors there. Now we're going to let this run, and then we'll come back once that's over. We'll be able to get our best parameters back and all of our hyperparameter tuned models, and we should be good to go and jump back over to Hector eventually. So let's let this train, and I'll be back once that's done.
A little longer than a few minutes later.
Alrighty, so that is our first set of hyperparameter tuning now done. Now remember, this is sort of just to show you how you might go about doing this. If you were to do this properly, ideally what I'd recommend is play around with this total time steps number. So for a more bulletproof implementation, I'd suggest bumping this up to 100,000 or higher, or effectively how long you actually want to train the model for, and definitely increasing the number of eval episodes. This is going to ensure that you have a more even or smoother set of mean episode rewards rather than stuff that's just spiking out. But you can see that we are now done. So this block over here is now finished. Also, the other thing to note, increase the number of trials if you want to train or hyperparameter tune for longer as well. Okay, so this is looking good. So you can see for each trial, we're going to get a result back like this. We're also getting a ton of warnings, but that's fine. So in this particular case, trial 0 finished with a value of 15,400, pretty good. Trial 1 finished with a value of 4,500. What was the best? So trial 4 had 10,800. So this is me in episode 4. All right, trial 5 finished with 26,700. Now you can see that there is a huge difference. This might be because one particular game evaluation got a really high score and the others might have got low. So sometimes you need to be pretty careful, or you do need to be very careful when you are evaluating. Ideally, I'd recommend a higher number of eval episodes. That's going to ensure you have smoother results. But for this is looking pretty good. If we run study.bestparams, so what it's recommending is go with an n steps value of 7,516, gamma of 0.98 or 0.908, learning rate of 5.02 to the power of e negative 5, clip range of 0.39, GAE lambda of 0.837. So we've now actually got all of this back, and we've also got all of our trained models. So if we go into our Sonic folder, go into opt, we've got all of our hyperparameter tuned models. So we can actually pick up from our favorite one and go from there. So what was our best trial? So let's see if we get this from our study.best trial. So our best trial was a frozen trial number 5, which was this one here, right? So we can actually go back and load up trial number 5 now. So if we go ppo.load, trial 5, that is our best trial now loaded. Let's jump back over to Hector and see what he thinks.
The hyperparameter tuning is done and dusted. Want to check it out, or you want to see how to fine tune first? Run me through how you might go about fine tuning first. I mean, it's probably similar to what you did for Doom and Mario, right? Yeah, it's almost identical to how we ran it for those games. All right, yeah, let's see it.
In the spirit of modular code, aka me being lazy, we're going to reuse some of our previous training code. We're going to leverage the majority of the training pipeline from the Mario and Doom tutorials to fine-tune the model. All we really have to do is reload the weights from our best performing Optuner trial using ppo.load and train from there. Kind of like transfer learning, but for RL. So we've shown Hector that we can train our model. We haven't actually gone and evaluated it yet. So I know we're going to jump to fine-tuning, but I sort of wanted to show you the flow before we get to evaluation, and then we jump to the sexy results. So first up, what we're going to do is, as per usual, we're going to set up our callback. So we're going to need 2 key dependencies for that. So we're going to import, actually we've already got OS imported. We sorted that one out. We now need to import our base callback. So import base callback. And this is the exact same callback that we've used for Mario, that we've used for Doom, to be able to log out as we're going and fine tuning. So first up, let's import our base callback. Cool, that is our base callback imported. So I've gone and written one line there. So from stable_baselines3.common.callbacks import base callback. And again, I'm just going to use my template code here. I'm not going to go on ahead and write this completely from scratch. It's basically the exact same train and logging callback that I've used for Mario, for Doom, for pretty much all of the reinforcement learning I do. And this basically just logs out the entire saved model at a certain check frequency to a specific log path. So we're able to pass this through to our, when we actually go and kick off our training. But that's perfectly fine. We then need to set up where we're going to save these models. So remember, we've gone and saved our hyperparameter tuned models into the opt folder. My French coming out, into the opt folder, this one over here. Now, I'm probably going to set up a separate folder to actually go and fine tune this model. So let's create a checkpoint directory. Checkpoint directory. And we're going to set that equal to ./train/. And again, you can save this to wherever you want. I mean, this is just sort of my normal flow now that I've got a hyperparameter, I guess, pipeline. So opt gets saved into its own folder. So those are the Optuner trained models. And then I've got a separate set of models, or a separate set of folders for the fine-tuned models. Okay, so that is our checkpoint directory. Then we actually need to create an instance of this train and login callback. Okay, that is our train and login callback now set up. So I've just written callback equals train and login callback, specified our check frequency and where we want to save it to. So check frequency basically means that every 10,000 steps, we're going to save the model. The save path basically means that we're going to be saving our fine-tuned models into that particular folder there. So that is our callback now set up. So we've gone and set all that up. So we've gone and imported our base callback class. We've gone and set up our new train and login callback class, which is the exact same as what we've used in Doom, exact same as what we've used in Mario, and probably a whole bunch of other reinforcement learning projects that I've worked on. Checkpoint directory, and I think I got this off, I tweaked it a little bit, but I got it originally off somewhere off, where was it? Is that off the GitHub from Stable Baselines, I think 2. So if I find the source, I'll link to it in there. But I've used this a bunch of times now. Again, I didn't write this completely from scratch, but I've used it a ton of times. Okay, I'll see if I can find the original source as well, to give the people their due. Okay, so a little bit of coffee. What are we up to now? So we've gone and done that. Next thing that we need to do is train our model. So we can create a new instance, or we can probably just copy a lot of this code, right? So this is what we want to do. We want to create a new Streetfighter class or Streetfighter environment with our pre-processing. So we're going to create a Streetfighter class. We're going to wrap it in a monitor. We're going to dummy vectorize it. We're going to frame stack. Okay, no worries. Cool. We are then going to create a new instance of our PPO policy with one key tweak. So let's bring that over here. All right, then before we actually go and kick off the training, so I've just copied over the create environment section that we had from our hyperparameter tuning function. So we've gone and copied that over. We've gone and copied this over. There's two key things that we need to do here to make this a little bit, or to get this to work as we want, and specifically to fine tune. So first things first, we are going to we've created our environment. We are going to then get our model parameters that we actually want. So remember, we can access the best parameters from study.bestparams. So we've got all of those there. Now we're going to save this inside of a new variable called model params and set that equal to that. And so if we go to model parameters, now key thing is that this end steps value is still not a factor of 64. So if I go 7516 divided by 64, closest is 117. So we can just go 117. So what we're going to do is we're just going to overwrite this end steps value with 7488. So I'm just going to say model underscore params. And this basically means that we're not going to be truncating the mini batches each time we actually go and train. So we're going to avoid this big warning that you can see over here. So this big warning is purely because it's truncating those mini batches. Now we can avoid that effectively by just setting end steps to a value, which is a factor of our mini batch size. Cool. So we're going to do exactly that. So we're going to go model params, set n underscore steps equal to 7488. And now if we take a look at model params, cool, that's looking good. So we've got n steps set appropriately. We've got gamma, we've got our learning rate, we've got our clip range, we've got our GAE lambda. That's looking good. So now what we can do is we can go and create a new instance of our model. So I'm just going to set verbose equal to 1 here. So we do get all of that nice logging. And the training flow from here is pretty much the same as what you've seen before. So I'm not going to spend a ton of time on this, but I will show you how to do it. So we've got our model parameters over here. We've got our new model that we're going to create an instance of. So if I go and initialize that, so it's wrapped using the CUDA device. So that means we're going to be using our GPU. It's going to wrap it in vec transpose image. It's perfectly fine. The core difference though, however, is we want to load up our existing weights. So we can go model.load, and we're actually going to load the model that performed best. So we can grab this, paste that in here. So this is now going to load the best model, which is trial _5 _best _ model.zip. So this means that we're going to effectively perform, transfer learning. So we're going to load up our weights for this specific model and then kick off from there rather than having to start completely from scratch. So regardless of whether you do this for hyperparameter tuning or whether you do it for something completely different, this gives you a starting point, right? So rather than having to start completely from scratch, you can at least load up your best model parameters and load up your best set of model weights and then go from there. So I'm going to show you how to do this and then we'll jump over to evaluating the model and we'll go from there. But so for now, we're going to reload our model weights. That looks all successful. And then we can kick off our training. So let's say, for example, we just wanted to train for total time steps 30,000. Now, in this particular case, I'm going to keep this short and sharp because otherwise this tutorial is going to span out to like God knows how long. So what I actually ended up doing is I think I did model.learn. I went pretty long for this, but I monitored quite closely. So total time steps equal to, I think I ended up doing it for like 5 million. The other thing that I might have changed, that I changed in some of the other models that I've done before as well, is rather than leaving the learning rate at whatever it was, so what is it right now? 5 to the power of e -5. I think I ended up setting it way lower. So I set it to like 5e to the power of -7. So it was a significantly slower learning rate, but that allowed the model to actually train. So if you're getting poor performance, then those are a couple of things that you might want to take a look at as well. So training for significantly longer and then dropping your learning rate as well. So those are a couple of things that you can try. In this particular case, what have we gone and done? So we've gone and set up our base callback. Oh, we haven't actually associated our callback. So we need to do that as well. And we do that inside of model.learn. So we go callback equals callback. Okay, let's clean this up a little bit. So we've got our model parameters. So we can get rid of that. We don't need to visualize that. We don't need that. So we're doing this. And then we can take a look at model params. So we are first creating our callback and we've imported our base callback. We've created our train and logging callback class. We set up an instance of it. We then went and created a new instance of our environment, which is perfectly good. We then grabbed our best parameters. So study.bestparams is the best set of parameters that we got from our hyperparameter tuning from Optuna. We're then going and let's add some comments here. So set learning, set n _ steps to 7488 or a factor of 64. The other thing that I also recommended was changing the learning rate if you wanted to. Not necessarily mandatory, but this might help your performance. So what's recommended? 5e -7. That's another thing that you can try there. And then we're just visualizing our learning rate. So these are a couple of things that you can try. We can delete that. We can delete that. Okay, cool. Then we are creating a new instance of our PPO algorithm. So model equals PPO, CNN policy, EMB. So we're passing it through our environment, setting up our TensorBoard log directory. We're setting verbose equal to 1. So that means we'll actually be able to see the results as we're training. And then we're unpacking our model params, which is what we got from here. So these are the best set of parameters that Optuna found for us. We are then able to let's actually add some comments. So reload previous weights from HPO. So we're able to do that. And then we're able to kick off training. Kick off training. And again, if you wanted to train for longer, you definitely could. You could bump up total time steps to 5 million. And remember, we can actually visualize this in TensorBoard if we really wanted to as well. But for now, let's increase it 100K for now. So we're going to do 100K and then we'll be able to see some results of our training and then we'll be able to evaluate it. So let's run this. Okay, so this is going to be logging out to PPO 17. Now, another thing to keep in mind is I'll share the best weights that I've actually got as well inside of the GitHub repository. So if you want to try it out, you definitely can. All right, logging the PPO. Let's quickly take a look at how we can do that. So we just need to go into the directory that we're working in. Activate the environment. So I'm going to Sonic scripts activate, and then go into our log directory, which is where we set up. Where did we set this up? We set this up during hyperparameter tuning. So we set it up here. So it's going to be inside of logs, right? So if we go in, we're already inside of our logs directory, so we can just run tensorboard -- log here equals dot. The dot is really important because it's going to say open up, or our log directories are inside of the current folder. Cool. All right, so that's up and running now. So you can see it says tensorboard 2.7.0 running at localhost 6006. So that's running on that port. So I can grab that, bring it up, and you can see that this is now running. So all of the other ones that you can see that are already running there, or all of these little colored lines, let me just hide the two big boys. All of these colored lines are the lines that we had from doing our hyperparameter training. So if I set it to wall, you can actually see them as they're actually going off and kicking training off. Now, obviously you want to train this for a lot longer if you're going to go and do proper hyperparameter tuning, but that sort of gives you an idea of what it looks like. Now, I kept some of the other ones in there because I wanted to show you what a good training run looks like. So this is what I actually trained last night. So you can see that I trained the orange line, that was PPO1 over here. So I trained that for 5 million steps, and that got to a mean episode reward of, what was that, 7,000. So you can see that, nope, now it's disappeared. Cool, great. Yeah, no worries. I didn't want to see any. All right, it's down here. You can see that little pop up. It says, so inside of the value column, it says 7.020. Oh, actually, let's look at the top line. 7.336 to the, I wonder if my head's blocking that. 7.3368 to e to the power 4. So that was the best result. So about 7,336 in terms of our mean episode reward. What else? So you can see that was our mean episode reward in that particular case. So we are able to, or this sort of gives you an idea of what's possible. Now, in this particular case, I ran the first run. So that was PPO1. I ran that for 5 million steps. And then I ran PPO2 for about another 2 million steps. So that ended up, I think after this point here, I started to get a drop off and performance sort of degraded. But the model that you see here is probably the final one that I'll show in the results. And I'll share these weights as well, so you'll actually be able to pick these up. But you can see that, remember, we just kicked off our fine tuning. Okay, so what are we doing? So we're checking out how this model is performing. So we've got our episode length mean. This looks like it's dropping a little bit. Probably not. All right, it's up. Increase there. So let's actually let me quickly run you through how to interpret these results. So these two lines are probably the most important. So these give you the mean episode length. So 9 to the e to the power of 3, which is going to be, what is that, 9,000. Episode reward mean is 1.85 to the power of e4. So that's going to be, what, 18,500 in this particular case. And there's probably more decimal places. FPS is how fast our model is training. Iterations is how many times it's gone through, I think, the full epoch. How long it's trained for in terms of time, how long it's trained for in terms of time steps. Approx KL, this is, I can't remember what it is or what the K stands for, but it's the KL stands for. It's KL divergence. Can't remember the guy's name. Kullback-Leibler divergence. So this basically tells you how different your current policy is from the old policy. So it's a measure of how much your model is learning. Clip fraction is how much your PPO model is clipping the advantage, and I explained this inside of the Doom tutorial. Clip range is, I think, actually, I can't remember what clip range is. Clip fraction is the number of time. Range is the actual hyperparameter. So this is the value that we're actually going to be clipping from. So this is, it basically constrains the model. So rather than having huge changes, it actually tunes, or it actually reduces the range of the advantage that we're going to increase. Again, I explained that way more in the Doom tutorial. Entropy loss, that's if you've got shared weights, and that's going to impact or show you the value of the overall model loss. And again, I don't normally pay too much attention to this. I do pay a lot of attention to the policy gradient loss and the value loss. So these two are the ones that I pay attention to, as well as the explained variance. So this tells you how much your value network understands or is able to predict the future rewards. Learning rate in this particular case is a hyperparameter, and updates is just how many updates we've made to our neural networks. Okay, so you can see that is definitely off and training. And if we go into TensorBoard and you want to see those specific logs, it's going to be out to PPO 17. So if we scroll on down, PPO 17, that is this model training here. Right, so you can see our episode length mean, it's sort of varying. Episode reward mean, it's shooting up, and then it's sort of trending down. Based on this, I would be training for significantly longer. I wouldn't be stopping at 100K. You'd definitely go for a lot longer to see how this actually ends up performing. So the best one that I got yesterday, you can actually see it against it, right? So right now, look at our little, the dark red line in this particular case is the model that we're training right now. The blue and orange lines are where I got to last night. So based on this, you'd probably want to go on ahead and train for significantly longer, maybe up to 5 million steps in this particular case. But that gives you an idea of how to go on about and fine tune. So based on this, we're all looking pretty good. Let's jump back over to Hector and see what he thinks.
Alrighty, so we've done a bit of a run through on fine tuning. Ready to see some results? Hell yeah, walk me through it. We'll do. So we'll focus on the best trials from our hyperparameter tuning in this case. I'll give some commentary and we'll go from there. Yeah, cool.
Now that we've gone and trained our models, all that's left to do is test them out. It's game time, baby. Like all those fancy restaurants do, we're going to be doing this two ways. First up, we're going to use the evaluate policy method to return the mean episode reward. Then we can actually put it through the gauntlet by writing our own testing loop. Alrighty, so we've finished fine tuning our model in this particular case, and let's quickly take a look at our logs. So I'm just going to deactivate the old ones. So this is where we got to. Now it looks like we're starting to trend downwards. This might be an indication that we might want to actually slow down the learning rate in this particular case. So if we take a look, we're getting some spikes. And again, you'd probably want to hyperparameter tune for a lot longer rather than just doing the quick rough run that we ended up doing. I will share the final model weights with you as well, so you can try those out. Explain variance looks like it's heading upwards, so that's a good sign. Loss is trending downwards. Policy gradient loss. This should start oscillating a little bit more. So the fact that our value loss is just heading straight downwards maybe means that the learning rate is a little bit too far. So in this particular case, I'd probably hyperparameter tune for longer, and I'd also drop the learning rate. But if we benchmark this against the two models that I trained last night, you can see that there is really not too much comparison in terms of performance, right? So you'd actually want to go and train for significantly longer. So looks like our current model dropped off. If I zoom in on that, let me actually just make this bigger. Right, so based on that, looks like we're getting significant amounts of drop off. So definitely dropping the learning rate, training for a lot longer, and doing a little bit more hyperparameter tuning might yield some better results. In this particular case, training for significantly longer has yielded significantly better results based on what I was noticing yesterday. But this sort of gives you an idea of what to look for, how to actually go about training. If you need some help, hit me up in the comments below. But based on that, we have now satisfied Hector's requirement, and let's go on ahead and test this out. So I'm going to show you how to evaluate, and then we will also take a look at how to test out using our custom loop, which is pretty much very similar to what we did up here. It's slightly different. We can actually just copy this while we're at it. Come back down here, paste that in. But for now, let's go on ahead and evaluate our model first. So I'll show you how to do that, and then we'll be able to do our custom testing loop. So first things first, we want to load up our fine-tuned model. So if we go into where we've actually gone and trained our models, remember we saved it into a folder called train. So over here. And the best model in this particular case, I think we won't take the final model. Let's take the one that why is that it's still so small? Okay, so let's take it at, what is that? So 67 looked like it was okay. So let's take the 70K model and take that one from there. So, and again, this hasn't exactly been trained for that long. You'd want to train for significantly longer. So we're going to go model equals ppo.load. And then we're going to go into our train folder. And then we are going to load the 70K model. Right, so that's our model.loaded or model loaded. Then we can use our evaluate policy method, which we brought in as part of our HPO. So this one over here, I can actually just copy that. And we can paste. So we're going to get mean reward. I think the second value is either standard deviation or mean episode length. I don't think it's mean episode length. All right, so we're going to pass in evaluate policy, and then what do we need to pass to that again? I think it's the model, then environment. Yeah, model, environment, and then the number of episodes. So we can go model env and eval episodes equal to, let's do 5. And if we want to render in here as well, we can pass render equals true. So this will actually allow you to see it evaluating the model in real time. So if I bring that over to there, make sure that's looking good. So what have we written? We've written mean underscore reward, comma, underscore equals evaluate underscore policy, model, env, render equals true, and eval episodes equal to 5. Okay, that's looking good. How are we doing for time? Tutorials getting super long. Let me know what you think of the long tutorials. I'm always curious because, I mean, these are pretty extensive and they go through quite a bit. They're almost like mini courses, right? All right, so if we go and run that. Okay, so you can see he's just blocking, right? So it's not all that good. And I noticed this happening when I had the learning rate a little bit too fast. The model would just learn and it'd just block. It wouldn't actually do anything. So in this particular case, not performing all that well, right? So I would take that as an indication that learning rate's too fast, haven't exactly trained for long enough. So he lost that first one. So let's actually try a different model rather than using that one. So let's try the 10K model. So we're going to load up the 10K. All right, so he's actually doing some more stuff now. So you can see. So fine tuning might have actually hurt us in this particular case because we're just trying to train way too quickly. Still not that great, right? He's kind of dying in this particular case. Now, if we actually, let me actually show you what you get back from me in episode reward because I keep stopping it. So if let's just set an eval episodes to 1 so we can actually see one full run. Run that. So he died again. And you can see that this is running really, really quick. Like, so this is just the default testing loop. We can actually slow this down using time.sleep when we actually write our own custom loop. All right, so you completely lost there. And what we should get back from the evaluate policy is the mean episode reward. So if we go and print out mean reward, so it's 3,600. Now, it'd be interesting, right? Let's actually test out our hyperparameter tuned model. So if we type in opt, and grab one of those models. What was the best one? 5. So let's load that. Run that. Died in that particular case. Not that great. Okay, that's performing better. All right, that's actually scored a win there. But again, we haven't trained this for that long. So if we eventually in the final results montage, I'll show you like a fully trained model. So let's see. All right, so we've got significantly higher mean reward from the Optuna trained model. So fine tuning in this particular case probably went a little bit too fast. Probably definitely need to drop down that learning rate, maybe train for a lot longer as well. Okay, so that's how we can evaluate it using the evaluate policy method. So that gives you an idea of how you can actually go about doing that. We can also do this using a custom training or testing loop. So the core change here is that rather than using env.actionspace.sample, we can use our model. So model, I think it's just model.predict, and then pass through our observation. Let's actually test this out. So OBS. Just copy this. So observation.shape. So if we type in model.predict, if we pass through OBS, so what we get back from that is our action. So we just need first value. Right, so that is our action right there. Now if we type in env.step, right, so that is going to work. So if we grab this, so model.predict, and bring that into our testing loop, So paste that down here. This should effectively allow us to go and pass through our prediction. Let me actually explain this. So if I type in action equals model.predict, and so to our model, we're going to be passing through our observation, and then we need to get that first result because it's vectorized now. Then we can take this action and pass it to our env.step method. So this will effectively allow us to actually go and pass through an action to our environment rather than just taking random values. So if we bring this back over to the side and run this now, so you can see it's a little bit slower. We're actually able to see what's happening. See Ryu actually getting some hits. Hadouken. So this is at least just some testing, good to validate that your model's working. What I'll normally do when I'm actually testing this stuff out or training, I'll actually have a separate testing notebook alongside the actual training notebook. So I'll actually train and test at the same time so I can see and make sure that we're heading on the right path. So that gives you a chance to actually not wait until the end to see your model has performed like crap. You'll actually be able to see it in real time. So that's just some practical advice. So these actions still seem kind of a little bit random at the moment. Probably not that great. But this sort of gives you an idea of how to actually go about and test your model. Now, okay, so Ryu's one up, and he's probably about to die in a second. Okay, so he's died. Yeah, okay, right? And again, we definitely haven't trained for long. So we've trained for 30,000 steps using, this is still the hyperparameter tuned model, right? Not the fine-tuned model. With fine-tuned model sort of went to crap, but that sort of gives you an idea. All right, so we're going to stop this now, but you sort of see how this actually goes ahead. Let's actually wait for this to finish. So we'll actually see one full game. This is so addictive. I ended up watching this for so long when I'm training these models. Yeah, it's still very random at this stage. Probably going to lose. All right, so Ryu's lost. So that's one full episode now done and dusted, or one full game, right? But that sort of gives you an idea of how to actually go about testing your model and evaluating it in real time. So we're printing out all the rewards, but you can see that we're getting rewards back as we're hitting our opponent, or Guile in this case. Now, that is the coding bit of this done. So I'm going to share the final model weights for this, but let's jump over and see a bit of a results montage. So you can see what this model actually looks like once you get a good training run and once you've actually gone and tuned appropriately. So what I ended up doing with this is a bunch of different things, but I'll actually share what I did, hyperparameters, how long I trained for, so you can actually see some final performance results. Let's jump over to it. So I ended up training this model for a shit ton of time. All up, it took 7 hours to train, but that was like after, I don't know, 2 weeks of grinding out test after test to try to get the damn thing to work. Now, PPO Ryu, what I've affectionately named this bad boy, started to get some decent results after around about 1 million steps. At that stage, he'd learned how to Hadouken and was getting to the point where he was consistently able to beat the crap out of Guile. Now, at times, things did get kind of close, and sometimes he'd get his ass absolutely handed to him, like right about now. But that didn't stop him giving it his all. He gave it a good go, guys. After 3 million steps, so around about halfway, he was getting up to Ken pretty much all the time and Hadoukening the shit out of Ken's equivalent. He'd also Dragon Punch up as a means to knock the crap out of his opponents. But this actually ended up working out pretty well because it meant that he was dodging the majority of the counterattacks just by jumping up and down. Now, this went on for a little while, so I'm not going to bore you with all the runs. However, have I got some crackers for you. This was the first time our little old boy PPO Ryu beat Ken successfully. This happened after around about 3.5 milli time steps. His judo was strong, and he throws the crap out of Ken and dropped the smack daddy on him. Which brings us to Chun-Li. Funnily enough, this didn't seem to be that hard of a level to beat. Because of Ryu's range, he could sit back and Hadouken the crap out of it and win. I managed to capture this absolute cracker while testing though. Double KO. It's so weird. When I was training, I'd find myself cheering for PPO Ryu like it was an actual player. I mean, occasionally I cracked the shits because he was so close to winning, but died. I laughed. I cried. It was a journey, all right? After beating Chun-Li, we were on to Zangief. Now, these runs aren't necessarily consecutive, just some highlights. I'll drop that big banger at the end. Zangief was dangerous. Every time PPO Ryu got close, Zangief would drop an absolute pounding. Yeah. But that didn't stop old boy Ryu from beating the snot out of him when he got the chance. This model was the one from about 4.5 millisteps. The car, oh my god, the car. Well, PPO Ryu dropped a few shots on it, but then just went rogue and decided to shadow box the wall. This was all planned, guys. I mean, yeah, all planned. Definitely all planned. And finally, we got to PPO Ryu playing around 5 million steps. He got to dial sim before he got absolutely pummeled. And then the bastard had the nerve to drop that he beat us due to the mysteries of yoga. Mate, when the fuck did they teach how to double fly kick Dragon Breath? I don't ever remember that coming up at Yoga Barn on Sunday. I mean, I'm down though. Sign me up, like, come on. This brings us to the final run. Now, just to be clear, I definitely didn't record the model playing for 11 hours, 13 minutes, and 4.25 seconds on Saturday morning just to cherry pick a run with sick performance. Nah, definitely didn't happen. Anyway, I'm going to shut the hell up for most of this, but this was a consecutive unbroken run from start to finish using a model trained for 5.46 million steps. I dropped the delta transformation here and it seemed to work a lot better. That being said, kick back, enjoy, crack open a cold one, and let me know what you think in the comments, homies. PPO Ryu versus button mashing. Who will reign supreme? So PBO Ryu finally decided to do some self-reflection and try to beat the crap out of himself. Now, unfortunately, it does end right about here. I figured this is because we actually grayscale our game during training, so the underlying reinforcement learning model, or AI, can't actually work out who is who. That being said, I thought this wasn't too bad for only 7 hours of training. What do you think, lads? Anyway, catch you in the next client combo. Enjoy.
And it's done, dude. What'd you think? Not bad, man. It kind of seems like we're reaching a bit of a cap though. Yeah, I noticed during training, the gym retro environment had a couple limitations. It was built quite a while ago and it used to have this game integration that allowed you to pick up from a certain game state or a game level. I think what would make this model significantly better is to fine tune on each individual level, sort of like applying curriculum learning to be able to boost performance. Ah, nice. So similar to the curriculum learning you used in Doom, yeah? Exactly. Sweet. So what's next? Time to cash in on that gamer money? Start rolling some tournaments? I wish. Maybe a different game. Let me know what you'd like to see, guys. Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell. I always get that order wrong. Anyway, you know the drill. Hit a bunch of buttons. Hopefully you did enjoy this. I mean, I am looking at more games and different types of environments that we can test out, as well as prototyping a whole bunch of different types of machine learning models and AI. Let me know if you're still interested, and if you've got any ideas, hit me up in the comments below and let me know what you thought of this model. Did you enjoy it? Did you enjoy the client conversations? Let me know your thoughts. Thanks again for tuning in. Peace. Have you ever wanted to build your very own machine learning model that is able to play games? Well, in this video, we're going to be doing exactly that. We are going to be building up our very own framework to be able to play different types of web games. Ready to do it? Let's jump into it. What's happening, guys? My name's Nicholas Renard, and in this video we are going to be building our very own reinforcement learning model to be able to play the Chrome Dino game. So we're going to go through all the steps required to get this up and running. That includes installing all of the dependencies, building up the custom environment, which tends to be the most difficult bit about doing this type of thing. We'll train it and then we're going to test it out. Now, even though we're doing this on the Chrome Dino game, you could take this to just about any other type of web game. The only nuance that you're going to need to take into account is how to define the reward and how to control the different types of actions. But we'll talk a little bit about that as we go through it. Ready to do it? Let's get to it. So Nick, you've done a bunch of ML work with games, but can you actually do it without a pre-built game? Like, say, a random game on the net? Look, we can give it a crack. I'll take it. What's the first step? Well, while there's a bunch of approaches to doing this, we're going to use reinforcement learning. It's a similar technique to what we've used for other games. This time though, we're going to be using the DQN algorithm. And the first step? Well, we're going to need to set up a bunch of dependencies and install stuff. But first things first, let's head on down to the breakdown board. You going to welcome us to it or what? Welcome on down to the breakdown board. So guys, in this video, we are going to be teaching a reinforcement learning agent how to play the Chrome Dino game. Now, there's quite a fair bit involved when it actually comes to actually building this up. Now, the first thing that we're actually going to need to do is set up our custom environment, which tends to be the hardest part in terms of doing all of this. In terms of our custom environment, there's going to be a couple of key things that we need to do because we are going to be using the stable baselines framework. So first up, what we're going to do is create a new environment class. And even though we're doing it for the Chrome Dino game, we could do this for just about any web game, depending on the complexity of the reward function, as well as the complexity of the controls. We're going to be able to get our Chrome Dino game. Actually, I don't like drawing this in red. It's more like, let's give Chrome Dino a gray. So let's imagine our web game here. And let's say we've got a little cactus and our Chrome Dino. That's going to be our dinosaur. So what we're actually going to need to do is implement a function which is able to extract a couple of things. Now, namely, this is going to be wrapped up inside of our web game environment, but our web game environment is going to be hooked up to this game. Specifically, the first thing that we're going to need to do is implement a get observation function. Now, in order to do this, we're going to be using a library called MSS. And this allows us to perform a screen capture. So imagine, let's say we've got our camera. So that is going to be taking photos of our web game, which we'll then be able to apply through OpenCV to do a little bit of pre-processing to get the exact type of frame shape and frame output that we actually want for our deep learning model. So we're going to run that through OpenCV. And then once we've done that, we're also going to need to implement a slightly more custom function. So imagine our game is running. What we want to be able to do is determine when our game is over. So let's imagine game over pops up on the screen. We are actually going to use embedded machine learning or deep learning to be able to extract that out. So we're actually going to be using the Tesseract OCR library. So Tesseract OCR to actually be able to extract the game over text. And this will be able to be used as part of our reinforcement learning environment to determine when the game is done. Now, this is really important because when we actually define our environment inside of the stable baselines and OpenAI Gym framework, we need to be able to determine when the game is actually done. Reward is another really important thing, but we're going to simplify this. So for every single frame that we are alive, we are going to give reward or set equal to reward or set our reward equal to 1. So effectively, we're just going to be rewarding our agent for staying alive. Now, in terms of our reinforcement learning, we are going to be using a library called stable baselines. Baselines 3, and we're going to be taking our environment. So let's imagine our environment as our game with our Chrome Dino. Surely by the end of this, I will be able to draw a better dinosaur. Little arms. We're going to be taking that environment and passing it through to a DQN model. And our DQN is going to learn how to actually play that game. So out of this, what we're going to get is a model which we can then use to actually play our game. So will I be able to have a Chrome tab up with our game actually playing, and this will actually go and run the game and ideally get a massive high score. Don't expect it to be that massive. I didn't end up training the model for all that long, but you get the idea. We'll be able to take our web game, we'll be able to train a reinforcement learning agent, and we'll actually be able to get it to learn how to actually play to maximize that reward. Let's get coding.
Alrighty guys, so we are going to be building our very own Chrome Dino AI. Now we're going to be using reinforcement learning for this, and ideally the end goal should be that we have some sort of model that is able to play the Chrome Dino game. And if you don't know what I'm talking about when I say the Chrome Dino game, you can go to Chrome / and it's pretty much this game. The game where you basically, the goal is to get the dino to jump above the little cactuses, right? You sort of get the idea. Now, what we can actually do is train a AI model to ideally try to play this. Now, that high score that you can see there of 444, that's actually from the model that I was training last night using AI. So I got to 241, but you sort of get the idea. So the goal is to be able to use a Python model to be able to learn how to play this. Now, admittedly, it does take a little while to train this using reinforcement learning, but nonetheless, we're going to give this a crack and see how we go. So there are 4 key steps or 4 key things that we need to do. That my OCDs kick in, that's not the right size. There's 4 key things that we need to do. So first things first, we need to install and import some dependencies. Then we are going to build the environment. Now, a lot of you have been asking me for this type of tutorial and showing you how to do some reinforcement learning on a completely custom environment. So stuff that doesn't have a pre-built OpenAI Gym framework for it. This is exactly what we're going to be doing in this tutorial. So once we've set up our environment, we are then going to train our model. And then last but not least, we are going to test it out. So first things first, what we're going to go on ahead and do is install and import our dependencies. Now, the first dependency that we are going to need is PyTorch, because the reinforcement learning framework that we're going to be using is Stable Baselines 3, which requires PyTorch. So in order to install PyTorch, we just can hit stable, Windows, or choose whichever version you want. So I'm going to choose stable. You could choose Mac if you want, Linux if you want. I'm going to use Windows. And then pip, I'm going to choose the language that I want to install for, which is going to be Python. And then I'm going to choose CUDA 11.3 because that is the current version of CUDA and CUDNN that I've got installed. Then all I really need to do, let's just double check I'm grabbing the same one that I've got. Yep. So all we really need to do is copy that command and then throw it into our Jupyter Notebook. I've already uploaded this Jupyter Notebook into GitHub. So if you want to go and check that out, let me make sure my Zoom's working. If you want to go and check that out, go to github.com/knickknocknack/Dino AI. And I've actually got the fully written Jupyter Notebook all available there for you. So you can give this a crack and actually test it out. So the end goal will be to be able to get our Dino to actually play this game. So let's give this a crack. So first thing we need to do is install, PyTorch. So I'm going to include an exclamation mark and paste in that command that we just copied from PyTorch. Get rid of the pip or the 3 in pip3. So the full command should be exclamation mark pip install torch, torch vision, torch audio. And then this bit is really dependent on whether or not you've got or you're using a GPU. So I've got a GPU on this machine, so I'm going to use a GPU. If you don't have a GPU, that's perfectly okay, guys. You don't need to stress. So the extra bit is --extra--index--URL, and then it's https://download.pytorch.org/wheel/cu11.3. So that is what drives which version of CUDA we're going to be using. So I can run that command, and I believe I've already got it installed. So you can see it's gone pretty quickly. Now we can take a look at the versions that I've got. So if I type in pip list, everyone usually likes to see this. So where's Torch? So right here, I'm using 1.11.0 plus CU11.3. So you can see those versions installed there. So I am using the CUDA accelerated version. That being said, for this particular type of training, regardless of whether you use a GPU accelerated machine or not, you're going to get pretty similar training times, at least because we're not doing stuff in parallel and we're not going to get that much of a boost from it. But nonetheless, that is PyTorch now installed. Now, the next thing that we need to do is install stable baselines and protobuf. So let's go ahead and write that command. Okay, so that is our next command written. So this is in, let's just double check that's run successfully, looking good. Okay, so the next command is exclamation mark pip install stable-baselines 3. And then inside of that, I've included the extra command to install all of the extra stuff for stable baselines 3. And then we've also gone and installed protobuf. So this was something actually quite recent that I noticed I had to have installed. There was a change in the protobuf package, which I believe is used for the training of the PyTorch model. So just keep that in mind that you've got to install, or at this moment, I'll update the notebook if it does change. So equals 3.2.0 or 2.3.20. And then an asterisk. So this sort of gives us a version within 3.2.0. Or 3.20. Oh God, I don't know why I'm saying that wrong. All right, so we've now gone and installed stable baselines. And for those of you that haven't checked out any of my previous stable baselines videos, so stable baselines is an absolutely amazing, reliable reinforcement learning framework. So think of it like the scikit-learn of the reinforcement learning world. It is really, really good, particularly when you're trying to do hardcore reinforcement learning problems, because you don't need to write them yourself from scratch. So that is stable baselines now installed. Now, in terms of how we're actually going to work with Chrome Dino, this is one of the funnest things one of the most fun things that I've actually done as of late. So to capture the Chrome Dino frame for our game, we're going to be using OpenCV, so that's not an issue. To send commands, we're going to be using a library called PyDirectInput. And this allows us to actually use Python to actually send commands, and it's very, very quick. And that's a huge advantage when it comes to working with reinforcement learning. You want it to be fast. Then the other thing that we're going to be doing, which is my personal favorite, is that you can see that right now we've got this game over tab over here. Now, what we want to be able to do is once an episode finishes, so think of an episode as one round, we want to be able to detect when that round is over. We're actually going to be using optical character recognition to detect when this game over sign pops up. Now, because we're not going to do too much pre-processing, we're really just going to detect the game section, but that's perfectly fine. We're actually going to set up a function that determines once this game over pops up. So we've got to bring in, or we've got to install a bunch of stuff to be able to do that. So for the PyDirectInput, we're going to install PyDirectInput. For the OCR bit, we are going to be using PyTesseract. which is Google's OCR tool for Python, which is pretty cool. So you got full-blown detailed installation instructions available on the site. So if you do get issues with my installation, then you know where to come. But really, it should just be a PyInstall PyTesteract. Coolio. But there are also some dependencies. So what do we need? So we need at least Python 3.6. You need PIL to be installed. You need to install Google Tesseract OCR. So if you actually go to that, it's actually going to walk you through how to install all of this stuff. Is this really just a pip install? I don't actually remember installing this, but I must have installed it at some stage because it looks like it is working. Oh yeah, so you can install it via the pre-built binary. I think this is what I ended up doing. Yeah, so you could just go to the binary over here. So download the Windows equivalent and then run through this. So make sure you got Tesseract OCR installed to begin with, otherwise you're going to have a bad time. Then we're just going to install the Python, effectively, what is it, like a wrapper to be able to use that. So let's go on ahead and do this. If you need more installation, I'll include links or more info on the installation for Tesseract. I'll include links in the description below, as well as some other good YouTube tutorials that show you how to install it from scratch. Okay, but for now, what we're going to go on ahead and do is just install the Python component. So we are going to include !, pip install, and then install those last couple of libraries. Okay, those are our last couple of libraries now installed. So we've gone and written one line, and that is !, pip install MSS, PyDirect input, and PyTesseract. I think MSS was for PyDirect input, PyDirect input. It was either for PyDirect input or PyTesseract. I think, oh yeah, so wait, we're using MSS for the screen capture. So that's actually what allows us to capture the screen. So MSS is being used rather than, I thought we were using, what was it? OpenCV, we're clearly using MSS. And there was actually a great YouTube tutorial that I watched recently that showed that MSS was faster than OpenCV. So hence, that's why I ended up bringing it over into this. But keep in mind, there's a bunch of different ways that you can do that. The PyTesseract bit is also optional. I saw another guy doing it using looking at the overall color in that particular region rather than trying to actually extract the text. So a bunch of ways to do this. This is my way. There's a bunch of different ways that you could actually go about this. But this is the way that I also wanted to teach you, not necessarily just my way. Okay, so what do we got? Got some installs. So we're installing PyTorch, installing stable-based lines, and then installing all the stuff that we need to be able to extract a frame, which is what we're going to use MSS for. PyDirect input is going to allow us to send commands, and PyTesseract is going to allow us to extract the game over component. So we've installed all of those. Now what we need to do is import them into our notebook. So let's go on ahead and do that. Alrighty, those are all of our dependencies are now imported. So we've gone and imported MSS, and MSS is going to be what allows us to actually capture the screen. So it's ridiculously quick. Let's actually make some notes of this. All right, so MSS used for screen cap. PyDirect input is going to be used for sending commands. And this is effectively telling the game or passing commands to the game, right? So it might be WASD, might be pastoral click, might be up and down. For Dino, it's pretty easy. It's literally just jump up or jump down to, or duck down to dodge the birds. You sort of get the idea. OpenCV, I can't remember exactly what we're using that for, but we'll see it soon enough. So OpenCV allows us to do frame processing. NumPy is just a transformational framework. Let's actually walk through these commands. So the first one is from MSS, import MSS. So that's our screen capture. Then PyDirect input. So import PyDirect input. Then we're bringing in OpenCV. So import CV2. Then we're bringing in NumPy. So import NumPy as NP. And NumPy is just great for working with a bunch of different types of arrays of different ranks. So that definitely helps us out. Then we are bringing PyTesseract for OCR. So that line is import PyTesseract. So we are bringing this OCR for game over extraction. We are then bringing matplotlib to visualize frames or captured frames. And that line is from matplotlib import pyplot as plt. So that's bringing matplotlib. We are then bringing in time or pauses. And that line is import time. So between when we actually send commands and while we actually wait for the frame to change, so we're going to bring in time. So this gives us a little bit of leeway when actually going between different actions within our game. So I've used this in a bunch of places to actually perform pauses. So just keep that in mind. It's really just to take a little bit of a sleep, have a nap. And then we're bringing in our environment components. So the first one is from gym import env, and this is going to be the base class when actually defining our own environment down here. And then we've brought in a couple of different types of spaces, and for this we've brought in from gym.spaces import box and discrete. So box is going to be used to extract or to represent the shape of our game input, which is just going to be an image. Discrete is going to be used to represent our possible actions within our reinforcement learning environment. Now, remember, a reinforcement learning environment is all to do with 4 different things. So if you remember Area 51, agent, reward, environment, and action. So we need to define all of those in order to have a valid environment. So we're going to be using our spaces down here to be able to define that. So those are our inputs. So MSS, PyDirect input, OpenCV, NumPy, PyTesseract, matplotlib time, and then we've brought in a bunch of stuff from OpenAI Gym. That's pretty much all of our dependencies installed and imported now. So it doesn't look like we've got any issues there, but the only one that I can think of which might be a little bit tricky is PyTesseract. So I'm going to link in some additional stuff in the description below so you've got that sort of covered. But for now, that is our setup all done. Let's jump back on over to our client and have a chat.
Alrighty, so that's the 1,000,001 dependencies now installed. What next? Well, this is where the magic happens. This isn't gonna turn into one of those close-in magic videos, is it? So, we're going to be building the environment for the ML model. This is what allows the machine learning model to interact with the game. This is the hardest part about training reinforcement learning models for games. It's often done using different types of architectures, which include virtual machines and containers to scale how fast we can train. Got it. We keeping this simple or what? Sure are. We're going to use the OpenAI Gym framework to do it. Let's roll.
Alrighty, so now that we have our virtual environment now installed with all of our dependencies and all of the frameworks that we're going to need, we are going to go on ahead and build our environment for reinforcement learning. Now, our environment that we're going to be creating is going to be called a web game environment. So we are going to create a new class and we're going to call it web game. And we are going to pass through our base environment from OpenAI Gym. So we're going to pass through env there. Now, there are a bunch of different methods that we need to implement for a base environment when working with OpenAI Gym. So the first one is the init method. And we're just going to define these initially for now. We're not actually going to write them out. So we're going to set that to pass. The next one is step. And typically to that, you pass through an action. So the init method is sort of where you do all your setup and you define all of your different environment variables, what your environment actually looks like, so the shape, so on and so forth. The step is actually what gets called, right? So let's say, for example, you wanted to take an action inside of your game. So let's say, for example, you're playing COD or you're playing, I don't know, Fortnite, and you wanted to strafe right or strafe left. So actually moving to the left and moving to the right is actually an action. So in terms of actually passing through an action to our game, we can pass that action through to step. Now, how we represent that can be done in a whole bunch of different ways. We're going to take it pretty simply and have, I believe, 3 actions. So do nothing, jump up, or just go down. Now, we'll play around with this in a second, but just know that init is where you set up stuff. Set up the environment and action and observation shapes. Step is what is called to do something in the game. And typically you get a reward, the next observation, any information, as well as whether or not the game is done. So that's the return out of your step environment. Then we typically also have a render function, def render, self. and this allows you to visualize the game. Not all that important for ours because we're actually going to have the game on the screen, so that's perfectly fine. And then we also have a reset function, so almost like restarting the game. And we are also going to need to implement a couple of custom functions as well, or custom methods. So we are going to implement one called def get observation. And that is going to be called to get the output of our game. So we'll actually pre-process, or over here, we'll actually pre-process and get a specific region out of the Dino game. So we might get, I don't know, like 100 pixels by 100 pixels just to cut down, because we don't really care about looking too far forward. Although that might be an optimization that you choose to do later on. It's definitely something that you could do. So this is going to get the part of the game that we want. Get at the observation, it's pretty much part of the observation of the game. And then we also want a get done function. Get the done text. Get done. So this actually checks whether or not the game is over. So whether or not we've actually got game over being displayed on the screen. So we will be able to check that out. Okay, so those are our 1, 2, 3, 4, 5, 6 functions. Let me check. Step, reset, render, close. Oh, we also need to close. So close, this closes down the observation. OBS, oh gosh, I can't type today. So def, close, pass through self, and pass. Okay, so those are our 1, 2, 3, 4, 5, 6, 7 different methods that we're going to need to fill out. Now we're going to take this one step at a time, so you'll see how each one sort of gets built up. So we'll probably do init first, and that will set up our initial game. What we'll then do is we'll probably take a look at the get observation, get done, and we'll probably need to do steps sort of simultaneously. But for now, let's first start by setting up our initialization function. So here we're just going to make sure we initialize the base environment as well. And we're also going to set up what our action and observation shapes look like. So let's do this. Okay, that is the beginnings of our init method. So we've gone and written 3 lines of code there. So the first one is subclassing our model. So we're calling super.__init__, and then open and close parentheses. So this allows us to use the base class. Then we are setting up our spaces. So these are really, really important whenever you're defining any reinforcement learning agents. And I'm going to walk through this. You'll probably see this being referred to a bunch of different times. So the first thing that we've actually gone and defined is the observation space. So self.observation space equals box, and then the low value inside of our box is going to be 0, high value is going to be 255. This is really just saying we're going to have a multi-dimensional array as the returned output, right? So that is all that it's saying. So box is sort of a little bit more of a free form shape. So you could have images. Typically you'd use box for images, you'd use box for time series data, and a whole bunch of others. And then we're specifying our shape. So our shape is going to be one batch, and then we're going to be 83 pixels high and 100 pixels wide. And the data type is going to be numpy u into 8 because it's a very small and compressed data type, which we like. And that is our observation space. So basically we're saying that we're going to give back an image. Our action space is going to be discrete 3. Now we are going to have 3 different actions. So spacebar, which is jump up, 1, which is down, and then the third action that we're actually going to have is no operation. So inside a step, we're actually going to define an action key here. So action key. So action 1, and discrete is really, let me actually show you. So actually, I'll show it to you once we actually create an instance of this model. So 0 is going to be spacebar. 1 is going to be is going to be duck, which is down. And then 2 is going to be no action, commonly referred to as no op. Cool. All right, what have we done there? So that's fine. So that is open. Positional argument follows keyword argument. We need an equals here. Boom. Okay, let's see if we can create an instance of this class. I don't see anything let's get rid of that pass for now. So if we said env equals web game, okay, no issues. So if we went env.actionspace.sample, this is exactly what I wanted to show you. Okay, so you can see here that when we're creating out, or when we're running action space, we're getting number 2. Now, what we're going to do inside of the step function is we're going to map number 2 to no action. So this means that we're not going to do anything, right? So our agent will just keep running forward. Our little Chrome Dino won't do anything. Now, if we go and sample again, we're getting action 1. Action 1 is going to be duck. So typically you want to duck when you've got birds coming at you. Action 0 is going to be spacebar. So if we sample again, so we're getting action 0, which is going to be a spacebar, which means that our little agent is going to jump. So this is pretty common whenever you're working with other environments, and you've probably seen me use this a bunch of times before whenever I'm building reinforcement learning models. So the action space typically defines what actions you can pass to the game. env.observation_space.sample is going to be a representation of the image. So you can see that that's the image. Now keep in mind we imported matplotlib, so we might be able to go plot.imshow. Let's see if this works. Doesn't look like it wants to. Let's grab the first value. There you go. So that's what our image is actually represented as right now. So obviously it's a bunch of random values because it's just creating random values whenever you're whenever you're accessing the observation space. But for now, just know it's a bunch of random values at the moment. Eventually, we are going to be representing this as a set of values from our Dino, right? And you can see it's 80 pixels high by, 100 pixels wide, or 83 pixels high by 100 pixels wide. That is that representation there. So 83 pixels high by 100 pixels wide. Cool. All right. So we've now gone and defined what our spaces look like. Now we also need to define some classes. So we want to define our MSS class. We also want to define where our game location is. So what positions we want to extract from the frame. So let's go and set these up. Okay, so we've gone and written another 3 lines of code there. So let's zoom in on that. So the first one that we've gone and written is self.cap equals MSS. So if you actually go to the MSS library, Python. So it does allow you to create cross-platform screenshots. Now, typically you're defining MSS as a first instance, and then I think we're using the grab method to be able to grab captures from our actual frame. There you go. So this actually allows you to grab specific areas of the frame, and we can define the regions as top, left, width, height to be able to grab a specific area of the frame. So we don't need to grab everything. We can actually grab a specific area. And this is the next line, or this brings us to our next line. So keep in mind, the first line that we've written is self.cap, and we're setting that equal to the MSS class, which we imported right back up at the start. Then we're creating a new attribute, so self.gameLocation. So this is going to be the entire area of the game that we want to potentially extract. And we're specifying this as top equals 300. So this is the region from the top, and then how far in we're going. And then we're grabbing everything from the left. So we're going to go down 300 pixels and go from there. We're going to go all the way from the left, and we're going to extract 600 pixels wide by 500 pixels high. So this basically just defines the region. So self.game.location is just defining the region that we actually want to go and extract. Likewise, we're doing the exact same for the done location. So self.done location, and then we're actually getting back the region that represents where done is. So top is equal to 405, or top, so we're going 405 pixels down, and then we're going 630 pixels from the left, and then we're grabbing 660 pixels wide by 70 pixels high. So that defines where that done section is going to be. Now, what we can actually go on ahead and do is actually set up our get observation and get done functions, because we've sort of defined the stuff that we're going to need to be able to define those. So really, we're going to grab that capture and we're then going to pass that through to cap.grab. We'll pass that self.game location to be able to get the region of the game. Now, when we actually go and run this, we're actually going to take our Jupyter Notebook and sort of run it like that. So we've got our Jupyter Notebook running here and then our game running in the background. So we can actually have them running simultaneously because that's what we're going to need. So that is our init method now done. So we've gone and subclassed our model. We've gone and set up our spaces. And remember, we set up our observation space and our action space. And then we also defined our extraction parameters. So we defined the MSS class because we're going to use the .grab method to be able to grab our frame. We've defined our game location and our done location. And I also showed you pretty sneakily how to actually create an instance of this environment. So I've written env equals web game, and this is just creating a new instance of this class up here. And then we can use env.actionspace.sample to sample our actions. Boom, 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 boom. And then we can use env.observationspace.sample to sample our different or our observation space. So, and we've also used matplotlib to be able to visualize that. And right now it's just a bunch of random values because we haven't actually gone and effectively grabbed our observation, but we can do that. So let's actually go and do our get observation function first. So we're going to use the get observation method inside of this step to be able to get the capture of our game. So we actually want to be able to go and extract this and maybe do a little bit of pre-processing. That's where we're going to use OpenCV. So let's start defining this. Okay, so that is the initial line for our game, and we're going to take this one a little bit more step by step than usual. So the first thing that we're doing is we're grabbing a raw screen capture. So let's actually remove all this stuff to begin with, and let's see what the completely raw capture looks like. So we are running self.cap.grab, which is using our MSS line over here to be able to grab the screen capture. And then to that, we're passing through self.game_location. So this is going to allow us to get our initial screen capture. So if we actually go and run this, create a new instance of our game. Now, if we actually run env.getObservation, let's see if that works. So it looks like we've got a screenshot. Now, what we actually need to do is extract the value from that. So I believe we can use mp.array to grab it. Let's try this. And that is a NumPy array representation of our getObservations function. So now if we pass this through to plot.imshow, maybe we can grab our game capture. Keep in mind, this is going to be from our current screen, right? So right now it's grabbing the code. So it's very meta. But if I move this over to this side, moved our notebook over and brought it back up. Wrong one, this one. If we go and ran this again, so we're now grabbing our frame capture for our game. Pretty cool, right? Now, right now it is pretty big. So we actually want to compress this down to be in the same shape that we had over here. So 83 by 100 pixels. So we're actually going to compress this down a little bit because right now it's pretty big. You want to compress your image sizes down when actually working with a DQN algorithm. So compressing it, passing through smaller frames is going to serve you a lot better in the long run. So we actually want to return np.array. So remember, we actually wrapped it inside of the array to grab the actual pixel values. So now if we run this, we can get rid of numpy.array here. All right, so rerun that. Boom. Okay, so we're already getting our frame. If we move this bad boy over. Right, so we're getting our Chrome Dino. Let's move this. Let's bring this first. Right, so we're getting our Chrome Dino each and every time. If we went and played a little bit, you can see that is exactly that. So we've now got a array representation of our frame. Pretty good, right? Okay, so the next thing that we actually want to do is we want to convert this into a NumPy array, and we want to convert the data type into np.uint8. So we want to get that done because right now it is not np.uint8. Let's take a look. Let's see how it's represented. Oh, it already is uint8, so we don't actually need to do that transformation. So we're actually okay there. So let's leave that for now. We don't actually need to go and do anything else there. Okay, so Once we've done that, the next thing that we do want to do, however, is we actually want to go and reshape this. While we're at it, let's just double check the shape. So we are 500 by 600 by 4. We don't actually need 4 channels. And I wonder if this is an output of MSS. So let's go and grab the last 3 channels rather than 4. So if we go all channels, all so all, all height, all width, and then let's grab the first 3 channels. See what that representation looks like. Pass it through plot.imshow. Okay, that's still looking okay. So there must maybe be an alpha channel coming out of MSS. So if I go and run that again, still looks good. Let's take a look at our data type. NPUint8. All right, so we're looking good. So if we didn't have the correct data type as well, just by the way, we could type in .astype and then np.uint int8. We go and run that. So again, we're uint8, but we can actually drop that. We don't need this because it's already returning the correct data type. Boom, uint8. Okay, so that's looking good. So we've now got our raw screen capture. So we've gone and written self, or let's actually take the full line. So raw equals np.array, and then to that we are grabbing or using our MSS screen cap from over here. So we're running self.cap.grab. Let me zoom in on this so you can see that. So self.cap.grab, and then to that we are passing through the game location. And remember, the game location represents where in our screen we actually want to capture. And then we are wrapping it inside of a NumPy array to actually extract the pixel values. And then we're just grabbing the first 3 channels because I believe there might be an alpha channel or I don't know, a specific 4th channel that's coming out of MSS. We only want the first 3 to actually allow us to work with OpenCV to reshape it and whatnot. Okay, so that's the first line done, and that's probably the hardest to sort of get your mind around. Now it's just a little bit of computer vision pre-processing, and that is our observation bit then done. So let's go and finish our get observation method. Alrighty, that is our get observation method now done. So I've gone and written 3 additional lines of code there. So the first thing that we're doing is we're grayscaling. There's a typo there already. So I've written gray equals cv2.cvt color. We're taking our raw output, which I walked you through, and we're converting it from BGR to gray. So this is just a channel color conversion code. So rather than having a color image, which we don't really have color in here anyway, so we're going to focus on dropping it down into a single channel rather than it being 3 channels. So we're going to make it a gray image. Then we're resizing it. So we're resizing it to be 83 pixels high by 100 pixels wide. So cv2.resize takes in width first, then height. Now a NumPy does it slightly differently, just a key thing to keep in mind. So resized equals cv2.resize. We're passing through our gray image, and then we're passing through the height and the width and then the height, so 100 by 83. And then we're reshaping it so that we have channels first, because that's the format that PyTorch and stable baselines actually wants it in. Stable baselines, not necessarily PyTorch. So I've written channel equals mp.reshape. We are passing through our resized image to that. We're specifying that we're going to have a channel first, and then we're going to be 83 pixels high by 100 pixels wide. And then we're returning channel. So if we go and run this now, we go and get our observation. We've got our observation. If we go and run plot.imshow, it's going to throw an error. If we get that, reduce the first channel, boom. That is our image representation. Looks terrible right now. Let's actually go and grab our Dino. Boom, that's our Dino representation. Pretty sick, right? So we've now gone and grayscaled down. We're getting our image successfully. And if we wanted to go and convert it properly, so we could type in cv2.cvt color, CLOUR, and then pass through that observation. And I think if we go cv2.color underscore BGR to RGB, maybe. See what that looks like. What have we typed in there? We haven't typed that in. RGB. Okay, there we go. That's looking better already. So if we go and run this, there you go. So that's what our actual representation looks like. So I've just gone and passed through the color conversion code to work with matplotlib. But we've now successfully actually gone and got our frame out. Pretty cool, right? Now, we're actually going to use this get observation function inside of our step method. So we're actually doing the most involved bits first. So once we've gone and done this get observation bit, we know we can extract our observation. The other thing that we need to do is be able to extract our done text. So you can see that we've got game over there. So we want to be able to extract that as well. So we're successfully getting our observation. Let's actually move this down because this is pretty useful. We don't need the sample bit anymore. We don't need the action space anymore. We'll come back to that. So the next thing that we want to do is we want to go and use OCR to be able to get our done text. So let's go on ahead and do that. So we are actually going to use PyTesseract for this. Okay, so I've just gone and quickly done written 2 lines of code there. So I've written done cap equals self.cap.grab. Remember, this is using MSS again to be able to grab our done screen, and then we're passing through done location. So remember, in our get observation bit, we used self.game location. For our done method, we are using self.done location, which was defined over here. Now, if you're doing this on other games, you might need to tweak these 2 parameters to be able to get the specific regions of the screen that you want to get. So I've already sort of predefined this to make your life a little bit easier. But if you're doing something like, I'm trying to think of a game. We played around with Timberman. We might specifically have Timberman in a specific section of our screen, and we might point our game location to that, and then our done location to a specific other region to be able to determine whether or not a particular episode is done. So defining these are really important. And I've sort of just taken a little bit of the hassle away for you to be able to know where to get it from. Okay, what have we gone and defined here? So we've now gone and defined where our done component might be. So let's actually minimize that bit for now. So if we actually go and run env, or let's actually reinstantiate our environment, env.getDone, it's just returning our screenshot. Now, if we wrap this in a NumPy array, you can see we are now getting our array values back. And if we wrap that inside a plot.imshow from matplotlib, we're getting a black bar region. Now, if we move this over to the side, let's try that again. So you can see that we're getting game over. I don't want that there. I want it around about here. Boom. So you can see that we're now getting the game over region. So we've now successfully gone and grabbed that text, but we haven't determined what is actually in that region. Because let's say, for example, bring it back up quickly. So let's say, for example, I went and ran this right now. I'm not actually going to have anything inside of that region which represents game over. So we actually need to do some sort of detection to determine whether or not the game is actually over in that particular or at that particular time step. And this is where PyTesseract is going to happen. So before we forget, let's just wrap this in a NumPy array to actually extract the picture values. And remember, this shape is going to have that 4th channel as well, right? So let's type in .shape. Yep, so we just want the 3 channels. So we're going to go at the end of this. So we've closed the NumPy array. No, we haven't. So let's close that. And then we want the first, all of the height, all of the width, and then we want the first 3 channels. So that is that done there. So let's go and take a look at that again. So if we go and run env.getDone now, boom, we've got 3 channels. Let's just move this over to the side. And then if we run, well, my head is probably covering that, isn't it, right now? Let's bring this up a little bit. So env.getDone, and then if we type plot.imshow, you can see that that is grabbing that region. Let's let it get done. Get done. Boom. So you can see we've at least got game over. If I move this over a little bit more, boom, we're getting game over. Cool, right? Okay, that is looking good. So what else do we need to do? We now need to do the PyTesseract bit, so actually do the OCR on this region. So because PyTesseract is a little bit finicky if you don't do pre-processing, we're actually going to just take a look at the first 4 values within our text. So we're actually going to go and just define a list of strings that are valid. So valid done text. And we're just going to focus on the game bit. So I'm going to create a new variable called done strings. And if you wanted to do more pre-processing and play around with PyTesseract a little bit more, you definitely could. I just found giving it a few options is a little bit faster. So what I noticed when I was actually testing this out is that it would read the game text for Chrome Dino as game or GAHE. So rather than specifying for, or rather than forcing Tesseract to look for game, I'm just going to say, look, if it's either game or GAHE, consider that done. So we're going to grab the first 4 letters that PyTesseract extracts. So let's go and do this extraction, and then we'll be able to wrap this up, or at least wrap the get observation and get done functions done. Okay, that is our OCR bit done. So we've now gone and defined a new flag. So I've just set done equals to false. So initially we're going to say our episode is not done until we go and validate whether or not we've detected game or GAHE inside of our game over area. Now, the reason that I don't look at the over bit is because for whatever reason, PyTesseract does not like this V and does not like this E. So it reads it in too many variables to actually count. Now, again, you could go do like some dilation and some other pre-processing to actually force it to look a little bit better, or look like the text it actually represents. In this case, just doing it this way is way faster. But you could definitely go and fine tune this and do as I say, not as I do. So you could definitely make this a lot better. So then what we're doing is we're defining a new instance of PyTesseract. So we're going to save the value out of the image to string method inside of a variable called res. So I've written res equals pytesseract.image to string. So this is the function that actually does the optical character recognition. And to that, we're going to pass through our done capture. So what we had from over here to that. So effectively, this line is looking at that game over region, and it's trying to extract any text from that to a string. So then what we're doing is we're grabbing the first 4 letters, which ideally should represent game. And we're double checking whether or not that string that's been extracted from here is inside of this array. So if the string that's been extracted is game or GAHE, then we're going to set done to true, which effectively means later on we'll end our episode. So we'll cut off our AI there, or the training of that episode there. And then I've specified a return, or we're going to return the done value. So whether or not true or false, it's done. And we're also going to return our done capture just so we can visualize that. So let's actually test that out now. So if I go and run our web game environment again, so let's run this. So our visualization still looks the same, but now let's just bring this up here a little bit. Right. And if we now go and run get done, this is going to return 2 values. So hold on. Okay, so it's running. So you can see it's detected true. So that's good. So let's just say this is done, and then this is done cap equals emb.getDone. So this is saying that we have in fact finished the game. So it's returned. It looks like it must have detected game. And if we go and visualize our done cap, plot.imshow, done cap. Boom. So we're detecting game over. So in that particular, if I move this over a little bit more, I know it's a bit of a pain. I'm recording on one screen, but you sort of get that. Let me zoom out. Maybe you'll see it. Oh, that's much better. So if I go and run that, looks like it's detected game over. Bring it over a bit more. Boom. All right. So you can see that that has definitely detected game over. Let's actually return the res value as well, just so we can see that initially. So we're going to return res, which should be the PyTesseract text. So let's go and redefine that. So our OCR has detected game. Pretty sick, right? We've gone and detected the game over region, and we have gone and set done equal to true. So that is our done capture now done. All right, so that is looking good. Let's zoom back in. We don't actually need to return the res bit. We're not going to need that for our game. So that's just extracting our code at the moment. Not all that useful. We've gone and extracted our done and done cap. Boom, boom. Okay, so now actually this is a good test, right? So you can see that right now we're currently just grabbing the black text from our code editor, which is a Jupyter Lab notebook. And you can see that it has not detected done. And that's because there's no done on the screen at the moment, which is a good sign. So it is actually working well. Okay, so what have we done? So we've gone and now defined our getObservation method and our getDone method. We've also gone and set up our init method. All that's left to do is wrap up our step, render, and reset and close method. Okay, so still a little bit to do. So first things first, let's go and wrap up our step method because that is quite possibly the most important method. So the first thing that we're going to do is we're going to map our action to an actual key. So we're going to create a new dictionary called action map. And we're going to say action 0 is space. Action 1 is going to be down. And action 2 is going to be no op. So we can now use that as like a translator between our discrete space, which remember just returns 0, 1, or 2, to be actually able to represent an action. So then what we can actually do is use the PyDirect input method to actually go and trigger an action. So we're going to say if action doesn't equal 2, so as in it doesn't equal no op, then actually pass through the action from our action map, right? And to do that, we can type in PyDirect input dot press, and then we're going to pass through our action map and then the actual action that we are getting from over here. So inside of our step method, we're actually going to be passing through an action. So this is actually going to do something to our game. All right, that's looking good. So that's our action taken care of. Then what we want to do is define our, so we want to double check whether or not the game is done. So to do that, because we've got our get done method, this is going to make our lives pretty easy. So we can go done, comma, done cap equals self.getDone, get done. So that's going to tell us whether or not we're done or not. And then what we're going to do is we're going to return back the new observation. So new observation equals self.getObservation. And then, so the way that we're going to define our reward, so let's actually just make some comments. So this is checking whether the game is done. Get the next observation. Actually say next observation. We'll just say new observation, whatever. You sort of get the idea. And then, so that's those two done. Then our reward. So we're just going to say for every second or for every frame we're alive, we're going to reward our agent with 1. So reward. And this is pretty simplified, but you could definitely go and make this a lot more sophisticated. But keep in mind, the way that you get a high score in Dino is by staying alive. Now, if you stay alive, then we should be rewarded. Hence, we're just going to set the reward equals to 1. So I'm going to say reward equals 1. Now, this basically means that we get a point for every frame we're alive. Cool? Cool. So let's quickly go through that again. So we've gone and defined our action map. Now, remember, when we call step is what we do every single frame of the game. So it's like taking an act, looking at the observation and doing something. That's effectively what our AI is going to be doing. It's going to look at the game and go, hey, what's the next best action? It's going to pass action to the step function. And then our action map is then going to map through a 0, 1, or 2 to either the space bar or the down bar. If there's 2 return, then it's not going to do anything. And in order to actually go and press that button, we're going to use PyDirect input.press. We're going to pass that action through our action map. So it's going to translate a 0, 1, or a 2 to a space or a down. Then we're checking whether or not the game is done, and we're going to grab the new observation, and we're also going to reward our agent with a 1 if we are still alive. We are also going to return an info dictionary. This could have just about anything in it. I just normally set it to blank unless I really need something, because that is what the stable baselines framework expects. And then we're going to return stuff. Order is very important here. So we're going to return the observation, which is new observation. We are then going to return our reward, which is just going to be 1 if we're still alive. We're going to return whether or not we're done, and we're going to return info. Cool. That is our step function done. So let's zoom out a little. So we've now, inside of our step method, we've gone and defined our action mapping. We've gone and defined whether or not we're done, and we've grabbed our new observation. We've gone and defined our reward, which is just going to be a 1 point for every single step we're alive. If you wanted to, you could also maybe do some OCR on this value over here. So maybe extract the 42 values it doesn't really matter. We can define our own reward because it's in relation to our agent learning anyway. But for more sophisticated games, you might actually want to extract the value. Let's say, for example, you're playing Forza and you wanted to extract lap time as a metric for how fast or how good your AI is. You could definitely go down that route. And then we've defined an info dictionary because that is what stable baselines wants. So that is that now done. I think we're looking good there. So what else do we need to do? So we need to do our render and our close. So these two are pretty much aligned to each other. So let's do these. So our render is just going to use OpenCV to show our screen. So cv2.imshow. We are then going to pass the current frame. So we haven't actually gone and set that. So, all right, let's do that. So over here, so rather than what we can actually do is just type in self.cap.getObservation. Wait, no, self.cap and then self.game location. So we could do that. Actually, we don't even need to do that. We can just pass through. So self.getObservation is going to grab back that value anyway. We could probably just go self.getObservation. And maybe this works. So cv2. What is it? .wait key. If cv2.wait key. So basically we're checking whether or not we're giving ourselves some time to render. And 0xff equals odd q. And then we're going to close. Let's check whether or not that works. We need... Where's our render? Add in a column there. So I've just written cv2.imshow. So we're going to show the game frame. And to that, we are going to pass through self.getObservation, which should get our observation from here. We could also set... So I realized that previously what I'd actually done is I'd gone and saved the current frame as a variable inside of this. But looks like I haven't done it this time. So that's what I've done in the past. Then we're double checking whether or not we've hit Q on our keyboard. And if we have, then we're going to close down our frame. So if I go and run this, render or run env.webgame, if I type in env.render, no, we've got an error. SCN is 100. That is not happy. All right, so we've got an issue there. Let's try to close that down. Doesn't seem to want to close. All right, let's double check this. Let's try self.cap and then what are we going to do? Self.game location and then pass through a NumPy array. So maybe it doesn't like the fact that it's grayscale. I don't know, maybe. We're going to convert it into a NumPy array, and then we're just going to grab the first three channels. So bang, bang, and then first three. Try that. Still doesn't like it. MSS object is not callable. We need to run self.cap.grab, don't we? Okay, that didn't throw an error. All right, so that looks like it's rendering now. So we should be able to hit Q. Doesn't like that. Anyway, at least we've got part of a render function. Doesn't look like it's the nicest render function, but you could definitely go and do that. To be honest, the render function, I know I'm sort of getting an out here, but the render function doesn't matter all that much because we've got the game playing live, but you could definitely go and extend this out a little bit. I've sort of just gone and written this on the fly here, but I think we need a better method to actually go and... I wonder if we just did plot.imshow. Plot.imshow, and then if we went and substituted this over here, I'm going off on a tangent now. Self.getObservation. And remember, we need to grab the first value. And if I got rid of this, what's happening here? Doesn't like it. Not a value. Supported values are accent. Does not like that. Oh, now I really want to get this done. All right, so self.cap.grab, self.game location. And then I thought that would work by itself. Boom. What's that error there? Oh, we need to convert it to a NumPy array. Element-wise comparison failed. Plot.im show game np.array self.cap.grab self.game location. What are we actually doing in here? So we are going grabbing first 3 channels. Should still work. Is not a valid name for supported values. I don't know. Doesn't seem to want to work, that render. I reckon let's go back to the cv2.im show, although I'm not all that happy with the way that that works. I would definitely go and tweak that. So this works, it just hangs massively. Like it'll return that. If I go and run render again. It's not, oh, sorry, it is changing. I just don't like it. It's not the nicest render. Do you know what I mean? Like it's a little bit janky. What about if I brought this? No, so it is working. Okay, we're going to accept that. It works. The close is not that great. All right, let's go and run the render again. All right, so you can see it's definitely working. It's just a little bit shaky because OpenCV doesn't like being in the background. But anyway, all right, so we've got that working-ish. I'm going to take that as an ish. Can definitely be improved in the future, but you saw that matplotlib was not playing all that nice. OpenCV's okay, but it doesn't move all that great. And I believe that's because we're actually working inside of a Jupyter notebook. If you did this in a random or a separate Python script, you should be okay. Okay, but that is that done. The next thing that we're going to do is just make sure we can close down this frame. So we are going to run cv2.destroy all windows. So that will close the render function. So you can see that we've got our little render boy over here. Boom, boom. So that's rendering. Now if we run env, oh, my head's probably covering that. If we run env.close, there you go. So that's destroying that. All right, so it's not that bad. So if we run env.render, env.close, env.render, env.close. All right, I'm going to take that as a win. That looks okay. So if we go and bring our Chrome Dino over to here, so if we run env.render, we'd have our render back there. Yep. env.close. Cool. Bring our Chrome Dino. env render. Boom. env close. All right, cool. That's looking okay. We're going to take that as a win-ish and then go from there. All right, so what else do we have to do? So we've gone and done our render, we've gone and done our close. The last thing that we really need to do is just restart our game. So do our reset function. So what we want is that when we get to this stage, effectively, if you just click anywhere, it's going to restart the game. So we just need to simulate a click using PyDirect input to finish our environment to basically say, once our game's over or once we've detected done, we want to be able to go and reset this game. So we need to go and define a reset function. So let's go on ahead and do this. Alrighty, I think that is it done. So all we're doing inside of our reset method is we're just waiting a second to make sure the game pop up, or we're giving ourselves a second to actually go and reset. Then what we're doing is we're just clicking somewhere up here and then hitting spacebar. And that actually is going to be what our reset method actually simulates. So then we're done. We go and click up here, hit spacebar. That is effectively what our reset method is going to do. Okay, so we're done. Let's bring this over here. And let me zoom out just a wee bit so you can see what I've gone and written. So I've gone and written 3 lines. Let me zoom in. Well, I've zoomed out and then I've zoomed straight back in. So I've written time.sleep1, and this basically says sleep for a second. And then we're saying PyDirect input.click. So we're going to be clicking up in this region. So X150, Y150, somewhere around here. And then we're saying PyDirect input.press space, which kicks off the new game. And then we're going to be returning the next observation. So return self.get observation. So if we go and create an instance of our web game, and then if I type in env.reset, so So right down here, env.reset. There you go. That's resetting our game. So I didn't click. It actually just went and reset our game. All right, let's bring our notebook back up. So if I go and run env.reset again, waits a second, clicks, and then kicks it off. Cool. That is our game effectively now working. So we've now gone and built an entire custom environment. I know it's a little bit sketchy, me trying to put the frame over there, but I sort of wanted to show you how I actually built this originally. That is our environment. And that's what it takes to build a custom environment for custom games. So this is obviously a simple game. You can imagine how hardcore this actually gets for way more complicated games. So we went and defined, let me zoom in to 150. So we went and defined our init method, and inside of that, we set up our observation space and our action space. We then defined our step method, and this is what happens. It's effectively what to do with our game. We created our action map. We created our get done functions, our get observation functions, which are down here. We also set up our render method, which is a little bit janky at the moment. I'll admit, could definitely be better. But I think that's because we're doing it inside of a Jupyter notebook rather than just a straight Python notebook. We also implemented our close method, which closes down our observation method if we use render. And then we went and set up our reset method, which effectively moves over the screen, clicks, and then hits spacebar to kick off a new game. So that is our environment now done. Is there anything else? That is it. So now what we can go on ahead and do is test out our environment, which we've pretty much already done, but let's go and do it again. So we can create a new instance. So to create an instance, we type in env.webgame. Then what we can do is type in or get our observation. So observation equals env.getObservation. And we can use plot.imshow to visualize that, which does not like that. What do we need to do? Oh, we need to get the first value as well, don't we? Right, so that's our observation of our current frame. Let's move this over to the side. Keep it up here. Boom. Let's get our observation again. So that's our little Chrome Dino. And what we can do is do the color conversion. So cv2.cvt color. And then if we pass through, what is it? cv2.color underscore bgr to rgb. Close that. Right, so we've now got a grayscale observation. So we're looking good there. We can also check whether or not our game is done. So remember, we can type in done, comma, done cap equals env.getDone. Print done, comma, we won't print done cap. So that's saying our game is not done, but that is because hold on, it should have picked up done. Plot.imshow done cap. But that has not picked up that. Let's try that again. Let's just move this over a bit. All right, there you go. So maybe it's because my screen's covering it a little bit too much. All right, so that is clearly detected that our game is done. So if I go and run that, you can see it is definitely printing out true. So ideally, we might want to ensure that when we're actually training this, we actually move this Jupyter notebook off to the other screen to actually get that. So key thing to note, important when you're actually prototyping. So again, it's hitting true. We can go and print out our done capture. You can see it's got game over there. Alrighty, and then again, we can use PyTesseract to go and test this out. So if I type in PyTesseract.image to string, pass through done cap, you can see it's printing out game or if or whatever. And this is what I was talking about. So like the game over bit doesn't always work, but we know that the game bit is coming out pretty strong. So if I just grab the first 4 values, 4, you can see we're getting game. So we are looking good. Now we can obviously go and test this out in a bit of a loop. So let's actually go and write a typical sort of testing or training step for a reinforcement learning environment. You would have seen me write a ton of these before. So let's give this a crack. Okay, that is our testing loop. So I've written for episode in range 10. So this means that we're going to play 10 games. Play 10 games. Then the first thing that we do whenever we're actually testing out or working with a reinforcement learning environment is we reset it. So observation equals environment.reset. Because remember, when we call reset over here, we're actually returning the observation because we're calling self.getObservation. Then we are creating a flag. So done equals false. We're creating a counter. So for our total reward, because remember, we get 1 point for every frame we're alive. And then we're looping. So while we're not done, so while we're not dead, we are getting our observation, getting our reward, getting our done value, and getting our info by running env.step. And for now, we're just sampling. So we're just taking random actions on our environment. So it might jump, might duck, might do nothing. We're then accumulating our total reward. The total reward plus equals our reward. So that's from one episode or from one frame. And then we're printing it out. So I've just done some string formatting. So print, and then I've got the F at the start to format the string, quotes, total reward for episode, and then inside of curly braces, I'm returning the episode number is, and then I'm returning the total reward again inside of curly braces. So if I move this over to here now, and let's zoom out a bit so we can see it. Just to make sure our OCR actually picks it up. So if I go and run this now, you can see that that is now effectively running. Should run again. So this is me not touching the screen. My hands are here, right? So this is our environment just doing its own thing. You can see it's effectively picking up when our game is over, taking random actions. And that is our environment now done. I know a lot of you have asked for how to actually do this. This is how to do it. So we've now gone and created our own custom environment. You could definitely scale this out. If you had containers or virtual machines, you'd be able to run a bunch of environments at the same time. But in a nutshell, that is our environment now running. And if I bring this over here, let's go back. Let me stop this. So if you actually go and take a look, we are printing out our episode reward. So total reward for episode is 11. Let me zoom in so you can see that a bit better. Total episode for total reward for episode 0 is 11. Total reward for episode 1 is 13. Total reward for episode 2 is 11, 12, 13, 15, 16, 17. So you can see that we are effectively running pretty successfully. So that in a nutshell is our environment and our reinforcement learning environment now done and tested. Let's jump back on over to our client and have a quick chat.
Alrighty, now that that's done, we can start to train the model. Sweet. You mentioned something about DQNs? Sure did. We're going to use a deep Q network to train our Chrome Dino. Nice, let's do it.
So we are on the home run now. Now, all that we have left to do is set up a callback, which you've seen me write a ton of times before. So I'm just going to copy the code in. And then all we really need to do is build a DQN and train this up. So first things first, let's go on ahead and bring in the stuff to create a callback. And again, this is the exact same callback that I use every time when I'm building a reinforcement learning agent. So if you haven't watched some of the previous reinforcement learning videos, by all means, do go and check that out. So first things first, we're going to import OS. So this just helps us navigate a file path. We are then going to import the stable baselines base callback. And we're also going to import the stable baselines environment checker. So this just makes sure that when we actually go and train our DQN, we have a valid environment. So I'm going to bring those in. And then the first thing that we're actually going to go on ahead and do is check our environment. That looks like we're still okay. So iProgress not found. I think we're still okay. All right. So the first thing let's go on ahead and do is we're going to check our environment. So we can run env checker.check env, and then to that, we're going to pass through our environment. Now I'm just going to move this over to the side and get our Chrome Dino up. Let's just wait for ourselves to die. Okay, we're looking good. So let's actually go and pass through our environment. My head's probably covering this. So env_checker.check environment, or check env, and then we pass through our actual environment to that. So let's go and do that. And if this returns nothing, that means that our environment is valid, right? So no errors. So let's double check. So you can see there, no checks, no errors. Looks like we're running okay. Then we can create an instance of our callback. And I know this is a little bit of a pain, me coding on here and having the game on the same screen. If there's a better way to do it, let me know. But hopefully this is useful in the long run. We're going to bring in our callback. This is the exact same callback that I've used in every single reinforcement learning video. And effectively what it's going to do is it's going to save our model into a folder called, or we need to pass through our save path. We're going to save it inside of a folder called train. So just create an instance of that folder and you should be good to go. Boom. Then what we're going to do is we're going to create two directories or two paths to directories. So I'm going to create a checkpoint directory. And I'm going to set that equal to /train. And I'm going to create a log directory and I'm going to set that equal to /logs. And so I've already got a folder called logs in here. So these are some previous runs. I'm also going to give you the checkpoints that I used for the final training model. So I actually trained this overnight. So it got okay. It wasn't the most perfect model. You probably want to train for a lot longer to get a perfect model. Maybe fine tune that reward as well. Okay, so we've gone and defined, what have we gone and done? So we've brought in a bunch of dependencies. We've check that the environment is okay. We've also gone and copied over our callback and we've gone and set up some directories or set up some directory paths. The next thing that we want to do is actually create our callback. So let's do that. So I'm going to say callback equals train and logging callback, which is this over here. So you can see that's that class. And then to that, we're going to pass through how frequently we want to save our model. We're going to say every 1,000 steps. You could change this if you wanted to. This just means it's every 1,000 episodes or every 1,000 steps. So one frame is one step effectively. Every 1,000 frames, we're going to save an instance of our model. And we want to specify where we want to save this to. So we pass through save path equals checkpoint directory. Close that down. All right, cool. So that is our callback bit now done. I know I went through that pretty quickly, but I've done that a bunch of times before. If you have any problems, do let me know. But for now, that is our callback now done. Okay, that is step 3.1 now done. Now what we can do is actually go to step 3.2, build and train our DQN. So the first thing that we need to do is import a bunch of stuff from stable baseline. So let's do that first. Alrighty, so we have now gone and imported our DQN algorithm. So that's pretty much it. We can import a bunch of other stuff. So our monitors, our vec frame stacking. But for now, we're just going to use the DQN algo. And if you actually go to the stable baselines documentation and take a look, there's a whole bunch of information on how to actually go and play around with this, how to actually go and spin it up. But obviously custom environments are its own unique thing. Now, I highly recommend you go and have a look at the papers as well as go through this stable baselines code. It actually gives you a ton of information as to how the DeepQ network algorithm actually works. And we've previously done a lot of work with PPO, not so much on DQN, but for now, if you get to test out DQN, see how we go. So let's add a comment there. So import the DQN algorithm. Now, the next thing that we're actually going to go ahead and do is actually train. So we're going to create a model and we're going to instantiate an instance of the DQN model. So create the DQN model. And then to that, we are going to pass through that we want to use the CNN policy because we're going to be passing through an observation from our game, which is effectively our little Chrome Dino. We're going to pass through our environment, which is our web game environment from over here. And then we are also going to specify a TensorBoard folder that we're going to be logging to, which is going to be going to our log directory. And then what else do we need to specify? So verbose equals 1. So this means that we're just going to be logging out our results. We are going to set our buffer size to, what is it? 1.2 million. So this is how many frames we collect inside of our DQN buffer. The buffer underscore size equals 1.2 million. And then we are also going to specify our rate or where we actually start learning. So learning starts, I've set that equal to 1,000. Okay, so let's break down that full line. So I've gone and written model equals DQN, and I've specified that we're going to be using a CNN policy. To that, we are passing through our environment, which is the environment that we just went and built. We're specifying TensorBoard underscore log. So if you actually wanted to go and take a look at your logs later on, every time you create a new DQN or a new PPO model, it's going to log out into this folder, and you can actually go and specify or spin up TensorBoard and actually view that log. It gives you episode rewards and episode length, so a lot of information there. But you also get it by specifying verbose equals to 1. You'll actually see that in the frame. Now, DQNs train off a buffer, so we're actually specifying how big our buffer is going to be. You might need to bring this up or down depending on how much RAM you have on your computer. So I've got, I don't know how much I've got on this, like 32 gigs, I think. Performance, memory. Yeah, so I've got 32 gigs on this machine. Hence, I'm able to get up to 1.2 million. You might want to bring this down. Keep in mind, to fill up a buffer that size, it's going to take quite a while anyway. So you might perfectly be okay bringing this down. And then I've specified where we actually start training our algorithm. And I've said that kick this off after 1,000 frames or 1,000 steps. Now, again, you can play around with these hyperparameters as well. And if you wanted to, you can actually go and use OpTuner like we did in our Doom video to go and fine tune your models. Oh, wait, no, we didn't do it for Doom. We did it for Streetfighter. You can go and take a look at those as well. All right, so that is our DQN now instantiated. Doesn't look like we got any errors there. Now what we can actually go and do is kick off some learning. Now, I'm not going to run the entire learning rate or the entire learning run for this video. I'm actually going to, we'll train for a little bit, and then we'll actually be able to see what it looks like as we're training. And then what we will do is I'll show you how to load up some pre-trained weights, and you'll be able to test that out. Okay, so the next thing that we actually want to do is kick off training. So to kick off training, we can type in model.learn. And we are going to specify how long we want to train for. So I think for the other model or the final model that I'll show you, I trained that for 88,000 steps. That took all night. So if you extrapolate that out forward, it's going to take quite a fair bit of time if you wanted to train for longer. For now, I'm just going to say 5,000 times steps to be completely reasonable to get this video done in time. But you could definitely go and train for longer if you wanted to. And I highly recommend it if you want to build something that's a little bit more bulletproof. Then, to ensure that we save our model, we can pass through callbacks, and we want to pass through our callback from over here. If we close that down, if we go and let's bring our script over to this side, and I'm just going to make it a bit smaller, zoom out a bit. So I've written model.learn, let me zoom in now, model.learn, and then I've specified total time steps equals, let's bring this over here. Total time steps equals 5,000. So you could definitely increase that. And this is effectively sort of like epochs when you're training with TensorFlow or PyTorch. So the longer the number of time steps, the longer your model's obviously going to train for. And then we'll specify our callback as equal to callback. Now, I'm not expecting a very good model after 5,000 at all. After 88,000, it still wasn't even perfect, but it was definitely a lot better. But you'll actually see that in a second. So what we'll do is we'll kick off training, and what I actually recommend is taking this off or taking your Jupyter notebook off to the other side and then starting the training run. So I'm actually going to kick this off. It'll actually hide it in the background anyway. So we can actually start this off. It should go over. That is our model now training. So you can see it's jumping a bunch, dead. It should start a new episode. There you go. That is our model now training. So we'll let this train for a bunch of time. So the full 5,000 steps, and we should be good to go eventually. Oh, it almost jumped over. So this is it learning. So we'll let it run and we'll be right back. Alrighty, so I let it train for a little while. So the training actually never started. But you sort of get the idea. That is the framework for actually going on ahead and building this. So it obviously takes quite a while. So you can see that the frames per second is only 2 frames per second, which is really, really slow. So I think that there's got to be a better way to actually go and define this, but it is still training. So that is our model at least starting to explore and starting to learn about how to actually go and build up or actually play a lot better. Now, rather than doing this completely from scratch, I've actually gone and pre-trained one, which you can actually go and test out. But that is the framework. So if you wanted to go and train for longer, all you needed to do is go and run model.learn for a whole heap longer, and you'd actually be able to go and kick this off. So I think I actually trained this for 88,000 steps. You can obviously go and train for way longer. It's obviously going to generate a significantly better model. But now what we can actually go on ahead and do is load up our model. So if we actually go and take a look inside of our train folder, so because we never got up to 1,000 steps, it didn't save either. But let's actually let this train for 1,000 steps. So we'll actually be able to see a save effectively. So actually what we can also do is we can drop this to 300, and then that way we'll actually save a model. So let's drop this to 300. I'm going to bring this over here. Just want to show you what it looks like once a model's saved, and we'll train. So rather than leaving learning starts at 1,000, let's say learning starts straight away. So we'll set that equal to 0. And then if we kick this off, we should effectively start training straight away. So if I go and run model.learn again, we are training straight away now. We might have stopped the training. Let's go back. We had an error there. What's happened? Do we kick that off? Keyboard interrupt. All right, let's go and kick this off again. So if we go and let me just move this over to this side a bit more. There we go. Okay, so now as soon as we start training, we are effectively training the algorithms. Just make sure. There we go. Looks like it's kicking off again. Let's give it a full 300. So we effectively, or a full 1,000. So we effectively get a couple of models saved. But again, 1,000 is going to be nowhere near enough to get an actually high performing model. So let's let that save. I'll actually let it save one model and I'll show you what it looks like. We'll be back.
5 minutes later.
Alrighty, so that has gone and finished training, that quick training run that I sort of wanted to show you. So you can see inside of the train folder, you've now got models saved at 300, 600, and 900 time steps. So that sort of shows you that the callback is actually working in that particular case. Now we can also view what our model performance is looking like. So you can see our learning rate, the loss. Ideally, you'd want to see that drop over time, as well as the number of updates that our model has actually gone through. Now, before we go through this in any more detail, let's jump back on over to our client and see what's left to do.
Alrighty, Nick, you're gonna bring this home or what? Time to test it out? Time to test it out. We'll give this a crack through the Chrome browser, but keep in mind you could apply this design pattern to just about any game. Let's wrap this up.
Alrighty, so all we've really got left to do is test out our model. Now, what we can do is let's test out our model just with the model that we actually went and trained, which ideally is probably gonna suck, or not ideally, it probably will suck. And then we'll test it out with the one that I trained for 88,000 steps. Now, 88,000 steps is by no means the be all and end all when it comes to training these models. You'd ideally want to train it for a ton longer. But in this particular case, that's what I've trained it for overnight. So to be able to get this out this week. Cool. So what we're going to do is first up, we are going to write a test loop, and it's pretty much going to be exactly the same as what we did here, with the core difference being that we are going to, rather than sampling random actions, we're actually going to use the model that we trained just up here to actually save, or to actually go and play the game. So let's go on ahead and make the updates to this. So we're just going to play one game at a time and kick this off. So let me go and tweak this and we'll be able to test it out. Alrighty, those are the only tweaks that we needed to make. So I've gone and added this line here, which is actually taking in our observation. Let me zoom in. Are we zoomed in? Zoomed in? Yep. All right, cool. So what we're doing is we're taking the observation that we originally got back from resetting our environment and we're passing it to the model.predict function. So model is actually our DQN model, right? If we actually take a look. So you can see that it is our stable baselines DQN model. So that is our DQN model right there. So we are taking the observation that we got from that model and we are passing it through to model.predict. And what we're going to get back from that is the action and then this, I can't remember what the second bit is. Let's try that up. So do we have an observation? We do. All right, let's try that. Model.predict, pass through our observation. So you get 2 and then I can't remember what the second value is, but you do get something back from that 2 values. So what we actually need to do is unpack this. So we need to get the action and then get that second value out. So all we really need is the action. So that action is going to be what we pass through to our environment.step function, because remember, our environment.step function is what actually takes an action on our game. Then I've added a sleep between taking actions and I've added a sleep between games as well. So that's the only real change that I've added there. So now if we bring this over to the left-hand side, we can test out our model. So let me zoom out a little. So this is our agent actually playing. If we go and run this, this is our agent actually playing in real time. So right now it doesn't look like it's doing very much. It's just running straight into it. And that's our agent actually going and running through. So you can see that the reward that we got for that episode is 27. So not all that great. Now what we could actually go on ahead and do is load up one of the pre-trained models that I've got. Now, in order to load a pre-trained model, I've got some of these inside of my folder called train_first. Now, I've also got these available on GitHub, so just keep that in mind. So if you go to the Dino AI folder, I've got this best model.7zip that you can unzip. So you need to un7zip it, and then you'll be able to load it up into here. So I had to compress that a little extra to get it to fit. Okay, so I want this one. So to load, I'm going to load the 88,000 one, which is over here. So I can type in model.load, and then we are going to pass through the full path to that specific model. So os.path.join, and then we're going to go into train first. And then we want best_model. I didn't actually check how this was performing this morning, so who knows, it might still not be all that great. But if you train for longer, the performance improves drastically. So just keep that in mind. Do we need to include .zip? We don't. Okay. Right, so we've now gone and loaded our model. So if we now go and try playing, bring our Chrome Dino back. Let's see how this performs. Not all that great. Let's try doing, I wonder if it's actually gone and loaded it. So DQN. Let's pass through the full file path. Let's get rid of that. There you go. So you can see it's at least jumped over 1. Let's let it run for a little bit longer. Let's actually give it a couple of steps to run. Let's play 10 games. There you go. 1. Nope, not getting over the second one. All right, it's getting over 1 at least. This is quite poor performance, guys. 1. So it's got over 2. I wonder if the sleep is making it suck a little bit. Hold on, let's remove the sleeps. Let's try that again. We can also test out another model, see if those are performing better. There you go. There you go. There you go. Hey. Hey. It's all right. It's died on 98, but you can see it's at least learned a little bit better on as to how to actually go and play the game. All right, 104. So that 444 high score there, that actually happened last night during training this model. So it's definitely able to learn. There you go. Come on, just a little bit further. There you go, 183. So you can see the model has definitely gone and learned how to play this a whole lot better. Obviously removing those sleeps allowed it to perform a little bit better. It's not always going to perform amazingly every single time, but you can see it's definitely playing the game. It's getting there. It's able to jump over. I don't think it ended up training with the birds, so I wonder how it would actually interact if it actually got some birds flying at it, but you never know. It's not bad. All right, 261, not too bad there. So you can see it's learned how to play the game. That was with 88,000 steps. So I'll obviously give you the fine-tuned model for this, so you'll actually be able to test this out yourself and play around with it. But that sort of gives you an idea as to how you can actually go and build your very own reinforcement learning model for just about any game. And you can obviously extend this out, train it to play a whole lot better. You're just going to need to fine-tune the reward that you actually give your game. But that in a nutshell is that over and done with. So we went and did a ton of stuff. We went and built our own custom environment. We went and trained a model. We went and saved a model. Hopefully you found this a little bit useful, guys, and I'd love to see what games you eventually end up applying this to. And let me know if you end up training this for a whole heap longer. I'd love to see what the performance looks like. It's performing not too bad. That's 200. Oh yeah, come on. 300. Dream run, come on. $424. So you can see it's definitely getting there. It's obviously performing a lot better. It's learned how to jump over cactuses. So I'm going to call this a reasonable level of success, but we could obviously go and take this a whole heap further. It's not letting me, let me move this over. We're going to call that a success. So you can obviously see the rewards are being logged out there as well. So we had 178 on that last one, which doesn't necessarily equate to the 444, but this is our own reward function. So again, we did a ton of stuff. Went and built up our model, installed our dependencies, built our custom environment, which is the hardest bit out of all of this. And then we went and trained our DQN model. And again, I've gone and put all of this code up on GitHub so you can test this out and try it out yourself. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell and all that good stuff. And hopefully you enjoyed this reinforcement learning tutorial, because it is quite a powerful skill. You can now take this and sort of start applying it to different realms, to different games. Let me know how you go. If you do apply it to some other games, I'd love to see your results. Thanks again for tuning in, guys. Peace. Thanks so much for tuning in, guys. Hopefully you enjoyed this full, deep reinforcement learning course for gaming. Thanks again for tuning in. Peace.